Ok.
Os alunos também?
É também
Para compor, porque a sala é grande.
Ladies and gentlemen, dear colleagues, dear students, my friends, good morning. I'd like to welcome all of you to this second Pavement Functional Design and Management Symposium, launched the first time 4 years ago in China, in Shang'an University, shared by Professor Hua and Professor Han. I wish you all the best stay with us in scientific terms, as well as in all social aspects. Concerning the organization of this symposium during the next 3 days, please refer to the program, also available on the website. However, I'd like to just remind you about 4 events. The reception today at 7:30 at the Duque de Bragança Palace, just 15 minutes walking from here. Tomorrow, after the last presentation, the visit to the traffic simulator at the CCG, Center for Graphical Computation, followed by the dinner at 8 o'clock, 15 minutes to reach the restaurant by bus from here. And please don't miss the closing session in the last day, Saturday, at 12 with awards and the announcement of the next symposium. Today, after this opening session, our symposium starts with the keynote lecture presented by Professor Hua. Now, I'd like to invite Professor Hua, PFDM founder and chair of the International Steering Committee, to share with us some words about this symposium series. Professor Hua, please.
Thank you, Paolo, for the kind introduction. Good morning, distinguished guests, speakers, and all participants. A warm welcome to the second PFDM. On behalf of the PFDM International Steering Committee, I'd like to provide you a brief background on how this PFDM conference came about. 4 years ago, 2019, in Xi'an, China, we held the first PFDM. The motivation for us to initiate such a conference was that, looking back in pavement engineering, from the early days in the 1950s, after the Ashoro tests, we found that in pavement engineering, major effort focused on structural design of pavements. And structural design has gone through several cycles of revision in terms of concept, theory. In comparison, the equally important functional performance of pavement with regard to its concept and theory has not advanced far enough. Many concepts in use today, for example, the International Roughness Index, serviceability, the skid-resistant concept, has been there 40, 50 years ago, and they are still in use today. It reflects the fact that pavement engineering researchers have not put in enough research effort in renewing such concepts to move with time. 4 years has passed on. Now, looking at the current situation, with the emergence of intelligent vehicles, vehicles are getting more and more intelligent. Now, we need to ask ourselves, the way that we monitor, manage the functional performance of our pavement, are they able to cope with intelligent vehicles? Intelligent vehicles will be quite demanding, more demanding than human drivers. In the last 40, 50 years, we have developed concept, functional index to cope with human drivers. But today, with intelligent vehicles, we at the International Steering Committee feel that we have to move with time. The concept being used today with respect to functional performance of pavement, we believe may not be able to cope with the demand of intelligent vehicles. In this regard, I would like to thank Professor Paulo Pereira, Chairman of the second PFDM, for the great effort in putting together a solid 3-day program consisting of 9 sessions addressing different aspects of functional performance of pavement. I believe in the next 3 days, we will be able to learn and enjoy the research ideas and experience from all fellow speakers in the next 3 days. So I greatly appreciate Professor Paulo Pereira and his team of organizing committee for the effort presenting us an exciting 3-day programs. And we look forward to an enjoyable stay and a good program at Gumaris. Thank you very much.
Thank you, Professor Flan. Closing this session, I have the pleasure to invite the Vice Dean of our School of Engineering, my friend Professor Raul Fangueiro, to address his welcoming address.
Thank you. Thank you for Professor Paulo, and good morning, everyone. And welcome to the School of Engineering of University of Minho. Let me start by greeting all my colleagues at the opening table for this event, Professor Foy and Professor Paulo Pereira, and congratulate them for organizing this event, Pavement Functional Design and Management. Thank you very much for this organization and for selecting the School of Engineering as the hosting institute of this conference. I would like to welcome you all and tell you that it is a great honor for the School of Engineering of the University of Minho to host this event and, above all, to have you with us. Please feel all very welcome to our School of Engineering. I would like also to congratulate Professor Paulo Pereira and, of course, Professor Foy for making possible to hold this prestigious event on our campus, and thank him on behalf of the School of Engineering for his important contribution to the recognition of our school in terms of its research activities. Having been one of the previous presidents of the School of Engineering, it is also a great honor for me personally to be able to share with him at this moment the opening of this event. Thank you, Paulo. I would like also to tell you that the School of Engineering of the University of Minho acting under the motto of Tomorrow Needs Engineering, is recognized for its strong innovation ecosystem, which is made up of the research centers, the technological interfaces, spin-offs, and the companies that are involved in our research activities. It is therefore a school recognized for its generation, innovation model that is composed by 3 different steps: the generation, the valorization, and transferring of knowledge to companies. So we are quite engaged with companies of this region, and not only on this region, in this ecosystem and in this transferring of knowledge. This field of civil engineering is no different in this regard. So with research centers internationally recognized as the CETAC, Center for Territory, Environment and Construction, for their research and development activities, and with a strong connection to reference companies in Portugal and abroad. We may see some of them sponsoring these events. So this is showing the strong link of the School of Engineering with companies. So I wish you all a fruitful Congress and an excellent stay in Portugal. Thank you very much.
Thank you, Professor. Dear colleagues, I have the honor to introduce our keynote speaker, Professor Foix, presented the keynote lecture, Challenges in Design and Development of Sustainable Pavements in the Digital Area. Dr. Foix is currently Distinguished Professor and Dean of School of Future Transportation at the Chang'an University, China, and Emeritus Professor, National University of Singapore. He received his Bachelor of Engineering from the National University of Singapore, Master of Science from the University of Waterloo, Canada, and a PhD from Purdue University, USA. Professor Foix is also actively academically in R&D of highway and airfield engineering and transportation infrastructure management. He has published more than 200 technical papers in leading international journals and equal number of conference papers. He has been invited to lecture in more than 20 countries. He currently serves on the editorial boards journals of 6 leading international journals in the areas of transportation infrastructures, pavement engineering, and pavement materials. Professor Foix is also active professionally. He is the founding president and current president of the Pavement Engineers Society, Singapore, and the founding and the current president of the Asia Pavement Engineers Society. He was the past president of the International Society for Maintenance and Rehabilitation of Transport Infrastructure, ISMARTI. He founded 2 international conference series, namely the International Conference on Road and Airfield Pavement Technology and the Asia Pacific Symposium on Transportation and the Environment, both of which are now in their 12th edition. In 2019, he co-founded the conference series International Symposium on Pavement in Functional Design and Management, PFDM. Professor Foix, please, the floor is yours.
Thank you, Paulo, for your kind introduction. Distinguished guests, fellow speakers, and all participants. It's my honor to be given the opportunity to present a lecture on this topic of challenges in design and development of sustainable pavements in digital era. I greatly appreciate Professor Paulo for the kind invitation for me to share our research team at Chang'an University on various aspects of functional performance of pavements. So I will be addressing the challenges of design, developing sustainable pavement from the angle of functional performance of pavements. Well, these are the relevant issues. Respect to sustainable pavement development, we are all familiar with. It can be classified into direct social concerns, other social concerns, as well as environmental concerns. So looking at the specific items, we have safety, noise, pollution, and also thermal environment with respect to heat island effect, drainage, storm drainage management, and also other concerns related to waste disposal, pavement recycling, and so on. Well, what I'd like to address today is not from the traditional, conventional angle, but from the pavement functional aspect on how it will affect sustainable pavement development. It's particularly of interest today because of the fact that, as I mentioned earlier on, the introduction of intelligent vehicles. Since 2019, we have witnessed the vehicles having higher and higher level of intelligence. And these trend will not stop. The vehicles would only get more intelligent. And we also realize that in the past, human drivers make certain driving decisions which are affected by pavement conditions. But today, when smart vehicle, intelligent vehicle make driving decisions, they are driving decisions which could not be made by human drivers before. For example, in terms of parking, in terms of the speed choice and so on, we'll see more and more decisions taken over by intelligent vehicles, even before we see the birth of autonomous vehicles. Today, long before the birth of autonomous vehicle, which we do not know when it will happen, but from now we can see already intelligent vehicles are making quite a number of driving decisions and is going to be on the increase. So that has a direct impact on how we, pavement engineer, provide a road to serve the traffic. We have to face the demand of intelligent vehicles. They may ask, hey, pavement, what are you providing me to ensure safe driving, low noise, comfort, and so on? We pavement engineers, we can ask ourselves, are we ready? Well, I do not think we can rely on concepts, ideas that was derived 40, 50 years ago. For that matter, we talk about serviceability, International Roughness Index. Do you think it's relevant to intelligent vehicles? I have great doubt myself. IRI was derived not based on a real vehicle. You think intelligent vehicle will believe in us when we tell them IRI? You think intelligent vehicle will understand what it is? Intelligent vehicle is able to make use of IRI to make decisions? I doubt. So that's where we have to think twice what we should do. Intelligent vehicle go for real-time driving information. So how often do we provide roughness information, skid-resistant information to the motorists? Are they able to serve intelligent vehicles? I doubt. We need to provide updated real-time route network condition, weather in different parts of the network. So it's going to get quite complicated, the information we provide to intelligent vehicles. We have to relook at pavement data for intelligent vehicle operations. Well, challenges in the digital era. Now, more and more things are getting digitized. we are looking for an age of digitalization. Besides intelligent vehicles, which demand for information and data real-time, applicability, and accurate data, they are not like human beings. Intelligent vehicles is able to go for accurate data. They are able to process accurate data. And we must realize we are now facing intelligent vehicles. We have to communicate with each of them separately, not as a whole. Each of them are different, not the same. And each of them at any specific time are located at different parts of the network with different payment conditions. So we need to do prediction, monitoring, both in the space and time dimension. It's indeed very challenging. Are we ready? Well, I don't think we are ready today, but we have to be ready. If not tomorrow, I hope not too far in the future. So pavement researchers like us will have to take a second look on the real world, which is changing. We cannot stay on with the old concept and method. We have to move on. We have to look at the new data requirements. We have to look at new data acquisition techniques that are now available because of the advancement of sensing technology, computing capability, and so on. New test methods and devices must be developed to cope with the new data requirements and the new data acquisition techniques available. And with the new data information, more accurate data, time and space-specific data, we have to apply new application analyzing procedures, methods, techniques. So today in my lecture, I will not be able to provide solutions for all those questions that I posed, but I can share with you what we have started to do, trying to address the new challenges presented to us because of the changes in the driving world. I will be talking about safety and briefly noise, thermal environment, and drainage. What are the things that have to be solved? Challenges are there, and we need to address these challenges. First, driving safety, skid resistance. We look at skid resistance, and we have to provide information on stopping distance to intelligent vehicles. Well, I think that's the first and foremost information we will have to provide to an intelligent vehicle on the road. At any single point, we have to provide information on skid resistance and what is the stopping distance. This type of information was not available anywhere. It's not available today. But in time to come, intelligent vehicle will ask pavement engineers for this information. Well, what we have today, we have two major forms of skid resistance measuring equipment. One for high-speed skid resistance measurement, CFME, and on the right, we have low-speed skid resistance measuring devices. Most widely used, the British pendulum tester, and also the dynamic friction tester. Well, the low-speed and high-speed skid resistance measurement each serve its own unique purpose, and we know how to use it to assess the skid resistance performance of a pavement. But are these information that we are providing today good enough for intelligent vehicles? It is a big question mark. On the left, we have all different types of skid resistance measuring devices available today, both high-speed and low-speed skid measuring devices. And on the left, you see the reported values of skid resistance. There are so many different forms of skid resistance measurement reported to users. Are they the same? Well, we all know they are not the same. Are they information that allow us to calculate the stopping distances? I'm afraid the answer is no. So where we stand today, in terms of road driving safety, are we able to provide the needed information required by an intelligent vehicle? I doubt. In fact, when we talk about skid resistance, which number on the far left that we can quote and what they mean? Well, in terms of braking distance, I doubt we can give a real physical meaning, because to calculate braking distance, we really need to know the tire model, the vehicle model, the vehicle speed, water film thickness, and so on. At different point of the network, the answers are not the same. For different vehicle model, the answers are not the same. It's indeed a big challenge. Well, what we need? We cannot rely on the reported values. It doesn't give us the answers that an intelligent vehicle needs. What we need to do? Well, I say first, harmonization. They are all measuring skid resistance at the same point, the same pavement. How can they be different? How can the skid resistance at the single point on the pavement be different? Obviously, all this measurement by different devices, they must mean the same thing. They must convey the same message. So there's a need for harmonization. Second, how do we interpret it? How do we use it? How do we use it in providing useful information for driving safety? The application on a straight road, on an intersection, on horizontal curves, lane changing. What are the skid resistance required for all these different vehicle operation modes? It's interesting. It's not easy. Well, we have to provide we have to start somewhere. So our work, step one, harmonization. We try to make sense out of measurements made by different measuring devices available today. Let's look at what we have done. Well, we start with the British Pavement test measurements. If you look around in the literature, they are easy for us to identify studies that shows that different British pendulum units, depending on the calibration done, you're going to get different answers in British pendulum number that is measured by a British pendulum tester. So this is just an example that how different it can be. RSA, RSB, CED refers to a particular specimen, test specimen. And then there are 5 accredited labs. 5 accredited labs. And you can see the differences you obtain from the 5 different labs. So that present a problem. If you conduct a research, you consistently use one piece of British Pavement tester, no issue. You are able to see the trend of variation. But if in a single study you use different units of British Pavement tester, you're going to have problem. That is what you experience. We try it in our university from 4 different labs, 4 different units. We are having problem like this. So what can we do? What is the problem? And if you look at the calibration requirement by the British standard and ASTM standard, you find that they are not the same. 2 most widely used standards in the world for British pendulum test, the calibration requirements are not the same. And I'm going to show you next what this difference means. Well, first of all, I would like to say that we all know British pendulum number itself doesn't give you the coefficient of friction indication of the specimen tested. It's not equal to 100 multiplied by the coefficient of friction. In fact, it is depending on the calibration you have done to the spring. You'll find that it is non-linear. British pendulum number that reported from test and the actual coefficient of friction between the test material and the rubber slider coefficient of friction, they are not related in a linear fashion. And you look on the right, if we take the British standard calibration limit and the ASTM calibration limit, you'll find that the relationship between ppn and the actual coefficient of friction varies over a wide range. That is the root of the problem that give rise to a range of variation in the British pendulum number reported. So if you look back in all the literature that over the years, thousands of studies using British pendulum tester, and they reported British pendulum number. Can value of different report be compared directly? Knowing this, we know that they cannot be compared directly because they're calibrated using different limits. Well, we see that BPN is just an index. You cannot use it in a skidding risk analysis. ASTM BS standard may cause over or underestimation of BPN, actual BPN. And measure BPN of different BPTs unit cannot be compared directly. And worse, sometimes, depending on your calibration limit, it may lead to different maintenance decisions. Now, how to overcome this? We have a proposal. We take a look at the main mechanical parts of the British pendulum tester, and we develop a finite element model, simulation model, to simulate the actual British pendulum test. And then we discovered something that we can rely on, that for the rubber slider of the British pendulum tester and the test material, there is one unique value of coefficient of friction. So as long as the standard rubber slider is the same, regardless of what unit of device you use, the coefficient of friction will not change. The coefficient of friction will stay the same. So that gives us a basis of reference. So we propose a mechanistic harmonization process based on, well, I should say, based on coefficient of friction. Or we introduce the standard BPN as a convenient measure, but I would like to say that, in fact, the actual comparison of basis for comparison is the coefficient of friction. So all BPN measurements can be converted to actual coefficient of friction, regardless of what unit you use, as long as we identify the spring stiffness of that unit. So you can see, in actual case, the measured, I'm sorry, I'm not very good at this. Anyway, if you look at the measured BPN, the maximum percent difference of 4 different BPT devices, the difference can be more than 20%. In the last column, based on the coefficient of friction, you can see we can reduce the variation of all different units within, I would say generally, or less than 6%. And if you are very accurate in terms of your stiffness calibration, you can go down to 3%. Essentially, we are proposing a mechanistic harmonization procedure for British pendulum tester as illustrated here. Finally, the basis of comparison is the coefficient of friction. Now, it's highly significant in that we are using a British pendulum tester, and at the end, we are able to get a coefficient of friction. The engineering significance of this procedure is that you are able to get from British pendulum test a coefficient of friction value that you are able to use in engineering analysis for braking distance calculation. Of course, British pendulum tester gives a low speed skid resistance measurement. We have to do transformation when you perform an engineering analysis of braking distance. So we are able to resolve different standards, no problem. You calibrate your equipment according to ASTM or British standard. Using the simulation model, mechanistic harmonization, we can get unique value of coefficient of friction. Whether it comes from lab 1, lab 2, different devices, no problem. So that we feel will be able to provide a consistent and unique value which can be used in engineering analysis. Next, I'd like to talk about the high speed. I'd like to talk about the high speed measurement. We're having the same problem earlier on I highlighted. So how do we resolve problem of measurement from device X and another device? The mode of measurement may be different. Different test speed, different test tires, different test loads, different water film thicknesses, and different slip angles, different slip ratio, and so on. Measure value cannot be compared directly. So this problem is more complicated than the BPT issue. Well, it requires more in-depth analysis. So what we can see is that there is a series of skid resistance curves depending on the test condition of the device. What we propose is something very similar to the concept I introduced earlier, a mechanistic harmonization approach. So what we do is to introduce the concept of pavement skid resistance state. So pavement skid resistance state refers to the state of the pavement, independent of the vehicles, independent of the test tires. It's the state of the pavement that counts. And this state of the pavement is defined by the micro and macro texture of the pavement and, of course, the material itself. So again, we make use of numerical model, three-dimensional finite element model, to represent the interaction between a tire and a pavement. Given now, we're going to recall what we did for the British pendulum tester. For this case, high-speed skid resistance testing, as long as the rubber of the tire is fixed, we know there is only one unique coefficient of friction between the rubber material and the pavement material. So that again, we are able to identify one unique value that stays the same regardless of how you test it, regardless of what speed you test, regardless of what water film thickness you use, regarding of what normal load you apply. That coefficient of friction between the two materials is the properties of the two materials, and it will not change no matter how you change in testing. So by applying this simulation model, we are able to analyze test value obtained from different test devices. So this shows the results, the simulation result to obtain. We can see how actually skid resistance varies during the high-speed process, sliding, and skid resistance reduces because of the fact that the contact area between the tire and the pavement surface decreases as the speed increases. So that explains why skid resistance at high speed decreases. Now, one thing still doesn't change. That is, at the point or at the area of contact, the coefficient of friction between the tire rubber and the material changes. What changes is the area of contact and the mode of contact. So with that, we are able to calibrate the tire model for the numerical finite element simulation, and we have verified from past research studies, field studies, measurement using different tires, different vehicles, and we found that the model is able to generate highly reliable prediction of skid resistance that verifies the concept of skid resistant state. That what the skid resistant state refers to is, regardless of the variables you have, but with an input of micro and macro texture of the pavement, which is closely related to the coefficient of friction of the pavement material and the test tire, we are able to generate a series of a family of curves. And that, the concept of pavement skid resistance state states that for a given pavement surface with known micro and macro texture, the tire pavement skid resistance generated under a given set of vehicle operating conditions and environmental conditions, though they include all the variables we mentioned earlier on, then we find that on that particular pavement surface, there is a unique skid resistance value measured once the different variables are fixed. That means for a given test device, all the variables are fixed. For test condition, you'll get a unique skid resistance value measured. And in that case, we can say the skid resistance state of a pavement is completely defined by its surface characteristics. The actual skid resistance value measured varies depending on the speed, water depth, pavement tire properties, slip ratio, and so on. But other than that, we can bring them together using the concept of mechanistic harmonization. And this slide shows what we actually see in what we are doing today using different devices. We have 4 different high-speed skid resistance measuring devices because of the operating conditions are not the same. So on the same pavement, at the same spot, 4 devices are giving 4 different values. They are all correct, although they are all different. They are all correct because they belong to the same state of skid resistance of the pavement. And that is how the concept of skid resistance state explains how different skid measuring devices are giving different measured values. So this mechanistic harmonization, again, can be applied to high-speed skid resistance measurement. And we can apply, using the simulation model, the braking distance of any vehicle under any operating condition. So what we can see, the current skid resistance measuring devices cannot be used directly to predict pavement skid resistance. What we do today, we correlate using statistical method to predict what will happen. But otherwise, we are not able to do it in an engineering fashion. So we are not able to effectively set skid resistance maintenance threshold. We are not able to determine the safe speed for different wet weather conditions. Harmonization has failed in the past. International Friction Index could not do the job. But with the concept of pavement skid resistance state and using mechanistic harmonization approach, numerical simulation model of finite element, we can meet all these above requirements. So this is one example that we are working towards meeting the need of intelligent vehicles. Intelligent vehicles, every different intelligent vehicle will be different. But if we find ways to model and interact with the intelligent vehicles, I hope one day we will be able to answer driving safety problem posed by intelligent vehicles. Next, I would like to talk about the thermal performance on pavement. Well, pavement engineers, many pavement engineers are not familiar on how to go about predicting the thermal state of a pavement. Yet, it is important for us in terms of pavement performance, the thermal environment inside a pavement structure. And of course, in this social context, we are interested in looking at the heat island effect, how pavement absorb heat and generate heat that lead to partially contribute to the heat island effect. Now, in the process, what do we need? What thermal properties do we need from the pavement? Many of us are not familiar with these thermal properties of pavement material. In fact, most standard highway engineering lab do not have equipment that allow us to measure the thermal properties of pavement materials. So I just like to say that we tried something and that will enable us to predict the temperature variation during the compaction. Of course, we are more interested in predicting the daily, monthly, or seasonal temperature variation within a pavement structure and how it affects the urban environment. Well, we need to do analysis to find out how pavement temperature regime would change at different time of the day, different day of the season. If you look at the literature in the last 3 or 4 years, pavement engineers started to look at this problem, and naturally, we researchers try to represent the pavement mixture using a microstructure. Microstructure representing every individual aggregate. Now, this is very tedious process. And in fact, even if you are able to do this, how are you going to apply this in the field? Because if you want to apply this in the field, every spot you have to know the aggregate distribution. You have to know the microstructure before you can do the analysis. So it's not realistic. Currently, I do not know. And in the future, I'm not sure whether it's realistic for a non-destructive test device to give measurement of what are the actual aggregate distribution every single point on the pavement. I think this is unrealistic. But we may have to do this to study the thermal environment of a pavement. So what can we do? Well, we analyze the problem, and we discovered that we don't have to do that. We don't have to do that. In fact, we found that what we need to do is, regardless of the microstructure of the pavement mixture, it doesn't matter. It really doesn't matter the distribution of the aggregate within the mixture. What it matters, according to the theory, according to the heat transfer theory, what it matters is the volume fraction of different materials. And this volume fraction has to be randomly distributed within the mixture. Well, that is a real situation. When you mix the mixture, the whole purpose is to randomly mixed thoroughly. So that assumption can be met. So what we discovered, instead of spending hours, many hours, trying to represent a mixture in its real microstructure form, we could just represent it using a standard row column structure, as long as we keep the volume fraction correct. We will be able to get the right answer. So with that, we find that instead of solving a problem in about 3 days, we can solve the problem within a few hours. And that makes it very convenient for us. And we found that as long as we know the thermal properties of aggregate, we know the thermal properties of asphalt, and of course we know the thermal properties of air. Once you know this thermal property of these 3 elements, we are done. Regardless of the aggregate gradation, regardless of the mixed proportion, regardless of air void content, we can apply the numerical model and predict the thermal properties of the mixture. So that means I just have to do one-time experiment measurement of the thermal properties of the aggregate asphalt. I'm done. I'm in business. As long as the material remains unchanged, regardless of mixed design, air void content, I'm able to predict the thermal properties. So that provides us a very convenient tool for solving the problem. And that, I hope, will provide us an effective tool to answer to the question of thermal environment when we do a certain design of our mixture. Well, I just mentioned about the advantage of simplifying the problem. We could actually apply this improved procedure in solving complex problems. Next, I'd like to talk about another problem that we face, and we have to resolve it before we face the intelligent vehicles. Porous pavement, which is widely used in many parts of the world. Now, the problem is, how do we know the infiltration rate in order to calculate the drainage efficiency of the pavement? Well, unfortunately, if you look at all the standards, method of measuring infiltration rate, you look at ASTM standard, you look at British standard, Euro standard, or any standard in any parts of the world, I would like to say a personal statement, which I have written in our papers, that none of this equipment give you the actual infiltration rate. None of them. Again, the problem is you use different equipment, it gives you different values. So you see, we have another problem of harmonization before we can face the intelligent vehicles. We have to do it. Well, again, we resort back to the basic theory, the mechanism of flow. So we did a lot of work in the lab, and we found that steady state, constant head test should not be used. Constant head should not be used because the rate of infiltration is not a linear function of the hydraulic gradient. So by using constant head test, you are only getting 1 point in the whole infiltration flow as the head changes. It doesn't work. So we have to use transient state test in order to find out the full relationship between the infiltration rate and the hydraulic gradient. Otherwise, we will not be able to evaluate correctly the infiltration capacity of a porous pavement. Again, we rely on this theoretical model solved numerically. This is able to give us near perfect. Hydraulics, somehow, when we measure the flow, we are able to reproduce the test result to a very high accuracy, thanks to the sensor accuracy that we have today. And we are able to simulate, of course, this is something that we need to improve on studying how the clogging takes place and how cleaning effectiveness of cleaning in removing the drainage capacity of a porous pavement. This is another important functions that we have to work on, and we can take a look at another one, which is the tire pavement noise. Well, my colleague, Professor Han in Chang'an University, is working on the tire pavement noise, trying again, helping us pavement engineers in understanding the functional performance of pavement in various aspects in order for us to answer questions that is going to pose to us by intelligent vehicles. We are still in the process of fine-tuning the prediction of pavement noise from lab tests. Now, in fact, I would like to conclude here by saying that in time to come, more and more intelligent vehicles are taken to the road, and we pavement engineers will have the responsibility of providing useful information, relevant information to intelligent vehicles for safe operation. And these are the initial efforts by our research group addressing the different aspects of functional performance of pavement. And I believe all of us in this hall will have the responsibility, being pavement engineering researcher, pushing forward for us to understand various aspects of functional performance of pavement in order for us to meet the demand of safe driving, comfort driving by intelligent vehicles. I thank you for your attention.
Professor Schwam, we thank you very much for your contribution with your brilliant keynote lecture in such a relevant topic for our symposium. Please join me again to thank Professor Schwam. Now it's time for our first break. Please try to return at 10:40. Thank you.
Welcome back. So we'll start the first session about road safety. And we have an invited guest to talk about modeling of pavement surface in road safety. It is Kumar Hanupan from TU Delft, Netherlands. And I have a short bio for presenting Kumar. So Dr. Kumar Anupan holds a bachelor degree from Indian Institute of Technology, Roorkee, India, and a PhD degree from National University of Singapore. He's an assistant professor in the section of pavement engineering, Department of Civil Engineering and Geosciences, Delft University of Technology in Netherlands. He's actively involved in teaching courses such as micromechanical modeling of asphalt concrete, continuum mechanics of pavement construction and maintenance. And his research activities are with performance-based big data analysis, tire pavement interactions, and micromechanical modeling of asphalt concrete. He has been involved in several international projects, which include European projects and projects in the Middle East. He is an active member of the ISAP, TRB, APACE, SMARTY, and serves on the editorial board member of IJPE. Thank you and welcome.
Thank you for warm welcome. Yeah. So good morning, distinguished guests, fellow colleagues, speakers, and also students. So welcome. So at first, I would like to thank Professor Pereira for giving me this opportunity to speak in front of you. And I would also like to congratulate the whole organizing team for arranging such a beautiful conference in such a beautiful city. So thank you for that. Without further ado, I'm going to introduce my topic, which is on modeling of pavement surface in road safety and rolling resistance. So the keynote speech from Professor Farr has, I think, paved a very nice way for this presentation because it's kind of a follow-up and you will see some similarities. Of course, I come from the same school of thought. He was my PhD supervisor. So you will see some similarities in the thought process, but hopefully take you further to my process. So introduction. So as Professor Farr mentioned, and I also think tire pavement interaction is a very important topic, even for modern days. And it has lots of challenges because not all the problems have been solved. So even if you look at the vehicles that we expect to come, the smart vehicles, et cetera, so the problems are still there and there are lots of things that are needed to be done. Particularly, I think that it touches two important aspects that concerns our community, which is safety and GHG emission. So safety related to skid resistance and GHG emission by rolling resistance. So I have divided my today's presentation in two parts. In the first part, I'm going to talk about skid resistance and a little bit about rolling resistance. We also discussed about harmonizations, but for those of you who are not familiar with the terms, I will also introduce a little bit about it. But for now, just keep in mind that even if you look at European landscape, you will see that there are different measurement techniques, different approaches, different policies for skid resistance and rolling resistance measurement. Yeah? So which causes a little bit of difficulties and challenges. We'll see that later on. So first of all, what makes the tire pavement interaction complex? So if I have to categorize, I categorize in three different factors that actually affect the whole skid resistance and rolling resistance. The first one is related to road itself, second one to the environment, and the third one to the tire characteristics. So let's look at it one by one. So for pavement, it is surface characteristics of the pavement. So we know that you can categorize it in terms of mega texture, macro texture, micro texture, positive texture, negative texture. There are various definitions for different types of textures that you can consider already. Then stiffness and deflection of the pavement also affect the rolling resistance and the skid resistance behavior. Type of the pavement that we choose at a very initial stage will also affect. Is it loose somewhere? Oh, yeah. I think it went loose. Okay. Thank you. Yeah. Maybe I'll use this better. So different types of texture, I was just saying, stiffness and deflection, type of pavement that you consider. All these factors affect the way you measure skid resistance and rolling resistance. In terms of environmental factors, temperature, moisture, and even the dust on the pavement that you experience. For example, in Saudi Arabia, the skid resistance will be dominated by such factors a lot than the Netherlands because it gets washed away. So all these factors actually affect your skid resistance and rolling resistance. And last but not the least, tire-related factors, which itself is very complicated, also affects the measurement, such as the rubber compound you choose, the viscoelastic behavior, then the operating mode, such as loading, inflation pressure, the temperature on the tire, speed of the vehicle, all these factors affect the skid resistance and rolling resistance measurement. So let me go to the safety part as part one, skid resistance. So many research studies clearly show that skid resistance and accidents are related. So as you can see, the trend. So therefore, it becomes very important for us to study skid resistance very carefully. Now, for those of you who are not familiar with skid resistance, it's simply the horizontal force divided by normal reaction, and you can get your skid resistance, depending upon how you define your normal reaction and forces. So how do we measure skid resistance and measurement? So there are different ways to measure skid resistance and rolling resistance. Professor Faw showed some of the devices, but I have categorized them in terms of different way you can put them, like longitudinal direction, you can have sliders, like British pendulum, you can have sideway friction coefficient. So there are different ways you can measure. And now we get back to the initial problem that I mentioned across the landscape of Europe. So think about it. Let's say we are doing a measurement at a particular country with one set of the device, and we get a number, SN1. Let's call it 0.6. And again, we did the test somewhere else with the same device, and we get another number, 0.55. Okay? So for people who are not familiar, so can we say that 0.6 is better than 0.55? So you may think, yes, why not? 0.6 is obviously better, right? But that may not be the case here. If you talk to the experts, these correlations do not exist. And that's why harmonization becomes a very important topic. Yeah? So how do you do this harmonization? A very simple way is to carry on statistics. So we do field tests here, you do field tests there, establish a correlation, you get a line, and you say, okay, now I can predict from one to the other. But there are problems there. First of all, you ignore fundamental mechanics. And therefore, it is only valid for the section where you calibrate them for. So once you validate in one country, it may not be true for another country. And that is why I said 0.6 and 0.55 may just become meaningless. Okay? And on top of that, yeah, you need several field tests. So what are the alternatives when we started thinking about it? And there were computational advancement. So why not use those computational techniques and build a model that can help us in solving such problems? Yeah. So this is the main message here, that we wanted to develop and analyze complex tire interaction models. Because of the recent developments in computational field, we can actually model such complex things. And also, such models on validation can help pavement engineers evaluate several scenarios, like what if? What if I change the load? What if in my initial design I did not choose process fault, I chose SMA? What will be the consequence in terms of skid resistance? What if I increase the design speed? Will there be a safety concern? So all these analysis could be done with these computational tools. That's why I think it's a very powerful tool if we use it correctly. So one practical example. So a few years back, actually it's 10 years, but a few years back, one friction measuring company, they came to us and said, Suddenly they see that at certain road sections, they find the skid resistance values are below threshold, which previous year was quite okay, no problem. And that should not be the case. Then why is it happening? And they could not find it. So they came to us with the problem, say, can you try to investigate it? When we tried to investigate, we found there was no change. Everything was the same, except one tiny detail that they made the water tank much larger than what was supposed to be on that device. Okay, because you can do longer measurements, so you don't need many breaks, so it's efficient, right? But the problem was, in such cases, we thought that you are not giving enough rest time now for the tires to relax so that you can start your measurement. And that could have caused these differences. But then this was just hypothesis. How do you validate this? Okay? So we thought, why don't we build a computational tool, a thermomechanical powered computational tool that can actually help us in testing such hypotheses. And that was the initiation for such models. Okay, so in my earlier work, what I observed that in certain in models, often we require initial point as an input parameter. But in such cases, when there are differences in morphology, we did not want to measure it continuously or get it from the literature, which has certain advantage because it's easier. You can obtain it from literature and directly plug it in. But in this case, we didn't want it to be there. So how to solve this problem? And then our approach was, why don't we bring the morphology inside the model? Yes. So how do we bring the morphology? I'll show you a brief description. So we have the CT scan tomographer, which is now available almost everywhere. So we utilize this device to actually create 3D profile and then convert it into finite element models. Just to show you in videos. So let's say if you have a sample, you can see I think it's 2 layers. And this is how we created the slides, stitched them together, and then that's how you create the whole surface morphology here. And you can actually see now clearly the differences here and here. Yeah. So once we had that information, we converted back into finite element model, something like this. Okay. Now is this unique? Will we be able to capture different surface types with this? So we did the same thing on different mixture, and now you can see that different mixture actually produce different types of surface morphology. So that was the mixture. What about the tires? So for tires, actually tire structure itself is very complicated, and we could not model all the components that are required. So we just simplified the whole process and thought, let's model only the important aspects, such as sidewall tread, lower belt, and upper belt. And in order to get the geometry, what we did, we utilized water jet, cut the tire with the water jet, got it like this, and then got the 2D geometry of this. Okay. Now, what about the material properties? Of course, this is well known, but this is well known for tire industries, not to us. So we approached tire industries. Can you provide us such information, particularly for the tread properties? And they were not open about it. They did not share. So we had to develop our own test protocol. So we thought, what is the device that is available in our lab that can give us viscoelastic characteristics of the tire? And that was DSR. So we developed a test protocol, actually you can find in one of our papers there, which can convert the sample test data to something like a generalized Maxwell model or Perroni series model. And then you can get this information from the test itself. So the protocol is defined here. Because you have to be careful. If you can create different types of sample size, then the test might not be repeatable. So that's why you need a test protocol for that. Okay, so that was the property. Then how did we validate? So the step 1 validation was simply in our laboratory. You can see this was made by us, wooden, and then we applied the load. And then we tested, got something like this on the Fujifilm. So there is a Fujifilm here. And with this Fujifilm, you can get the footprint. And then you can compare it with the literature and with your models. Next step was to really test it for the real tires. So now you see the full tire, and then we got this kind of footprint and tried to validate and calibrate our model utilizing this data. You can see here. So recently, one of my PhD students have collaborated with the tire industries, where we tried to put sensors now inside the tires, and then try to compare different output of these load deflection curve. And you can see that the results of experimental and numerical match quite well. So that was quite satisfying. And you can see that this was 2021, and the previous models were from 2016 and 2017. So it's quite good continuation of what we did. Okay, so how did we model the tire? So once we had the 2D profile, we converted it to 3D model by rotating it, and then we applied desired load, desired inflation pressure, and force. And then if you compare, you will see something like this, it's a footprint, right? And if you turn it over, you will see like this. So again, I'll ask you a question for those who are not familiar. What do you think about this profile if I let this tire move or rotate or brake? Will this profile or footprint patch that we call will be same, or will it change, even if it is on the flat pavement? So if you think about it, it's not going to be the same. But does our model catch this? So if you see it, indeed it's different for different operating condition. Yeah. So we have a tire now. We have a pavement. We need to interact it. Okay? So this is a schematic representation of what we did. So we have a tire body, which is moving like caterpillar in this case, on a rough surface. So what happens here? When this rubber slides over this rough surface, it continuously phases loading and unloading, right? There is a cycle. And because it's a viscoelastic material, you dissipate energy. So depending upon what rubber type you use or rubber characteristics you provide, you can get different shapes here. And that will also dictate your rolling resistance and skid resistance. Okay, so similar to that, once we had this flat pavement, if you see here, the road is flat. What we did is to transfer the results from this state to a state where we converted it into 3D morphology surface, as I showed before. So we just patched them and build a whole road out of it. Okay, so just to demonstrate how it looks, this is one of our simulations. I think this gives us much more information than just skid resistance or rolling resistance, probably. Here, if you see and look at it carefully, there are not all the parts of the tire that are in contact with the pavement. This green area always remain green, and there are many more green areas. But when we design conventionally the pavements, or we consider many other analysis situations, we just ignore this fact. But this could be crucial because your pressure distribution is not even, which means at some places it could be much higher at the other places, right? So, of course, there are lots of capabilities of these models. We can progress further on it. So the last step was to add the thermomechanical elements to the model, just to demonstrate the fact. So this is like what we are simulating here is the interaction. So you rub your palm like this continuously. What you will feel, your heat is increasing, right? There's friction. So this is what it is simulating here. So we are just rotating the tire, and you can see how the temperature inside the cross-section changing. Okay, so far what I have showed you a model that is capable of running thermomechanically, but what about the validation? So now we were stuck, I think, after 4 years. Now how to validate? Again, the tire industries probably had it, but they didn't want to share this information with us. So we had to develop our own system. And it was quite simple, so as shown here. So we developed this kind of system, which is a data logger. So you can place your sensors at different locations, wherever you want to put them, and you can run the tires continuously and basically the data logger collects the data and transfers it in runtime to your laptop. And we validated this, 2 cases, one in the field, but previous to the field operation, we also validated in our colleague's car. So we replaced his tire with the instrumented tire, and I will show you the result for that. So this is inside the Delft. So we do 2 test cases, of course, first of all inside the cities because you drive at lower speed, and then we move to the highways. But can you clearly see from here which side was highway and which side was local road? Yeah, I think it's very obvious. So the lower temperature rise was in the local area. However, if you see highways, the temperature rise was much significant and smoother at 100 km per hour. Yeah? And if you see there are lots of this kind of undulations. Why is that? And the reason here is because on local roads you have to stop, right? Because there are lots of cars, you have signals. So therefore you see big drop here. So we were very happy with what we were getting. We were able to capture all this information from our system. And another point that we should be careful about is if you look at this sensor, which was, I think, closer to the outer side, remained more or less at the same temperature, did not change a lot, even if the inside temperature went quite high. So which means if you are just measuring your tire temperature from outside the tread, that may not be a true representative thing for your model because your inside temperature can be significantly different. In this case, it's almost 20 degrees centigrade difference. So it's a huge difference. Yeah? And if you just measure it from thermometer outside, it may not be accurate. Okay, such things can also be very useful for, again, rolling resistance and other models. So simply put, when you combine all this, you can obtain such results. You can plot your friction coefficients with different variables. In this case, I showed in terms of pavement temperature, ambient temperature, but of course you can add more axes and you can do more, you can prepare more complex plots. But this information can be very useful. Why? Because now you're not talking about 1 point measurement of skid resistance. It's not about 0.35 as the lowest point in this whole network. You get the whole curve, whole profile of it. And that is very useful information for your pavement management system. So I think this should be the way to go in future where you have lots of intelligent vehicles, smart vehicles, or even autonomous vehicles. What about the pavement characteristics? Yes. You can see that we were also able to capture the behavior of different types of surfaces. Okay, so with that, I will move quickly to the rolling resistance. I see that there is a wonderful session in the afternoon or in the evening today, so I will not go into much detail of this rolling resistance because I think most of it will be covered, but I'll just touch quickly on what we are doing. So as we know, GHG emission, we are one of the largest contributors, you see. About 76.7% comes from us, pavement and transportation. Yeah. And this is a huge damage that we are doing to the pavement, to the environment. And of course, we need to do something about it. Yeah. So rolling resistance is directly related to this kind of emission, as shown in different literature also. So first, let's see the key resistive forces that the engine needs to overcome so that it produces more of carbon. Yeah. So there are 5 main resistive forces that can be highlighted: gravity, inertia, mechanical friction, aerodynamics. So I think none of them we can control. They are there from the vehicle side. But what about this? This is where we come from this side, pavement. Okay. So the rolling resistance contribution from the total resistive force is only 5%. And then again, you might think, okay, this is very insignificant. Only 5% of total 76% that we are damaging. Probably that's not a lot. But if you multiply with the total number of vehicles that we have, that's a significant loss. And it's not only true for the vehicle that runs on fossil fuels. Yes, of course, you are doing carbon emission. But of course, for other types of vehicles, they consume more of energy. So at the end of the day, you're charging a battery from the energy source that we have. Yeah. So moving on, simply, what is rolling resistance? So as depicted in this figure, what we show that you see that the forces are not balanced here, and that's why your vehicle needs to overcome these forces. As compared to a surface that has low rolling resistance, their forces are balanced, and then less energy is required. So with this, I think we can try to come up with something that is beneficial for the environment itself. So similar to skid resistance, now hopefully you'll see the connection. Similar to skid resistance, rolling resistance is also measured with different types of devices. Yeah. You can have, again, similar answer, similar harmonization problem that we discussed. Okay. So in collaboration with IFSTAR, I think Veronique, I saw her somewhere. So we did some tests at IFSTAR. Now the name had changed, I don't remember. But we did some tests on the rolling resistance measurement. And then for different surfaces, we have this kind of instrumented car. And then we try to compare the results that we obtained from there to the final element models that I showed you before. And you can see that they were quite in good agreements, yeah, even for rolling resistance. So what next? Still, we need to improve the prediction of rolling resistance. So what we are doing as of now, like we discussed, now we have intelligent vehicle. Okay, so they gather runtime information. On one side, it's a difficulty for us, but also it gives us more information than what we could have gathered. Right? So this information, plus we do yearly maintenance monitoring. So we also have this kind of information, plus we have geographical information. So if we combine all the information inside it, it's probably per second, this one is per year, this could be something like that. So at different frequencies. So what we are dealing with is the information that is coming to us at different frequency. Once we combine this into a big data, we can utilize AI to predict it. Now AI has proven its worth to ourselves. We all know about ChatGPT and Google Alpha and so many other types of AIs that have working perfectly. But does it work for us also? That was the question. Will it work in our case? So our current steps, this is what we are still doing. So I don't have much information over here, but I'll show what we have done so far. So we collected some information in our road network at some place. And then what we tried to do is to predict rolling resistance from standard statistical model. And now you see we get R-square value of 0.36, the prediction accuracy. Okay, with other models, it improved to 0.665. What could be the problem here? So if you think about it, maybe here you're just considering that RMS is the only factor that affects rolling resistance. Here MPD and RMS, and then you have different combination. Then you can add power to this. So what is the truth? We don't know, we just try, right? So that's why we said, okay, let's try to compare, put it into machine learning with the knowledge that we already have, and then try to have the predictions from the same data set. And now you can see the prediction accuracy went to 0.94. So that gives us quite a good confidence that we should proceed further. Yes. Now, how to proceed further? So if you don't want to use data like just a blind thing, you don't want to use like a black box, then probably this is an approach that we can take it, and this is what we are doing, a hybrid approach combining both the data modeling and the numerical modeling that I showed you before. So this is a toolkit we have developed, and this will be available to the user. It's a very simple toolkit run on the machine learning where users can provide its own data set, train the models, and then the prediction can go much better. Of course, the users, by users, I don't mean every road user, the users like ministry and the organization that can collect such information. So once we have this kind of information, you just put it in like this, quite simple. Tire pressure, all the factors, then you just click and then it will predict the rolling resistance for that particular section under that condition. Yeah? Okay. So what according to me is an ongoing challenge? So I talked a lot about rolling resistance. So if we build a flat pavement, a very smooth pavement, probably we'll have less rolling resistance. But is that the way to proceed? That cannot be, right? Because we need safety. So I think the challenge for us in this domain is to balance the skid resistance and rolling resistance. Come up with a strategy that we can develop which maximizes or optimizes the performance of skid resistance and rolling resistance for mixed design. And you can do it at early stage, even very early stage of mixed designing itself. So this is, I think, not easy, but should be the way to go. So with that, I have reached to the conclusions of my presentation. So some key highlights, as I discussed, that field measurements require often calibrations. You have to be careful. Texture parameters like MPD and IRI, if you just use it blindly and predict your rolling resistance, be careful that your prediction accuracies are very low. We can use AI to actually enhance the performance of the prediction. This I already said. In terms of finite element models, it is effective for both skid resistance and rolling resistance measurements. Temperature measurement system, the box that I showed, works well, and we validated it. I think mechanistic-based statistical relationship between friction and various parameters could also be developed, as also shown by our keynote speech in the morning. So the key highlights for me is like numerical models can be combined with AI models in order to predict rolling resistance and skid resistance. I think this is the future where we can actually interact with smart vehicle. We can also make our pavement management system smarter. And yeah, could be made for road authority for safety and environmental perspectives. So here, as the very last slide, you can see this vehicle probably is smart enough to apply brakes in time so that it doesn't meet with the accident. But kudos to ourselves and the community that also built this pavement, which provides sufficient skid resistance that it can stop. Otherwise, we could not have. So with that, I would like to thank you. Thank you for your time. So wonderful.
Thank you very
Thank
much
you.
for your clear and very nice presentation. And we will move forward with the next presentation, which is about multi-scale analysis and contact model for road pavement skid resistance. And Veronique will present it. We just have to change our computers, so just a brief moment.
Where is it? You put all the presentation on it. Thank you, Elizabeth. Good morning, everybody. Nice to be here with you. Thank you for giving me the opportunity to present to you this work. I will present this paper on behalf of my PhD student, Dr. Ejeu, who is now performing a postdoctoral position in Sweden. So he cannot attend, and I have the hard work to summarize in 15 minutes 3 years of work. So apologize if sometimes I just give you a brief overview. There are several papers and I can answer all your questions after. The idea here is just to show what we try to do during 3 years and the interest of using multi-scale analysis for road pavement skid resistance modeling. Well, regarding friction, when we are talking about tire road contact area, we have two main phenomena. hysteresis and adhesion, and these two mechanical phenomena lead to the generation of friction forces that oppose to the movement and that allow us braking or turning. We have, for road engineers, in fact, we are considering mainly two scales, microtexture and macrotexture. They are defined in ISO standard. And basically, most of the people, when they are thinking about road pavement design, they say, okay, I'm focusing on macrotexture for water surface drainage, and microtexture to have a contact point between the tire and the road pavements. And I need to have a raw surface to allow me to have a high level of friction and skid resistance. But what we are seeing by making a lot of measurement is that sometimes there are differences between two materials that seem to have very close microtexture and macrotexture. And they are not always evolving in the same way. So we were wondering why. And we wanted with this, this work to try to understand the influence of each scale on the friction force generation and how these scales are evolving with the wear. So this PhD was funded in the framework of a French national project called iStreet and led by the Eiffage private company. So it was a 5-year project with a lot of different topics, but basically the idea is to try to develop the pavement of the future, so a multifunctional pavement. We had a collaboration between École Centrale de Lyon and Université Gustave Eiffel. I am sure that most of you don't know what is Université Gustave Eiffel. Just don't worry, it's just the new name of IFSTAR. So we created this university 2 years ago by merging IFSTAR, which is a research institute, and Université Paris-Est Marne-la-Vallée, a French university close to Paris, and 4 school engineers. So the same people working on the same topics, don't worry. So Weao Ejiu was a PhD in this project, and during 3 years he worked on the multi-scale analysis. And the idea is to identify through a multi-scale contact model the relevant scales that affect road pavement. For the methodology, in fact, we based our approach on laboratory study, experimental study, with 3D surface characterization. Then we work on the multi-scale decomposition method, and then we propose a 3D contact model that was validated with several different pavement mixes. So for the experimental study, we use samples. So, and we use a machine called Venner-Schultz machine, which allow simulating polishing of these samples. So we simulate the mechanical wear of pavement surfaces. And we have, basically when we are making the measurement, we are applying some forces to polish the surface, then we stop and we measure friction. And with different steps, we are able to simulate the whole life of the pavement. We also use a method to obtain 3D cartographies of the pavement surface. So you can see here some example of cartographies. And the idea behind is to analyze these 3D cartographies with different indicator of the texture of the surface. For the experimental study, we first work on samples made with aggregates. So we selected 5 different aggregates for this analysis. 2 aggregates were what we called polymineral aggregates, and 3 were monomineral aggregates. The idea behind was to try to better understand what we called the differential polishing between the mineral, because there are previous studies that that demonstrate that when you have different mineralogical elements in the pavement, they are not weared in the same manner. The 5 aggregates we selected, 3 are good aggregates with a polish stone value superior to 50, so they can be used on real road, and 2 were selected with a very low value of polish stone value, and they were supposed not to be used in road and to have very bad performances for friction. So you can see on the test here that the 2 aggregates with polymineral formulas, we obtain the best friction value with that, which is normal, because each time we wear the pavement surface, we remove the smooth minerals and we recreate texture. So this is a rather classical and well-known result. So what we try to do then is to go further and to say, okay, basically it works like that, but we would like to understand better which scale is really concerned by this wearing process. So there are several methods to decompose the pavement texture signals, and we compare different existing methods to analyze this signal. And finally, what we decided to use is continuous wavelet method. The interest of using this method by comparison with fast Fourier transform, for example, is the fact that you can detect singularities, but you know where they are located. And it's very important when considering a surface like pavement surface, which is very heterogeneous, to know where are the key points, in fact. So we compare different existing wavelengths in literature, and finally, to apply the continuous wavelet method, we decided to use as a mother wavelet the wavelet Morley, so the Mexican hat, which appears as very efficient to decompose the texture signal and to recompose it. So with this mother wavelet, we obtain a very accurate decomposition, multiscale decomposition. You can see here an example of decomposition. So I hope it will work. Yes. So this is the pavement surface obtained with a 3D cartography. And here you have the 16 scale. And for each scale, you can see the texture, so the different height of the surface. And when we use all these 16 scale and we obtain, we recombine them, we obtain the same surface at 99%. So of similarities. So we consider that this decomposition was relevant to understand what happened, in fact, in the pavement surface. To model, we decided to use half-space theory with field element method, and we make some assumptions like the fact that we have small asperities, as we were focusing on microtexture effect. It was true. We consider that we have small slopes on each element, small deformation, and we make calculus of the contact parameter. So, in fact, we estimate the friction at each scale, and then with the friction calculated at each scale of the decomposition, we calculate the global friction as a combination of all these scales. And the interest is to be able to know what was the contribution of each scale to the global friction between the pavement and the tire. So to validate the model, we use different steps. First, we check what happened when considering the contact between a rigid half sphere and elastic and viscoelastic plane. So we use some data from literature, and we obtain very good results, as you can see here. The blue curve is the analytical solution, so the literature taken as a reference, and the red is the results from the contact model. Then we use reference surfaces. The idea behind the reference surfaces is to have some specific surfaces we control very well. So we have a controlled microtexture and macrotexture. So we use, in fact, a plane with different big half rigid spheres to simulate the macrotexture. And then on each rigid spheres, we put small half-rigid sphere to simulate microtexture, and also we use fractal function to simulate microtexture. So with this, in this part, we make a lot of simulation, and we obtain very good results with the good trends, an increase of contact pressure and a decrease of contact area when we had some small scales. So this is logical. We also have good results by considering the aggregate penetration in rubber and the correlation with the height distribution of the texture. In fact, that was rather good. So by considering the model is valid, what we did, we used this model on real aggregate surface. I present you at the very beginning. And what you can see here is a very good level of correlation of the model who is able to help us to find the global skid resistance of the pavement surface. To obtain that, we have to use a weighted method. We have good and bad news. So you can see here the comparison between two mixes, F3 and F4. Basically, the differences between these two mixes is the fact that here you have only small aggregate size. All the maximum size of the aggregates is 6 millimeter. And here on F4, you have 30% of the aggregate that are in the range 6 to 10 millimeter. And in fact, what appears is the fact that when you are considering pavement mix, we are overestimating skid resistance. And this is basically due to two phenomena. First of all, there is the bitumen removal phase, which is heterogeneous, especially when you have very different size of aggregates on the pavement surface. And this heterogeneous bitumen removal is not well modeled until now. And so we need to add now a new function to consider, in fact, this bitumen removal phase. And this is the next step we are working on at Université Gustave Eiffel. So to conclude, just I would like to say that we managed to develop a method to make a multi-scale analysis of different pavement surfaces. This is based on the wavelet decomposition method, and the friction model is rather simple but rather robust, and it's able to take into account global and differential wear because it works with monomineral and polymineral aggregates. So now we need to go further for an extension to asphalt pavement mix because we know that there are the bitumen removal phase we have to improve. So thank you for your attention, and thank you for the French Ministry for funding this project, and to FH for leading this project. Thank you very much.
Thank you, Veronique, again. And we'll now move to the next presentation, which is about sustainability and higher skid resistance. that will be held by the David Woodward.
Somebody set this up, please.
Just go here.
Thank you.
Okay.
Thank you very much. It's very nice to be back at the second conference. I was in China at the first one. Fantastic conference, and it's fantastic to bring it back to Europe here. Thank you, Paul. So it's also nice to come to a road surface conference and hear somebody talking about aggregates, because that's what we're driving on, okay? It's great to hear models and stuff, but behind it all is the geology of the aggregate. And both of us, Paul and myself, we're both geologists. Okay, I've had over 40 years working with aggregates and road surfaces and stuff. And Paul's a relatively newbie, but he's a proper geologist. So I'm going to talk about sustainability and what I've called higher skid-resistant aggregates, or skid resistance. But the key word is higher. So where are we going here? And it's going to be based on a couple of case studies, which I won't tell you where they're from, because some of the case studies, you're maybe talking projects that are valued $200 million, where you've had failure within a few weeks of the surface, and other failures that the world was watching on television. Okay, so I'm going to tell you where these failures come from. Well, we're talking about aggregate, and some idea, just those who don't appreciate, the mixes are essentially aggregates, and different types of aggregates. If you want to know something about aggregates for asphalt mixes and know absolutely nothing, go and find that document. It was done over 20 years ago in the UK, and it's sustainable use of high friction aggregate. In the UK, those who don't know, we've had a tremendously long history in skid resistance, and we specify values of skid resistance in the methods of measurement long before many other countries adopted them. And there's a huge background research in the UK based on skid resistance. What gives skid resistance, the asphalt mixes, how you use them, how they evolve with time. All of that stuff has been well researched past 20, 30 years. And the development of the mixes and the test methods long before that. So if you want to know something, read something, it's 20 years old, but it's still very relevant. And as regards sustainability, the little map there of the UK shows where that aggregate is available. And if that was a comparable country around the world, you may not have the aggregate in the ground to give you high skid resistance that we have in the UK. So you're starting off in a very different ballpark to what we have the luxury of in the UK. And any country trying to adopt the history work that we have in the UK will have problems. So this presentation, this is taken from the abstract. What have we got? Sustainability and higher skid resistance. Everyone talks about sustainability these days. Net zero, all of this stuff that everyone's talking about, climate change, rolling resistance, all the rest of it, safety. It's all big holistic story that we're going to listen about for the next couple of days. Depending on different scales of texture, during manufacture, compaction, and then offered to the tire during the evolution of in-service life. So trying to model this stuff is really, really complicated, and it's really, really difficult. And I've been trying to do this for a long time, and I'm getting tiny little steps of inside knowledge of what might be happening. And then the eventual expectation that this asphalt material is recycled. Okay, this is an idealization that may not always happen. And with a background in aggregates, I tend to get invited in where big projects go wrong. And they say, to me, it's always inevitably something going wrong with the aggregate. First telephone message, send me a photograph. I get a photograph and I say, oh, bad word, there's a problem here, and it's the aggregate. Within Europe, and all we're within Europe here, aggregate is a construction product. And again, You may not appreciate this, you may not realize this, but we're talking about construction products here. And within Europe, we're covered by a thing called construction product regulation. Okay? Go onto the Europa website, it's all detailed. There's 35 different construction products. We've got all the standards and specifications, all the test methods have all been rejigged over the past few years to make them what's called CPR compliant. Okay, and it involves CE marking. You have to declare the performance. So this talk is all about skid resistance, safety, and a poor contractor or a designer or a road authority trying to think about performance based on a lab test and how that's going to work out through the complete life of that product, asphalt, in the road, with all the other factors of climate change and everything else in terms of electric vehicles, smart vehicles, all these things that are happening in the world these days. So, from my perspective, if you go right back to what is essentially 90-odd% of a road surface, that's aggregate. So what is the Construction Products Regulation? This is European law. Okay, it applies to 35 products right across construction. Aggregate and asphalt materials. If you're into concrete, it applies to concrete as well. When you go to the toilet in this building, it applies to the sanitary appliances which you use in the toilet. Okay, these are products right across construction. And it's all there down there. Go and have a look at it. I come from Northern Ireland, part of the UK, and with Brexit, Northern Ireland is still part of Europe when it comes to construction materials and construction products because of our local political situation. So, everything from toilets to road surfaces. 7 generic requirements: mechanical resistance, safety and fire, hygiene, health, environment, safety and accessibility, noise, energy economy, heat retention, sustainable use. These are going to be the big issues that this conference is addressing. For those who don't appreciate, this is the European regulation behind all of this. So, talking about time, speaking as a geologist, a rock is 200 or 300 million years old. Engineering time. You open up a quarry, you crush it, you mix it with bitumen, you make asphalt. You design it and you hope you're going to get 10, 15 years out of a surface. That's wishful thinking. And then you have performance time. This is what you're back to trying to declare the performance if you're aggregate or you're asphalt. And that can be as little as days to hopefully many years. So, can you guess which aggregate test refers to which development in vehicle? Nothing has happened in the world of testing aggregates for a long time, despite everything else going on in this world at the minute. 1960, Morris Minor. Right back to 1830. Can you name the test methods which you used to predict the performance of aggregate? That's when they date from. There is no Tesla there or equivalent. We have no modern ways in the European standards for predicting the performance of aggregate. We're now into the problems. Giving you examples. This is a core we took out of a road somewhere. The road was cracking within a week or two. Pulled the core out, set it on the lab, and it fell apart. How do you model that? This is Sonnenbrand. German problem typically, get it in Poland as well. It's a particular type of basalt. You quarry what looks like good stone, and the stone falls apart. British standard said it doesn't exist. Or basalts in Ireland, that happens. You take a lump of stone and it falls apart. You see a problem. When I go on site with experts, I'm looking at something. An expert comes on site. I've just finished a problem where I had to deal with 4 different experts. I had to educate all 4 experts as to what they were looking at. So do you see the problem? This is 1-month-old asphalt. Here's the problem. The bitumen has come off the stone on its own. It has peeled back. And in that little slide, there's maybe half a dozen bits of stone in various stages of failure. I like this one. You're probably thinking, that's a nice rough surface, good macro texture in that. But if you look a bit closer, the white line, I'll go back to rail units, that's about 1 inch above the road surface. The whole road surface has wore away within 6 months. This was a $150 million project, okay? This happened within a week. Classic failure of aggregate particles. They're only talking a few % of aggregate particles, but this is in a high stone mix. And a high stone mix relies on the skeleton. That's the 3D skeleton that you drive on the surface, and then within the asphalt layer. If those particles start to go, your whole skeleton starts to fall apart. Knew what to look at immediately, and if you follow through the life of these particles, this happened after the first shower of rain. So failure can start after 1 shower of rain. Never mind all the scare stories about how our climate is going to change as a result of climate change. This is reality at the minute. And it just develops. In the end, you end up with these little empty wine glasses where you've still got the bitumen perfectly preserved the shape of where the aggregate particle used to be. And say that's within a few weeks. You can take cores out, high pressure water. Why high pressure water? Okay, in reality, in the road, when it rains, you drive over it in the wheel tracks, water gets compressed onto the tire, and it basically blows the stone out. We're just looking at the big sizes of stone here. Okay, that's easy to spot. But the same thing applies to the small sizes, right down. It's this continuous problem. So if you're putting blends of different sizes of aggregates together, and you're only interested in the big stone, which has got the skid resistance, your failure can be due to the small sizes that you ignore in your design and your testing. If you look at this, thin surface layer, a couple of particles, and you're right down to the bond with the underlying layer down to your bond coat. And that surface there is totally shot when it was constructed. What do we got? I will wear my glasses eventually. You can see what I'm looking at here. So, 1 day old basalt. 1 day. Bitumen's come off it. The stone has failed. Other things going on. We're taking these aggregates, a few % in a stockpile, putting it through an asphalt plant. If you get stone, the stamp, water inside, goes through a mixing plant, the temperature's there, you can break the stone up. And the stone that's going into the back of the lorry has failed due to mixing. Power hosing to see the extent of the problem. Remember, this is just the surface. What you see is a 3-dimensional problem. So if you see something in the surface, it's in your layer, and your layer is shot. Stockpile, first shower of rain. Really good aggregate there, mixed with bad aggregate. Sorry, I'm not calling it bad aggregate. That material actually is from a quarrying perspective, extremely useful for other applications outside of a construction product. Again, take that material, put it into a mix, power hose it. That's what your road surface is going to look like. So you can predict these things. This is something else. This is a corner somewhere. And we're starting to use sort of more fancy methods, things which I'll elaborate on in some of my other talks. But basically, if you can imagine, got a corner somewhere, this is in the wheel path, there's been a total disaster, mix-up, asphalt has gone down, it's starting to be open to traffic, and this is, if you've got a three-dimensional surface, you can start to see, okay, if in our asphalt material, if we think a tire is going to interact with the top 2 millimetre, how much contact is there? Okay, in practice, it's usually a lot less than 2 mil. You're driving on probably about 1 millimetre of the top texture on a road. So you are, and that's changing over the life of the road. But I'm being generous here, I'm going down 2 millimetres into the surface texture. And this is how much of the surface is actually available to the tire. And on the apex of the corner, we're down to 7% of the original asphalt left to make contact with the tire due to this rapid breakup, degradation of the asphalt mix. This is about a week of being trafficked for this corner. Just to show you a way, this basically is based on photographs, scale, that's the surface, make a 3D model, go down into your 3D model, and basically it's the visual showing the contact area. Never mind a lot of other parameters that you can measure. So that's it, about 60-odd% available to the tire, down to 7%. So this is all happening within very short periods of time. When things go wrong, and these little case studies which I've zipped through here are just to maybe get you to think the 90-odd% of your asphalt, is aggregate. When you do laboratory experiments, when you do these case studies, these PhDs, certainly I've fallen into this. When you're trying to think of an aggregate source, you think of the best aggregate sources out there. And certainly within the UK, we have a tremendous variability in rock type and skid resistance properties. And a lot of our studies in the past have basically involved the best aggregates, the ones with the best in-service performance. In reality, those are the boring aggregates. Those are the predictable ones. And whereas if you're really interested in performance, you need to be thinking about what's gone wrong. Where's something going to fail? If we're looking at tire surface interaction, how is it going to fail? What's going to affect these nice models that we can predict? So, very last slide. So, all the aggregates in these mixes had test certificates, had pieces of paper that said they were all right, they were okay. And everyone worked in good faith. But yet, we had catastrophic failure in some of the examples. So I'm questioning those old cars, those old horses and carts. Do we need to rethink about how we test aggregate? Because it leads into Professor Foy's presentation this morning in the last keynote. We have to start thinking in different ways, think outside the box. Because there's no point building a road if it's going to fail within a week. Absolutely no point. So, I'll finish with that.
Thank you, David, for sharing with us all these bad examples, which are very useful too. Thank you, and we'll now move again to the next presentation about development of high-fidelity staggered tire pavement interaction model for skid resistance analysis. I don't dare pronounce the name, so I'll leave the presenter. Okay. I'm waiting for the presenter. Okay, thank you very much. We are now watching, so please share your screen.
Could you see the screen now?
Yes, we can see the screen and we are hearing you very well. Thank you. So please.
Yeah. Hello everyone. I'm Ajay Shankar Jagadish, lecturer in the Delft University of Technology in the Netherlands. I'm very happy to be presenting my work here in this prestigious conference. Last time I was able to attend it in person in Xi'an. This time I couldn't be able to attend due to some of the teaching work. The title of our presentation today is Development of High Fidelity Staggered Tire Pavement Interaction Model for Skid Resistance Analysis. Let's start with the bigger picture. Like World Health Organization reported that nearly 1.35 million road deaths has reported every single year. This counts back to like one single death for every 24 seconds. If we try to ignore the accidents due to the poor vehicle conditions or the poor driving skills, if we try to sort out with respect to the pavement engineers, it still counts high. And this is very high when we consider the wet pavement conditions or the rainy conditions. So we as pavement engineers are in a crucial need to find the cure for this road accident epidemic. So the research problem which we have now is to model the complex tire pavement interaction characteristics during the wet pavement surfaces or the rainy surfaces. Some of the existing challenges are like people have been investigating the skid resistance for almost 70 to 80 years using some small scale experiments like British pendulum testers, dynamic friction tester, or like trailer based friction tester. However, many of these experiments are not exactly replicating the field conditions with respect to the larger scale tires or different water film thicknesses or different speeds. This is why people started creating the tire pavement interaction models, numerical models using finite element or finite volume models. As Professor Fa and Professor Anupam explained the need for the simulation models and the existing challenges people are facing, if we look at the past 10 years, by Professor Anupam's team, they created the XRCT-based simulation models for investigating the skid resistance characteristics. Inspired by this pioneering work, I created a similar model in my PhD study like 3 years back, and we were trying to understand the uplift and drag forces in the models. But the biggest problem with the models is it requires heavy computational power. If I talk about my model, it had almost like 20 million elements. It needed a supercomputer with almost like 128 cores. It needed to run for almost like 2 to 3 days in a supercomputer in Singapore. This is just for one single case study, like for example, like one water film thickness or one particular vehicle speed. If we change the parameters, it needs more and more time to investigate this phenomenon. The second problem which we were facing is the super expensive softwares. All these models needed a very expensive software like ANSYS or Abacus or Adena or any other console or different softwares. And these are very expensive as well. So how do we go forward with respect to the development of newer models or more accurate models in a cheaper software or lesser computational powers? In the previous invited lectures, people were talking about usage of artificial intelligence. in replacing the existing finite element or finite volume models. But before creating the artificial elements, the existing simulation models have to be accurate. We have to make it as accurate as possible with lesser computational power. So this was our motivation to start this work. How do we progress further? So we are proposing a 3-step framework to understand this skid resistance characteristics. This picture might be a little bit overwhelming, but I will try to explain one step at a time. So this is the overall picture for the overall framework for understanding the skid resistance. I'll start with the 3 different key elements or key models for understanding the skid resistance. The picture which is shown on the left is the highly accurate model for the tire and the pavement models, which we call it as solid model. Only the solid elements are there. And in the second model, it shows the XRCT based pore and the solid structure. In this, the water can seep in through the structure, and it can help us to understand the pore pressure exerted on the different aggregates or the asphalt materials. The third image on the right is the skid resistance simulation model, which is a simplified model of the existing ones. In this model, it has the tire model and also the fluid model. The fluid model, it's making use of volume of fluid methods in which the air and the water film are simulated in the models, and we will be able to understand the uplift and the drag force. So the first step, what we are trying to do is understanding the friction coefficient between the tire and the pavement surface. So for this, we started with the very basic small scale experiment, which is the British pendulum tester. We are trying to calibrate the friction between the rubber slider and the pavement. Once we get the friction coefficient, once we calibrate the friction coefficient in the small scale model, we are inputting this friction coefficient to the larger scale tire and pavement interaction model. From this large scale tire pavement interaction model, we will be able to get the contact stresses, both the vertical and the shear stresses for the longer stretch of pavement surface. Once we have the contact stresses and the strains, we are inputting this stresses and strains to the simplified tire pavement model, in which we can also see the water model as well. From here, we can be able to get the skid resistance of this whole pavement surface. Over here, we can again obtain the uplift and drag. We can get the mu value from the previous solid model. Instead of assuming the mu from the past studies or getting the values from the back calculation procedures, we can directly get the values from the previous accurate simulation models, inputting that into this second model. Then going forward with the step 3, once we obtain the uplift and drag forces in the fluid model, these stresses or pore stresses are transferred to the moisture damage model. In this, we will be able to understand how much pore stress are being generated with longer duration of time. We don't have to see just for one particular time. For longer time, maybe like few years time, how does the pore structure is changing? How does the pore stresses are changing? How permeability values are also changing. This new permeability values will again be transferred to the skid resistance model. We can again try to calculate the uplift and drag force and the newer skid resistance value with longer duration of time. So this is our third step. Going forward with the fourth step, the friction coefficient, what we are getting out of it, we will again take it back to the small scale equipment, small scale testing, or with respect to the British pendulum tester. And again, we can create a loop kind of thing to understand the skid resistance and obtain the converged skid resistance values. So this is our overall picture for for getting the skid resistance using 3 different models and getting the simplified results and more accurate results as well. So at first stage is the model validation for all three different models. For the first model, we are showing the results over here. This is with respect to the solid model alone. We are trying to understand load versus deformation with the experimental results, and the error percentage for all the three cases were less than 3%. So we are going forward with the tire model. Then with respect to the fluid model, the results currently which I am showing now are taken from my previous study. So we are trying to understand the skid resistance, skid number with respect to speed for various water film thicknesses. In our earlier work, what we were trying to do is more towards the back calculation procedures. We always have the SN0 value obtained from the back calculation, and we will try to calibrate the results. In our current study, we are removing the back calculation process in such a way the model will still be validated more accurately. So that is our overall picture. Over here, if you look at some of the results, still some of the results were not that converging or not properly validating at higher speeds. We are trying to remove those things in the advanced models now. So once we properly validate the developed framework, we will be able to get the results pretty easily, and this results can still be inputted in the AI-based models to predict the skid resistance very easily, much faster way. So that's our approach, what we are proposing. So coming to the conclusion, it's like we are currently developing the multi-scale and multi-physics based numerical models for analyzing the skid resistance. We are currently carrying out the proper validation for the existing models using some of the past studies and with the more of the experimental works. In the third way, we are again planning to include the thermomechanical modeling in the further stages. Finally, we would like to analyze the tire traction and wear rate under different different surface conditions, temperature conditions, loading, and rolling conditions. In a concluding way, we are planning to, our ultimate objective is to achieve the zero accidents in the future with the help of advanced numerical models and the AI-based simulations. Thank you. Thank you so much for listening. I think that's all from my side.
Thank you. Thank you very much for staying for your presentation, and please stay with us a little bit more for the discussion within 15 minutes, please. We'll move to the final presentation of this section, and afterwards there will be 15 minutes of discussion, so prepare your questions. And the next presentation will be about the evolution of road surveying, the era of AVs, and I'm calling Christian.
Thank you. My paper today will build a bridge between the automotive sector and the road sector. I will emphasize a little more on road construction and road contractors, but the message I would like to bring is just like the road contractors look at AV technology, autonomous vehicle technology, it might be good in your research to also account for that technology available in those vehicles. So after this talk, the purpose is that I show you what is already present in AV, autonomous vehicle technology, that you could use. For the road contractors, they're also aware that they use that sensors already today to do virtual engineering and design of the road, starting from the foundation of the road and then the different layers they built on top of it. Of course, their motivation is to save on materials and on preparation cost. and check the quality while they pave the roads instead of waiting until the authority after the works accepts or does not accept the work. I'll start with the vision of the future. So today, the road quality is checked by different means, and one of them is with multifunctional vehicle. Multifunctional vehicles are vehicles that integrate a lot of sensors in them, and they collect all the data, and in the vehicle they collect the quality indices from the road, and then report it while coming back home. Some of the equipment that is used to check the quality, and this is mainly for the evenness, is an APL, which is actually the physical representation, the physical machine that represents the IRI. The World Bank has designed the IRI with the quarter car wheel. But for road constructors or road contractors, a lot of work is done manually. They do use total stations to have the positions, but they spend a lot of work while doing or while preparing the road construction. And so they see the light in using autonomous vehicle technology. Here I make the bridge to autonomous vehicles. Autonomous vehicles are like multifunctional vehicles. Autonomous vehicles have a lot of sensors in them. Not to help you to do the road design. No, the main purpose is to drive safe, to keep the car in the lane, to avoid collision, not to hurt pedestrians and dogs that are crossing suddenly, and so on. But those sensors can also be used to characterize the quality of the road. Autonomous vehicles are not there today yet. It's postponed and delayed again, but the technology is evolving and they will get there. Today it's all in ADAS, so adaptive help for the driver, advanced driver assistance systems, that's ADAS, but the autonomous vehicles are coming there. So let me give you an example. Today, when we measure the quality of the roads, road authorities, or also contractors that having in public-private partnerships, they want to have an overview of the quality of the roads. Green is good quality, obvious. Yellow is so-so quality. Red is bad. And black is to avoid. The same data is available for autonomous vehicles. When you go to autonomous vehicles conferences, they talk about sensors and what the car is doing, but they talk 1/3 of the time about connectivity. In the cloud, big players like Google are building a high-definition map of the world, of the road networks. Looks a little bit like this. So if we manage to integrate some skid resistance or other parameters that are important for safety of the drivers, then the autonomous vehicle will connect while approaching a black area and be warned of the quality of the road. On top of that, and it's part of the solution, and I refer to the keynote of Professor Wa, part of the solution is that the autonomous vehicle itself will measure road quality. So here an example of a network, what is available for autonomous vehicles or for road network owners. Let me zoom in on the bad section of the road, just as an example, and zoom in even further. Here you see red and black to avoid. Maybe the message for autonomous vehicles is don't get there, I don't know. And even other data that might be available on the surrounding. Like here you see in that bad road section, a lot of residents are living there. So when you plan your road contractor work, or when you plan renovation, you might account for all the disturbances for the residents. For the autonomous vehicle, it might account for a lot of people are living here, so they might cross the streets. Although I'm allowed to drive 50 kilometers per hour, I should slow down. And all this data is available in the cloud today, but not all centralized. I zoom in some deeper. And here I see where that road was black and red, so bad quality it means. And I see also why. This is where it started from. The autonomous vehicles does not measure red or black. It measures something, In this case, the road surface with a LiDAR technology. Everybody has heard about LiDAR technology. So it measures the full road. And autonomous vehicles, they prefer numbers. So all there is in numbers, in the geometry of the road. Here we visualize it in colors. So we as humans can have also an impression, and an intuitive impression. Green means flat road. Blue means subsidence. Oh, sorry. Blue and purple means subsidence, so potholes, and yellow and red means bumps. So here already intuitively you see that this road is in a pretty bad condition, and you can imagine why the index of quality is coming out bad. Here you see some manholes that are sunk, might also be dangerous, some potholes, just giving you the picture of one of the measures an autonomous vehicle will give or will measure itself. Of course, every autonomous vehicle also has a camera, multiple cameras. From cameras with AI, you can deduct a lot of information on the quality of the road. Besides the pavement surface, also quality measures. Another example where we have pavements, and you see that the pavements on the camera image that it's worn, but you don't know if it's dangerous for autonomous vehicle. If you look at the 3D geometry visualized with color, you see that indeed it might be forced in a certain track, and so might be dangerous, might be influencing the behavior of the vehicle. Another example where the camera image will not give the full picture. And this is an example of an intercity road where commuters were going up and down in the morning and the evening, and where there was a lot of complaints about the rough concrete slabs that were bothering noise to the neighbors and discomfort to the commuters. Just before elections, a lot of roadworks happened just before elections. Just before election, it was decided to renew those slabs. Slabs were renewed, visually inspected, and everything looks fine. Indeed, on the 2D picture, it looks fine. But unfortunately, within a month, a lot of complaints were accumulating from the neighboring residents and from the commuters. And when you look at something that an autonomous vehicle is measuring, the road geometry in detail, millimeter precise, you can imagine why. It looks like a washboard. Remember the color code, green is flat, blue is subsidence. So it's like going up and down at a higher frequency, making noise and also discomfort. How is it measured? A little bit about the technology. In autonomous vehicles, you have a GPS. Today, we work with RTK GPS to have a very precise, centimeter precise location of every deficiency of the road. This is the kind of the LiDAR, a special LiDAR. It's not a traditional LiDAR with the camera on top of it to collect those 6 dimensions. And as I said, it's technology from automotive applied today in research phase on road contractors and road production machinery companies. So it's built on any machine. It measures 28,000 points of the road surface simultaneously. And well, the machine or the vehicle can be at 120 kilometers on the highway, but the machine goes very slow, production machine, also that works. As long as the machine is not moving, the same 28,000 points are measured. And then a machine moves and scans the full road and gets that digital twin that we see in color code. And the result is a detailed geometrical representation of the road, including the 3D geometry and the intensity information. Intensity information research is done to see how intensity, reflectivity of the road can represent some slippery conditions. You all know, for instance, on the lane markings, if you're a biker, on lane markings, it's more slippery. It's also higher reflective, but it's more slippery. I'm not saying there's a one-to-one physical relationship. I've seen with AI, you could deduct what intensity can warn the autonomous cars for slippery conditions. A double lane, so the intensity that you see here on the side also marks the lane that the autonomous vehicle needs to know in what lane and to keep the lane and drive autonomously. And to go for productivity for those road contractors, processing is done on board. So just the measure of the road geometry is not sufficient. You want to deduct what is the roughness or what is the skid resistance. All data collected by an autonomous vehicle should be then translated in quality indices, safety indices. And so the message is that this technology is used today by road contractors in their design. So they measure the foundation of the road and then can, from their virtual design of that road, see what thickness of layer the machine should put on top of it to follow the requirements of the authority. An image of something that's really in research phase ongoing today. Why is the technology from automotive autonomous vehicles interesting for them? Well, you can place it on any vehicle. It can be on slow driving machinery or higher driving vehicles. You have onboard processing to have the quality index that you want to know, so you can stop the works because the condition is, the result is not good enough and will not be accepted by the road authority. It gives high, accurate, high-resolution, 6-dimensional data, geometry, intensity, and camera images. And it's a machine-wide. That's for the road contractors. And just to give you a hint that it is seen by road leaders, this is a shot of a few customers that are using this road LiDAR technology, where you see automotive companies, where you see road inspectors, surveyors, where you see suspension companies, where you see tire companies, where you see road machinery equipment companies, and so on. So as a company, we started also off in the, not also, we started in the autonomous vehicle sector. We are a LiDAR company. We moved with this technology to other sectors like mining and warehousing. And since 5 years, we are called by research institutes and by contractors to apply this technology for the road sector. And so my request to you is to also have a look at all technology available in autonomous vehicle, because it will help you also collect the quality of the roads by the cars that are driving anyway, crowdsourcing of data. As a company, we have headquarters in Belgium and have offices in the United States and in China, and work worldwide all around this sector of automotive and road markets. And so the conclusion is that, or the message, have a look at that technology that road contractors are already looking at, where it might help you in research for your challenges. Thank you.
Thank you very much. And now we have a 15-minute period for discussion. Would like to open the session and ask a question to one of the presenters. No? Well, I can start, actually. I can start. Well, in this session, I think we saw opposite aspects with very theoretical modelings and also very practical approach to friction and damage and what happens to pavement. I would say it's, and I would really like to have a comment. So it's open to all the presenters. I really would like to have a comment and thinking on people that works every day in our networks and that need to use the information and have to deal with safety and particularly with friction. On one side, the theoretical models, how do you think you can use it in a useful way for example, for motorway managing, which is actually the most relevant type of work where the friction is dealt with. And in the other side, with all these bad examples, as I told, how to solve it and how can we look at these problems and try not to happen. So I'm looking to Veronique, and she's looking at me. I think she thought about the subject and can help some people here that has the same question.
In fact, we are now in a period where we are very powerful tools. So we are able to collect a lot of data and to try to go in very small scales. So I think that the theoretical approach is very important to try to understand really what is happening in the materials and in the tire road contact area. But I understand that it's difficult for road manager to directly use part of the the work presented this morning. There is a step to go forward to transform, in fact, our theoretical approach in something more usable, easily usable. And that's why there are some presentation. For example, Professor Anupan showed us a very simple tool for wearing resistance, and I think this is the kind of thing that can help the road manager to apply our job. In my presentation, I didn't have the opportunity, but at the end of the job, what we managed to explain is, for example, the scale that are relevant and that the scale that disappeared. And we make a connection with the size of this scale and the aggregates, the composition of the asphalt mix. And we have the collaboration with FH company with designing the asphalt mix, and we say, okay, you are designing it with mechanical test, but based on the multi-scale analysis, what we say that maybe you could try to decrease this size of aggregates and the quantity in the limit of something reasonable for mechanical performances. So this is the kind of work we need to go further to help for the better design, in fact. So I think that models are very important, but they mustn't be the end of our job. We are academic, but we are also working with the real world. So I think that we have big opportunities, and now we need to develop more applicative projects, in fact, and to try to solve the issues, for example, raised by Professor Woodward. When we see all the distress, it's terrible. So we need to avoid these kind of things.
Okay. Thank you very much, Veronique. So what we need with all this theoretical modeling is approach with companies and more contact, I think, to lead to more useful models. And now I'm waiting for you.
Okay, well, I am definitely not a modeler. I was no good with sums at school, so I am not a modeler. What I do have is a lot of experience in the real world, working with industry, working with the quarrying industry, the asphalt industry. And thanks to my colleague beside me here, I got introduced in motorsport, big-time motorsport, maybe 10, 15 years ago. And I was told by name dropping, the head of performance and hybrid systems in Ferrari. This is GT cars, not motorsport. Well, motorsport, but it's GT cars. To go to a conference that was being held later that year. And we went to the conference, me and another guy called Campbell, who subsequently got his PhD. And it was a simulation conference. Maybe 300 people from the tire and vehicle industry. And Campbell and myself were the only people there with any knowledge of asphalt and the contribution of road surfaces. And consequently, when the word got around, we were introduced to everybody. We got really drunk. That was the best way to do business in the real world. The problem is you don't remember what you said that night. So be careful, younger researchers here. But that's how you do business. You develop collaborations, contacts. You get knowledge, inside knowledge. It's okay working with idealized models and theories and stuff, but the real world is very different. And everyone here is filtering into the real world. And I always like, if I'm given the opportunity, to talk about what happens in the real life. And I picked those couple of simple little case studies to let you see just what can go wrong. You can have the best possible model, but something silly like 2 or 3% of really bad aggregate in your asphalt mix, and bang, your brand new road fails. So please start, if I can get somebody here or some of you to start to think about this in terms of application of research. Develop a better aggregate test than what we have. There's nothing wrong with it, but they do not predict performance adequately.
Thank you so much. Does anyone want to comment or make a question? Or everybody over there? Oh, I'm sorry.
Just as someone who developed a pavement management system about 50 years ago in the state of Arizona as a young engineer, and I admire the gentleman talking about experience. As I listen to these presentations, I'm reminded of an expert at that time who said to me, there's a fascination with data, a lot of data. But the question is, what are you going to do with it? How do you translate the data and connect it to performance? What I hear is a lot of snapshot data, but unless you can get it along a long life curve and start unraveling that, you just have a lot of snapshots. And they're beautiful. It's a lot of data. But the bigger question is, how can you synthesize it down to a few things? The rest of us, pavement design engineers who do not have PhDs, who do not have a super-duper computer that only runs in Singapore, which is great for Singapore. But for the rest of us, what does this mean? My second thought is, and this gentleman here is great with all of this data that's coming from all of these devices, do they ever get down and collect it so that the agency, what I used to work for was the government, who, by the way, are the ones responsible for the roads. They're the ones who fund it, create the specifications, check the construction, and then ultimately maintain it. Do they have access? Are they being trained? Just some thoughts. This is a great group. Many of you are younger than me, and I'm sure you will tackle these and do a great job, but let's keep a few things in mind. Thank you so much.
Thank you so much. Regarding the computer, just let me say just that we are installing a big computer here at the University of Minho, so we'll have the opportunity of performing. So in a few months, I think we'll have one, so let's take the advantage. Just an extra information. Another question or time to go for lunch? Okay. So thank you very much for your presence and patience. I hope you have enjoyed. And now we are going to lunch. Please go out, turn left, go outside, and then look at the building in stone outside, and the lunch is there. Okay? And we'll be back at 2 o'clock. Thank you. Thank you. Yeah, we changed some emails, but we don't net yet. I'm Elizabeth. Yes, yes. Temos que perguntar ao senhor Alice. Sorry, just a rational question. Yes, actually, I would with noise and I will show you how I link both. Yes. I'm developing using driving simulator. And tomorrow you can show me simulators.
I have to introduce you, eh?
Yes.
But I don't
Yes.
Ah, here it is. Ah, okay. Perfect, perfect. And I would like to upload new version.
Yeah, we do. I like to check if my PPT is the newest.
I will just. The next
Yeah,
one.
oh, yeah.
You are here.
A new one, yeah.
Number one, the first one. One, two, three.
Originally is
Hi. Hubert, yes.
Very nice to meet you. Hansen.
Senhan, are you in my Baopeng? Bia. Yes, yeah. Uh-huh.
20 years.
Okay. So that we can start, huh? You. Okay. Okay, I think we can start. My name is Luc Hubert. I will be the host for this session. Good afternoon. So this is a session about road noise. I have the pleasant duty to introduce our first speaker, keynote lecture by Professor Elisabeth Freitas. Everybody knows, of course, Elisabeth, but I will briefly give her CV. She holds a PhD in civil engineering obtained in this university, and she has been a researcher and assistant professor in this university in the civil engineering department since 1998. She develops research on surface characteristics of road pavements, and she's also working on road safety. She has been involved in a lot of funded projects, national and international, and been acting as a principal researcher. She's also a member in the CEN working group 5, surface characteristics. She's also coordinator of the Mirror subcommittee and provides consultancy services to companies. So she will talk about the title of her presentation will be Beyond Tire Road Noise. So, Elisabeth, you have the floor.
Thank you. So I'll start by where some people today already started, so just to remember and then to make the noise, which is the aim of my presentation, in context. So we have been faced with year changing in the mobility paradigm, and there are many things that are being changed and studied. We talked about connectivity, we talk about clean energy and sustainability. We talk about nature and, of course, vegetation. And there's something behind this, which is to give back the urban space to people. And to do that, we need a human-centered approach. So connectivity is related to vehicles, but there are like pleasantness in what we do every day, and there are other things that are, let's say, in fashion, and that all politicians put in front of their politics, that is the pedestrians and the walkability. And why is this related with tire road noise? Because noise is one of the most relevant sources of pollution in urban, particularly in urban centers, and it comes mainly from the tire, and that's what makes the link between all these subjects. And human-centered approach. So, what I'll be doing with this communication is to discuss the role of tire road noise in this changing mobility paradigm in several aspects, and taking in mind that there's an emergent demand of giving back the urban space to people. For that, I'll start by revisiting the design of low noise pavements and put that then in a urban context. So take a look to the assessment of thyroid noise based on nuisance, annoyance, and perception descriptors, such as the psychoacoustic descriptors. But first, we have to know, and it's really relevant to know what noise does to us as human beings. I must say that this came from work that I did in cooperation with Emmanuel. And we studied and we read a lot of papers regarding addressing noise, of course, but all coming from medicine, so written by doctors. And reading, because noise actually kills us, and even worse when we are sleeping. We hear often saying, oh, I don't mind with the traffic noise. I like to fall asleep with the traffic noise. So that's a way of killing us. And there are several factors to take into account. For example, we are individuals and we have sensitivity to noise that we must take into account. And for example, we react to noise differently when we are a child or adult or someone that is old. There are some measures very well known, like the maximum noise level, the SPL, but we have other noise that we need to take into account. The number of events, the duration of the event, for example. And why I'm referring this? I'm referring this because when we have continuous noise, like the one of the traffic streaming, the effect in our body is different from, for example, a car passing by, where one passes and the other one sleeping. What does it make? It creates cerebral and automatic arousals, which means that it wakes up us and makes our body to react, even if we are not conscious of that. Awakening frequency, or if we awake a lot of times, we hear these sounds. For example, in the morning, they are awful because they disturb much more our sleep and our rest than, for example, in the beginning of the night. And this creates short-term effects and long-term effects. So performance reduction, daytime sleepiness, impaired mood, and also cognitive performance. That's why it's so important to control noise in schools. But there's a long-term effect which recently was studied and discovered, which are the cardiovascular and metabolic diseases. And why do you arrive here? Because the process that is created in our body is exactly the same of the stress. Okay, so to sum up everything that I just said, the noise stresses, and we have exactly the same result as being stressed by other reasons. And we should control it at night, but of course during the day. So, if we want to reduce thyroid noise, we need a holistic approach that considers several factors, not the road. So, regarding the road in itself, the road design, we also need to rely on urban planning, but we need to make an improved approach to human reaction to noise. We can't rely on the max or the L equivalent, so the most basic descriptors of noise. So, but I know that most of you is worried about how to construct a low noise road, and I will start by that because it's my opinion the easiest part. Is in mind that is one of the most relevant noise sources, the tire road noise. So, some factors affecting the tire road noise. We have the type of vehicle, so light vehicles and heavy vehicles have different noise levels. The light vehicles produce less noise than the heavy vehicles. For also speed, the highest the speed, the highest the noise, independently of the vehicle. We have a big effect of the surface type. If we think of big different types like flexible pavements and rigid pavements, and we can also include the elastic or the elastic pavements, there are big differences. So the rigid pavements, most of them produce or generate higher noise levels than the flexible ones. And we expect that the elastic pavements produce even less than the flexible pavements. Then there are some that we must pay attention. So absorption, that is related to void content. The highest absorption that is connected with higher void content should lead to less noise coming from pavements. Another factor that is really important and we can control in several stages is the aggregate size. If we select the good surface, we can reduce noise at the surface. So small aggregate sizes are associated with less noise. Not every time. I will show you one example where it doesn't happen. Thickness also, we can fine-tune. For example, porous asphalt with more or less thickness, so we can have more absorption in the frequency that we need, for example. The stiffness is very much related with the surface type. If we have, for example, these poroelastic surfaces which are very elastic or not stiff at all, the tire road noise is much lower than compared to common surfaces. We have the effect of temperature, so higher temperatures are related to a little less noise. And we have here an effect of aging, where we can also include some distresses, and I will show you then later how. Okay, I was telling before that optimizing the grading is a good tool or a good way to control tire road noise, and also the aggregate size to be small, but we have to pay attention to the texture. If the texture is positive, like this one, where we can see the peaks turning up, the noise level will be much higher than in this case. And for example, this one, which is a slurry seal, where I had the opportunity to measure the noise, and it's really awful. And that one is related to, for example, this one, where the surface is flat, aggregates are small, and the noise level is the lowest that we can get. And I also had it here blocks, granite blocks or cubes that are used in city centers, for example, for the ones that had the opportunity to visit Guimarães. We have these pavements everywhere in the city center, and we even have worse than that for tire road noise. And these ones are really different from the flexible pavements that are shown here. And the noise level increases in this direction. So we can do some advanced testings and measurements. For example, here I have an example of the texture level. And if we reduce the higher textural wavelengths, we can expect less noise. And if we increase in this band here, we can expect lower noise. And we can also, in porous asphalt, optimize a few parameters like the thickness, as I mentioned, the void contact, and then the flow resistance that is provided by the aggregate. And we can, this is an absorption curve, and we can move these peaks to the left or to the right, or we can make it longer or smaller. Of course, we want more absorption. We want this as big as possible. But we can try to move this, for example, for these frequencies where the noise that is generated by the tires is the highest, so to match these peaks. And this depends a lot on the layer thickness, not only for asphalt, but also we can do this with dense asphalt. I leave here a few suggestions in a low noise surface. So first, we should choose the smallest aggregate size, so acceptable regarding the durability, because we need to pay attention to that. We should make the texture as small as possible, and never forget what was discussed this morning also, which is the skid resistant, and in particular the wet skid resistance. We should create a negative texture, and the selection of the aggregates should be careful, so they should be flat or have flaky faces, and we should ensure that these faces are upwards. If possible, higher voids volume, and also, if possible, make it as flexible as we can. So these are the main guidelines to have a low noise pavement. And here are some examples. We can achieve this by ultra-thin or thin layers. There are these quite well-known two-layer porous asphalt, where the biggest aggregate is below and the smallest aggregate is at the surface, and at the same time, of course, this is porous and have a high volume content, and the surface is very, very flat. And I have here an example of a poroelastic. So Luke can say a little bit about that, because he was in the development of this pavement, which is made of rubber essentially. And it provides a really nice reduction of the tire road noise. Well, and how do we put between all these aspects, the humans and the person? Well, we start looking at the spectrum and from the different pavements, and they have different features, okay? What happens when we work only with the noise indicator that average everything, like the LMX, the LMX doesn't average, so it takes only the maximum, or the LE so the equivalent noise level. What happens is that we can have provoke us, I'll say that way, different reactions or sensations, but they have exactly the same equivalent noise, okay? So we should look at this in a different way. These are examples of spectra that came from the CPX method, and this method measures the tire road noise near the wheel. There are other methods, but this one came from a similar systems. Well, and we should also pay attention to something very important. I would say that in motorways is not so relevant, but for example, in urban centers where the speed is lower and there's less money for maintenance, like this or raveling is really bad for noise, particularly at low speeds. Okay, this graph was the noise level was measured at different speeds in pavements with cracking and raveling, so it is an average to have an idea what happens in general. And this is, so these are the non-distressed pavements and these are the distressed pavements. And we have a few decibels of increase, which makes a huge difference in small speeds or less higher speeds. So what I would like to say about this is that we should face the noise as a noise measure to control the noise at low speed roads. Okay, you should pay attention, more attention to that and to the cracking that occurs in the surface and raveling also. It doesn't mean that it's not important at high speeds. I can give an example that recently happened in a porous asphalt where the result was not according to what was expected. So if we have a porous asphalt, we expect to have noise levels that are lower than dense asphalt. It was not the case because the raveling was really high and the MPD was really high. So the vibration of the tires was so much that the noise was really, really very high. Okay, so there are some tools to predict noise and then to try to controlling it, combining different measures. So we have traffic management, we can lower speeds, expecting that this will reduce noise. We can try to do the best selection regarding the road surface. Of course, there are some aspects like aesthetics, the architecture, and I always give the example of Guimarães, where we are in an historical center, and the choices of the pavements are based on aesthetics and historical decisions. And we can then use the noise maps to have an idea of how the combination of these aspects can result, and have also an idea of the number of people that is exposed and make our decisions on this. Well, I want to arrive here that is, in this process, is missing something, that is the human perception of sounds. What is noise perception is the first thing, and what is noise? So noise is unwanted or unpleasant sound. The other aspect is a subjective concept, and that we have auditory characteristics, circumstances, and it depends on the location where we are. And perception is a brain function that gives meaning to sensory stimuli we need to interpret and select and organize that information, and perception defines visually and auditory stimuli. And we need to take this into account. Another definition that we need to bear in mind is what is annoyance, because when we talk about noise, is the next thing that comes is that we are annoyed or not annoyed, and the concept behind this, and annoyance, a multidimensional negative reaction that is related, so to immediate behavioral noise effects. I started at the beginning showing that noise has effect, so it's related to disturbance, interference in ongoing when you look to annoyance, aspects such as nuisance, unpleasantness, and sometimes getting on one nerve, so getting a little bit mad, which is also referred here. So include feelings of fear or mild anger related to a belief that one is being avoidably harmed. Okay, and how do we study annoyance? Annoyance can be studied through questionnaires, but we can use measured sounds from the road, which is the case, and we give them to people and to rate how they feel regarding a noise. What is the level of annoyance? So rate it please from 1 to 10. That should be more or less the question. And this graph shows an interesting thing. For example, asphalt rubber or desk asphalt have quite similar ratings, but for example, the cobblestones or the granite tubes are far away from these two surfaces. So the level of annoyance is much higher than for the flexible pavements. We have a moderator, which is sensitivity. We don't rate the sounds exactly the same because we are humans, and it's a characteristic that we can measure also through questionnaires, and this shows very clearly that people that says that is sensitive to noise rates, of course, noise higher than the people that says that is not sensitive to noise. And just for related to this, there are some skin conductance tests, so that show how we react to noise, and people were exposed to just 5 seconds of these sounds, and the ones that are rated being sensitive, also more annoyance because they are sensitive to noise, their skin reacts more than the other ones. So we have immediate responses that we should be aware and use it in some way. So we should perform an enhanced approach to noise, and we can use some psychoacoustic indicators to do that and explore contextual cues, so where we are, what is our environment, which are the characteristics of the environment. So in literature, we found several. The most used, the loudness that is related to the equivalent sound pressure level, but is a perception-related indicator, the sharpness that is linked to high-frequency noise, the roughness, which is associated with the rapid amplitude modulations in this frequency range, and then fluctuation strength, which is related to low amplitude modulations. Question marks, actually, if we should include also indicators related to speech, because we live in urban environments, we are on the road, we are pedestrians often, and we like to talk with our mates. And can we do this in a environment, in a city center, or in a road where there's a lot of traffic? That's a point that I would like to investigate further. So, perform a holistic approach, so a complete approach. We can use immersive experiments with human subjects or people, and we can do this kind of tests. So here is an example where the sounds measured on the road are given to hear to several persons. Here the context was in a crossing situation, but it will be done in future in other situations, and with very interesting results. For example, here we could see that loudness explained better the crossing percentage than let's say the most used noise descriptors, like the SPL, so the ones that we use all the time. Here we could have all very good relationships, and here you can see that there's a kind of threshold. We can see this here, but using loudness, we can explain better how pedestrians cross and when they take their decision, which are the levels. We have very other interesting results regarding vehicles, electric, so combustion, and with no sound. Here we have the response time, so if we are crossing, we have a response time to the stimulus, so to the sound that we hear and to what we see. And with different speed patterns. So here the vehicles were at constant speed, here they were slowing down, and here they stopped. We forced them to stop. And these curves are almost over each other, which means that the persons that did the experiment didn't make a huge difference, or nearly none, between electric and gasoline vehicles, and also when to see the vehicle passing by without the sounds. This means that their answer was quite similar. Okay? We can discuss a lot about this. So if we see the vehicle, what we can say here is that when we see and hear the vehicle, we have approximately the same response as when we only see the vehicle, which means that probably the sound is not doing a lot here to help the pedestrians to cross, okay? And this corroborates what I've just said. Here we have different auditory conditions with sound and no sound, visual and sound, and only the results are quite similar. Well, as the experiment that we did was static, so the person was like me here, hearing the sounds, we wanted to improve the experiment, and we took all the modulus and everything that we know about tire, road noise, and the factors that affect them, and we tried to oralize the sound. What does it mean? It means that we have the headphones and we hear the car passing by. If I turn my back to the image, I feel the car passing in my back. So the sound was spatialized, and I can move, and my auditory sensation is exactly the same on the road. And we did experiments also. You can take here a look. In this case, always on a crossing situation. The pedestrians in this case were moving around with the sounds in the ears, and everything was being connected. So we know where the sound comes, where the vehicle is, the noise level in a certain point, and the idea was to study the crossing behavior. Okay, so what do I want to say with this is that when we have complex environments like this one, so these are streets from Guimarães, and here we have a pavement, here we have another one, and we have to select and make our decisions. For example, this is a very nice street. I hope you have had the opportunity to go there, but this is extremely noisy, and the people that live in these houses, they are really, really annoyed with the noise. And for example, in this case, it didn't happen at all. It is very nice to drive in this street. We can drive in this street because the architect selected really well the pavement, and it took in attention what I said at the beginning: flat surface, small, in this case, granite blocks. And I had the opportunity to measure the noise here. Here I have the idea that I'm driving at 30 kilometers hour. It's equivalent to driving at 7 kilometers hour in asphalt pavement, while here is much less. So, and we have lots of opportunities to select. We need to have a context, and we need to introduce the human behavior to take our decisions. My presentation, we have different environments. Now we are coming in many countries. This is already done, but in Portugal, for example, we are arriving to the shared spaces, and there's a lot of work to do in this area to define what are the speeds, what are the pavements, and the vegetation, if it has an effect or not, and how we should design the street. Here, the choices are not the same, but we can do in these environments the same studies for higher speeds. And my expectation is that in the near future we can turn road noise into music for the ears, and this is still a kind of a dream, but I hope to arrive there. And thank you very much for your attention. Welcome.
Well, thank you, Elisabeth. It's time for our next speaker. That's Biao Peng. Is he? Yeah.
Yes, Professor.
Yeah. Biao Peng will speak about his research on the test methods of an indoor high-speed tire asphalt pavement interaction noise. You have the floor.
Good afternoon, all participants and presenter. I'm Hansen, just from this university. The Biao Peng is my student for PhD. He graduated. He studied test method, just part of the content presented by me today afternoon. At first, I'd like to thanks to the Professor Paula and all members of this conference committee, and also thanks to the International Steering Committee, Professor Fa. Also, Professor Fa is my colleague in China University. Now we have a big team in our university. So the Professor Fa is very famous. He have a very broad research on the pavement surface. My presentation just is research on the test method of the indoor high-speed tire asphalt pavement interaction noise. So that is a background. In recent years, more attention has been paid to traffic noise in developed and densely populated areas, since the tire road noise when vehicle driving speed above 30 to 40 kilometers per hour dominates the traffic noise. Research institutes have or are working on the way to reduce the road pavement noise. For example, I know the Persuade project, that is a very big project in Europe, is a 60 years project which started 1st September 2009 and is funded within the 7th framework program of the EU Committee. And also another example is the CPOR. Just the project was conducted in Poland. And some pores tested section were also conducted in Japan previously. Also, there are many other projects related to low noise pavement in the world. Process of the research pavement noise reduction technology, noise testing can be carried out by indoor or outdoor field testing method. Outdoor testing methods are related to high cost, long cycle, and the test results are susceptible to the various factors. Therefore, number of the indoor pavement noise test methods have been or are being developed. So this is some example about the indoor test method for the pavement, tire pavement noise. In Germany, Germany Federal Research Institute, there is a vehicle pavement interaction facilities. It belongs to the inner rotating drum. This is just this. That's also is famous. It's a diameter of the pavement drum is about 5 meters. Maximum velocity is 208 kilometers. Installed at up to 24 samples. This is a picture to prepare that just a curve slab for the test, just 24. The tire in the inner rotating drum fits close to the test pavement. For this prepared sample, also have to spend the many time. And I think the noise inside the drum is easy to be reflected and affect the test result. Just for this tire is here, the rotating pavement just around here. So the sound is easy to be reflected, but just my image. Maybe in future, I will just get the direct feel about that interim test equipment. Another one is American Purdue University. It's called Tire Pavement Test Apparatus, TPTA. It belongs to the outer stationary drum. So just this one, diameter is 4 meters. And the maximum velocity of the tire running is 40 kilometer per hour. Just the tire just rotate around this drum ring wall. So its problem is no effective compaction, no effective. Here we can see some manual or some tools to compact the sample. And the specimen preparation procedure was tedious. Only one specimen could be prepared each day according to the material from the Purdue University. Another one, the Poland Technical University of the Gdańsk. It belongs to the outer rotating drum. I think there are many this kind of the equipment in Europe. There are many. So in Poland, the diameter is about the 1.7 meters. So relatively small drum. So some country maybe have the big drum, big diameter of this kind of drum. So the outside surface, just the outside of the surface is made of the artificial material. That material just is it's not real pavement material. Just I think artificial, just imitate the material, especially the texture of the surface is similar to the pavement. Also can give some thickness of the pavement. For example, some pores, pores we can put, but its thickness cannot be the thin. If the very thin, maybe during the rotating, maybe the pavement material fly away. I think that adhesion is a big problem. Also, there is another example in South China University of Technology. And another example, just in our university, we call that high-speed tire pavement test platform, abbreviated the HTP2 in Chinese University. For this equipment, the diameter is 4 meters. Little bit we can increase the diameter if the thickness of the pavement becomes thinner. The maximum velocity is 8 kilometers per hour. So we are going to extend the velocity or speed of this tire running speed. Install up to 12 pavement sample. This HTP2 just is housed in the semi-anechoic. You can see that the semi-anechoic in this environment. So background sound level is about 33 depths. So that environment noise is very low. For this drum rain wall, pavement thickness can be varied from 5 millimeter to 90 millimeters. So if the thickness of the pavement becomes 9 centimeter or 90 millimeter, maybe the double layer of the low noise pavement we can test in this apparatus. The car tire diameter is 60 to 8 centimeters for the time being. So we are going to extend the diameter size to 110 centimeters. Also, the load of the tire on the rim wall can be changed from 1 kilometer to 5 kilometers. So we can test the tire pavement noise under the different loads. This video is tire running speed is up to 8 kilometers per hour. So all drum rain pavement is asphalt pavement. This is a video of the tire running speed about 30 kilometers per hour on the 2 pavement samples. We can see that the one is a cement concrete pavement with transverse grooved, and this asphalt. So we can feel that the sound, the big sound is belong to the cement concrete pavement, and the lower sound belong to the asphalt pavement. So we can measure that from. So in fact, pavement noise test results are affected greatly by type and the smoothness of the pavement sample on the drum wall. We can call this the drum wall. So for these facilities or equipment, also if we change the tire direction, there is a special track on ground. Use this ground track, we can test the durability of the material. Also, we can measure the texture evaluation under the certain load. So, but for the time being, we can just measure that the drum rain wall pavement noise. We can use a different. Tire. So we can change the different tire. Even some tire is belong to the ASTM standard, or for the time being, the vehicle industry, much more. We can test a different tire of the different kind of the vehicles. So for this HTP2, there are two molding methods. One is a initial manual molding. Another is improved automatic molding. So for this one, for this manual molding, just use this rod ruler. We just use this rod ruler to compact the different mixture. But this compaction process cannot be standardized. Compaction quality depends on the operator experience. Also is a time consumer and laborious. Pavement thickness error is a very big, 5 millimeter. Rod roller are prone to overturning and existing safety risk. Now, because there are so many shortcomings, so we developed improved automatic molding, just like this one. There is a curve, just a framework, and put this curved sample on the here. We use a special fixed rule along the certain curve to. Okay, yeah. So this is for these two methods also makes a different result. So that we just the object of the research optimize the influence molding method on the pavement noise and investigate the maximum number of the pavement type of the single cycle test of the HTP2. Also verify the effectiveness of the HTP2. As this mixture type we used to carry out this test research. And we found the different compaction with a different, just comparing test result of pavement noise level of the molding. From here, we found the advantage of the improved automatic compaction. So also here some test result for the two test method. The standard deviation of the pavement noise level test for two molding method are different. Also, we test, we do the many tests to the optimize, to determine the optimum test pavement length to maximize the efficiency of the noise of the test. So we here, this is some test procedures for this research. So we also found some test result to measure the tire pavement noise, just the different lengths of this HTP2. So for total circumference, more than 14 millimeters, 40 millimeters, or about the 40 millimeters. So we just measure. Finally, conclusion, just normally for single circle, we can measure the three types of the mixture. mixture. Just that is a test result. Okay. We also verify the effectiveness HTTP tool by using our special vehicle test track. Use that as just an on-site test result. With indoor test result. So this is this morning, our professor also gave some information about this test result. So we can use indoor test result to predict the pavement noise on site. So that is a conclusion because of the time. So that's all my presentation. Thank you very much.
Thank you very much. Very impressive, highly interesting. But we have to move on. Next presentation is a presentation made by Ablenya Barros. It's about the mechanical impedance for the acoustic assessment of low noise pavements. Ablenya Barros is PhD student of Professor Cedric Veuye of Antwerp University, and he is presenting today the work. Cedric, you have the floor.
Thank you very much. You hear me? Okay. Thank you very much, Luc, for the introduction. So indeed, Ablenya Barros is a PhD student of mine. She's also almost on her way to go to a conference in Boston, so that's why I'm replacing her today. So we've already heard in the previous presentations about the importance of stiffness. And actually, it's mostly the dynamic stiffness of the pavement that plays a role to make it low noise or not. And an alternative way to mention that is the mechanical impedance. And that's actually the ratio between the driving force and the response of the pavement, the vibration velocity. So, very shortly an introduction. We've seen already that surface texture is very important. I'm not going to conclude that. Professor Freitas already mentioned as well porosity and absorption and how they play a role, but as already mentioned before in the previous presentations, stiffness, elasticity is also important. So the idea is that if you can bring down the stiffness of the pavement to the level of the tire, then the tire vibrations will also be lower and therefore you will have less tire emissions. This morning session, we talked a lot about issues with different test methods and a lack of harmonization, and unfortunately in my presentation, this is the same problem. There are different researchers who do their best and come up with their own approach based on standards that have not been optimized or developed for road surfaces. So we have a variation in input stimuli. You see some images where they use an impedance hammer. It can have a different weight, it can have a different tip. Sometimes they use a shaker to inject more energy, and also the location, the measurement devices, the accelerometer, the way it's connected. It will all have an influence. And of course, if you're measuring on the road surface or in a laboratory, you will also have different boundary conditions. And that's what my talk is about at the moment. So what have we been doing? You see some pictures from in the lab. So we have made our own asphalt slabs that we glued onto a concrete surface. And then we tested the mechanical impedance of those samples by using an impedance head instead of an accelerometer. It produces an immediate response, an immediate measurement of the impedance, and it also gives better output signals with less noise. We used an ORAS data acquisition system that gives us the acceleration, and then by integration we get the velocity, which is what you need to calculate the mechanical impedance. And as you can see, we also did measurements on site, on some test tracks, and on cylindrical specimens as well to see what the effect is of different shapes and boundary conditions. Also those, they were glued onto the same platform in concrete to have the same foundation of your sample. What did we test? First of all, dense asphalt as our reference, a test track, a slab, and a cylindrical sample, or multiple of them, and then some samples and a test track that were provided by Luc Houbert from the Belgian Road Research Center, and who was involved in these well-known projects. Persuade was already mentioned as well. What is the focus? What were we trying to investigate? First of all, can we get repeatable measurements? So what about measurement accuracy, variation, so forth, so repeatability? And then I hope most of you know that bitumen and asphalt are viscoelastic, and temperature plays a huge role in their mechanical behavior. So the warmer, the less stiff they are. And our assumption is also that temperature will affect the measurement of the mechanical impedance. But we never found this in literature, so we did some own testing there. And then, of course, as I already mentioned, we investigated 2 types of materials and 3 different types of geometry. So on to the results. First of all, repeatability. So normally what you see in literature when there are a limited amount of papers on mechanical impedance, but when they show the results, they show the spectrum without any information about variability or information about individual hits. So you take a hammer, you hit the surface, and each time you do this, you will get a spectrum. So we looked at those individual hits, and what we also did was we take away the impedance head and we re-glue it in the exact same location. Unfortunately, results were not good. So what you see for cylindrical sample and rectangular sample for the dense asphalt concrete, both at 5 degrees Celsius. So we put them in freezer for a number of time to get them to the desired test temperature, and each line represents 1 hit. And the 2 colors means you have re-glued the sensor at the same location. So in theory, they should be similar. And what you see on the results, so those spectra, they will be all the same. So on the x-axis you have the frequency. We measure from 100 to 4000 hertz. And on the y-axis, you have your calculated mechanical impedance, the ratio between the force that you input with your mechanical impedance hammer, and the response, your integrated vibration velocity. And you see that you have very large variations, sometimes in between the 3 consecutive hits. Nothing changed. It's just the way you hit, probably. And also when re-gluing, you can have some really big differences. And this, of course, makes interpretation very difficult, or comparison between different research papers or different mixtures. On the test track, things were a bit better. We did the same test, and you see that the deviations in between the hits are better, but not when you re-glue. So there is an important effect of how you glue your sensor to the surface. Type of glue can also play an effect, etc. For poroelastic road surfaces, the results were better, maybe because they had a smaller aggregate size, so they were a lot smoother. So probably there the re-gluing of the sensor is better, less effect. So you see that the repeatability for these ones is actually quite good. But for the asphalt samples, it was a lot worse. So intermediate conclusions on repeatability. Most cases, if you have a very large difference, you can call it an outlier and ignore it. That's not a problem. So when you repeat your measurements on the same location, they're quite nice. But if you take away the sensor and put it back, or ask a colleague to do it, then there are considerable differences. The higher you go in frequency, the less important those differences will become. I don't know if that's relevant or not. Repeatability for poroelastic was a lot better than for dense asphalt concrete. We do find the same natural frequencies even if the values themselves are different. Okay, that's repeatability. We also investigated temperature under the hypothesis that at higher temperatures you would see a decrease in your stiffness. So we preconditioned the samples for 3 hours in a climate chamber, and if we went on site, we went another date when outdoor temperature was different. And we tried to get around 5, 20, and 40 degrees, depending on weather situations. So these are the results for the dense asphalt concrete. 3 different lab situations. So you clearly see an effect of temperature, but it's not completely what we hope to see. If the colors would have been different, I would have been very happy, because then you would have 5 degrees, 20 degrees, and 40 degrees, but unfortunately those two were mixed. Probably as well because of the measurement variability itself. On test track, measurements were repeated at 5 degrees and 20 degrees outside situation. And you also see a clear difference of temperature. So temperature is something we need to take into account when we do measurements of mechanical impedance. I was hoping to get to a correction factor, but yeah, we need more research for that. Similar story for the poroelastic road surface. And here you see clearly a crossover point at the higher frequencies, where a lower temperature gives you lower impedance values at very high frequencies. So let's say our hypothesis is almost validated, but we need some future work. But the variability that I've shown in the previous section, of course, makes it more difficult to come to a very high conclusion. And that's what I just mentioned. Geometry, so cylindrical samples, 12 centimeter height, diameter 10 centimeters, rectangular slabs, 3 centimeter thickness as they are used on site as a surface layer, and then test tracks, 1 at the Belgian Road Research Center and 1 next to our own campus. When you go on a test track on a real road, you will have a lot higher mechanical impedance values. So also there, when you do a lab measurement, it will be difficult to compare your results with the actual pavement. And that's confirmed when we look at the poroelastic road surface, where also all measurements on the road are higher, except in those very high frequencies. Why is that? Yeah, boundary conditions are different. So you're emitting energy in your material, you're creating surface waves, they reflect at the boundaries, they bounce back, etc. The surface area is, of course, a lot smaller for a sample. And the placement itself will probably have an effect on your vibration behavior. It will be a lot more easy to make your slabs and samples in the lab vibrate compared to the road surface. Material, same geometry, same temperature. Luckily, we see a huge difference. And of course, that's the reason why poroelastic road surfaces have such a nice noise reduction. You see values 10, 20 to even 40 times difference in mechanical impedance. So if you just want to compare two very different situations, materials, then this method is valued. But if you want to see differences in mechanical impedance in the same type of mixture and just add bitumen content, I don't believe that you can see a difference in mechanical impedance. Okay, main conclusions. So whatever you see on mechanical impedance, be critical about it. That's my main message, because of the variability and repeatability. We first need to do something about that before we can really investigate how mixture content, aggregates, binder content, etc. will influence the mechanical impedance. Well, a good thing is when we investigate poroelastic road surfaces, the repeatability is a lot better. So for that one, yes, you can use it. And temperature, I'm not saying we've cracked it already, but it's something to take into account. And then, yeah, it is of course also sensitive to the boundary conditions, but comparison between slabs and cylindrical samples was quite okay. But there's a huge difference between laboratory samples and the real behavior on the road. And these are the references that I used for this talk, and thank you for your time and your interest.
Thank you, Cedric.
I just pressed escape and it went blue. Oh, no. Okay.
I take the time to announce the next speaker. That's Gaetano Lichitra from University of Pisa. He will speak about the testing, experimental evaluation of the acoustic performance of innovative low-noise road surfaces.
Thank you, Luc. The work is inside a project. It's a NEMO project. It's an Horizon 2020 project. It's a collaboration between the University of Cantabria and the group in Pisa. NEMO is a noise emissions monitoring and radical mitigation, so it's a big project of 7 million euro, and try to propose a new solution, a wide range of solution as a remote sensing system or innovative materials. So there are many things. Part of the project is also low noise road surface development, and I will show some results about the test case that we did in Florence. There's a long list of possibilities in the project, so I will not go in detail for that. But we try to, in the mitigation solution, we try to test green noise barriers and also road surface design. Also to, oh no, maybe see from here. Okay. That's better. Yeah. So one of the other possibilities is to study new pavements that try to prevent the microplastics, because there were studies that show that 30% of the microplastics in the ocean comes from the rubber of the tires. And another big problem that we try to tackle is the identification of the eye emitters in the traffic. This is for air quality and for noise, in order to give it to the municipality the possibility to avoid these eye emitters. This is the group. It's a very large group of university and companies and organizations in Europe, from the extremely north to the south, so from Norway, Finland, or Spain and Italy. And here you see some of these devices. One is the NRSD, is a system that permits to identify, using more microphones, the vehicle that is highly noisy. And at the same time, on the right here, you can see a device that permits to intercept the exhaust of a car passing by, and in this case, recognize the pollutant of the car. We did this kind of measurements just in Florence. These systems also are with cameras that permit to recognize the plate of the car and connected in real time with the database of the ministries in order to recognize the owner and all the data of the vehicles, in order to verify if respect the emission that are set in the documents. So it's a system that is really useful if you wanted to stop this kind of people. normally we go to the maintenance service maybe for a year or 2 years. In this case, we can invite the people to go immediately to this check. And the pollutants that the system can recognize is CO, CO2, NOx, and PM and ammonia. So they are the tested the pollutants. And finally, I just give you some other information about the payments that University of Cantabria developed. Particularly, one is a very thin asphalt concrete that after I show in detail, and the 2-layer pour asphalts for the peri-urban road. Some data, I don't go into detail of the data of the payments, also because this is just one of the first time that we present the results, so this was a good occasion. They also tried some photocatalytic efficiency using liquid photocatalytic material, but I don't give you more detail of that. And this is for the peri-urban, and the results that they obtain about 7 dB, considering the Knossos reference data. Also, they verified the capacity of the payments to reduce the microplastic, so to retention of that. Okay, but I go to my part. This morning and also this afternoon we spoke about the characteristics of the rolling noise, particularly in this case the relevant of the rolling noise after 40 kilometers per hour. Now this threshold will be reduced in the time because the tires become larger because for the size of and also for the electric car, this could be also a problem because the electric car are heavier, and so the tires are larger and larger. So for this case, we considered in peri-urban and urban roads. I don't go into detail of the phenomena, but we know that for the noise come from the tire vibrations and aerodynamics reasons, and there is well known the phenomena that are connected with the vibration and with the aerodynamic parts, considering turbulence and the Horn effect for the aerodynamics. And this is the definition of a low noise road surface. It was done by Sandberg, that provide a noise reduction of about 3 dBA compared with the most common used one. And there is an important document that was issued some years ago from the Joint Research Center in Sevilla, that is an organization, is part of the European Commission. And this document defined the methods to evaluate the acoustical performances of the road, and fixed the method, in this case, the CPX, that is a standard, an ISO standard that also Elizabeth showed before. This document is not really implemented in many countries in Europe, and we are working with the Environmental Ministry to put the document in the legislation, because we know that everyone can say, I have a low noise payments, but are not really defined the way to verify this. And in the documents there are some limits for when you lay the payments, so after 12 weeks, in this case the value that are showed here are 90 dBA at 50 kilometers per hour and increasing with the speed. And there is the possibility also to check the durability of the performance of the low noise payments within 5 years. This is very important because this kind of application are in Europe. We have to implement the European Noise Directive, so there is an action plan in the city to reduce the noise in the time. And it's important that the money that the public administration spend to reduce the noise maintain their performance after 5 years. In this case, this is a rule in the public procurement. So this is very strong in order to avoid that the administration pay for something that after a few time is losing. The test case was in Florence. In this case, is in the center of Florence, so it's a medium traffic road, but with a standard vehicle. The characteristics of the VTAC mixture is reported here with the maximum aggregate size of 4 millimeters, so it's very thin, and the thickness was 20 millimeters. And we used as Elizabeth shown, a system that was implemented on Vito. We use the SRRT, that is the standard tire to do this kind of measurements. And in this case, also, we have the possibility to make measurements with a laser profilometer in the same time of CPX and the laser and the texture. And this gives us the opportunity to obtain, in the same time, the two important parameters. We use also an accelerometer to exclude the vehicle vibrations. And you see here the results obtained for the old payments. That was for us like a reference, a local reference for that, with a value 95.1 of the parameter. That is obviously upper respect the limits, the threshold that the GPP procurement documents suggest. So we repeat obviously the measurements with the new, and the results were something like 10 dB less. So this is the results obtained. That doesn't mean that the exposure of the people is 10 dB less, because we know that there is a relationship between the CPX value and the exposure of the people. That depends also from the geometry and the point where you measure the exposure. But in terms of benchmarking fixed by the GPP standard, is 6 dB lower than any other low noise payment. So the results were very, very good. And also for the texture, you can see the differences between the old one and the new one, that is according about with what already Elizabeth showed when showed the difference in the texture if we wanted to reduce the noise. So the movement to the low level, to the low millimeter area respect to the previous one. So I go to the conclusion. The project is going, so these are preliminary results that looks very, very good. And I hope you have the opportunity to follow the conferences that we organize. The next one will be the next week in Valencia. This is open. If you want to see also the presentation and the discussion that we will have, is an hybrid event, so you can contact and see in NEMO website the possibility to follow. And that's it. Thank you.
Thank you, Gaetano. I can announce the next speaker. That's David Woodward. He will speak his The title of his presentation is Laboratory Study into Evolution of Microparticles for New Road Surfacing Materials. You have the floor.
Okay, thank you. When I put these abstracts in, I had different colleagues as co-authors, and I picked the short straw to come here. So apologies for listening to me. This is with my colleague, Philip, and this is you could say it's a project that was a failure because of COVID. This is something that we started before COVID, and basically when the university got closed down for a year, the PhD student decided to go elsewhere, so he left the project. And Philip and myself was basically sort of left to try and pull something together and then start to think of this problem again. Particularly when you start to talk to the tire people. And I say through another avenue, I've had the good fortune to start to talk to that industry and the car industry, and you start to appreciate what they are doing or have done. This is the key thing about sort of microparticles. If you talk to the tire people, they know all about this stuff. And it's not their tires which are causing these things. It's the road surface. Okay, and I come back and I talk to the asphalt people in my country who specialize in producing very high grip surfaces. And I'm saying, guys, we need to start thinking about reducing the skid resistance in our roads, because this high grip is possibly creating all these little nasty particles which people are potentially breathing in. Okay, so that's sort of the background to it. Where do we go here? So a bit of a blurb, but some more blurb. So anyway, what did we do? We approached asphalt company. Can we have some SMA 10, please? Standard mix in the UK on our motorways and stuff. We call it thin surface material, but it's basically an SMA 10. Make some slabs, and what we had intended to do was basically run them in this machine. We call it a road test machine. It's 80-odd years old. It was the original machine developed in the UK to test asphalt materials. About 20-odd years ago, it was brought in to test wear. Okay, if you look at the European standard test methods, there is no wear test for asphalt. And if you can start to simulate wear, then you're looking at asphalt evolution and all of these texture-related properties, like skid, noise, roll resistance. And so it was brought in about 15 years ago, 20 years ago, to look at a specific type of surface called high-friction surface. That's a two-part resin system, because it either goes down cold or hot. And you apply calcined bauxite, 3 mil calcined bauxite, and it gives really high levels of skid resistance. It's the top end of anything that's possible from the perspective of a road surface, high-friction surface. And I say, we got the equipment then, and we started basically certifying or accrediting all the high-friction surface materials that were being developed in the UK. And this is a set of tires from testing different materials. Okay, we've got the equipment, we're testing high-friction surface, we've got the highest, grippiest material that's possible to be made to put down on a road surface, and then we've everything else. We've got concrete, we've got limestone aggregates, we've got gritstone aggregates, we've got granite aggregates, we've got porous asphalts, we've got SMAs, all of that stuff. Working with the road industry and product development, we've got access to all of those different aggregate combinations, bitumen combinations, all the things you can think of. And I say this is a set of tires, and I say this is after a 4-day test. This is the top tire there is what a good high-friction surface does to a tire after 4 days testing on this machine. It just really rips it apart. You're right down to the wire carcass in the tire. Down the bottom, that's a relatively low grip, low roll resistance, low noise asphalt surface. Virtually no wear on the tire treads. Now we had to measure tire characteristics, but we never really took it too seriously. We just sort of measured it. And then people started talking about microparticles. And we went back and, okay, we've got a machine here that can potentially pull a tire to pieces over a few days. Okay, and I say that was the background to what we tried to do, and then COVID hit and all the rest of it. Oh, what's happened here? We have a technical. That, get rid of that. This is sort of database that we were measuring. And so this is just simply based on skid resistance, wet skid resistance measured using British pendulum. Still hard to beat a pendulum test. And this is passes. Top line is high friction surface, bottom is a low roll resistance, low noise limestone asphalt. And within that, there's this whole spectrum of potential asphalt materials and aggregate combinations and bitumen combinations that you can think about. So that was our sort of database based on this machine. Okay, we made these slabs. Are they comparable? We did some pendulums, we did some estimated texture depths based on a little Ames machine, and formed this little cluster. So 10 slabs are not too bad in terms of material, in terms of similar. However, coupled with COVID, our university decided to move campus, and that machine has not been operable for a couple of years. So I had to go somewhere else. These are the challenges that a researcher faces. So what about microparticles? What else did we do? How could we do something? So there's our slab, and we had a piece of equipment that we developed a small-scale wear test a good few years ago. And what we did, we put a little ratchet device that a little tire rolled one way across the surface and then was dragged back. And in those days we were looking at, that was a project that was all about warm mix asphalt. Was warm mix as good as hot mix asphalt in terms of wear characteristics? And we found no difference between the two materials. So we went back to that test method. And that's the sample of our SMA10 after about 30 minutes testing. And this sort of simulates what happens in real life. You put in a new asphalt material, the aggregate's all covered in bitumen. You have to get the bitumen off the surface to expose the aggregate. So you have this sort of early life drop in skid resistance as the bitumen polishes, then the bitumen comes off the aggregate. The aggregate is at its maximum in terms of microtexture, and then the microtexture starts to polish. And then depending on the test conditions, mainly load, the surface is down into equilibrium. And if you go out and measure a road, that's what happens. Okay, you have this sort of sequence of events. New road, early life, then a maximum, and then into equilibrium. And they say that's what you can do with this little test in about 4 hours. You can simulate, and again, based on real life data, in about 4 hours, what happens to that SMA10 over a period of years. So how can you measure something from this? And this is all about sort of fairly simple ways of taking data, and as Professor Foy said this morning, thinking sideways. Get rid of these ideas if we have to do things like this. Oh, sorry. That waking everybody up. Something else. Okay, there's our little Ames device. Great little machine. We've been using it a lot the past couple of years. Little laser device, if you don't know what it is. And I say, within the confines of this little slab, 300 by 300, you can put it along the length of the track, you can put it sideways. And then you can sort of, again, just non-standard pendulums you can do now with the small pendulum slider, the wide pendulum slider, and then you can stick on different rubbers onto that and look at the different types of rubber, things that might equivalent closer to a tire, or things that you can pick a rubber to accelerate the whole process of something happening, which is really what you want to do in a quick lab test. So, little tire, backwards and forwards. It's sort of designed around a grip tester tire, if you know what size that is, or, to be a little bit more interesting, go-kart tire. Go-kart tire, small racing tire, made to very high standards, with all sorts of different compounds of rubber in terms of grip. I did a lot of work outside of the university in terms of motorsport. So you get some idea of what a tyre is doing to a surface at all sorts of speeds, braking conditions, turning forces, all that sort of stuff. And this sort of constant moving forward and braking, that's what it does to the tyre. So we're starting to do things to a tyre very, very quickly that you can measure. Little lane set up, very, very crude experiment, but underneath that wooden block or wooden board is the tyre. So run the tyre for a few minutes, stop it, put the laser on, get our little scans, and we're starting to measure things of how these sets of conditions, do they relate to anything to a road? I don't know, maybe not, but you're starting to get an idea of how asphalts and rubber and tyres interact. And from that then, you can then start to think in the bigger picture. Yeah, anybody who's been on a racing track might recognize this. But say on track, you all heard about sort of all these little bits of rubber that come off. And again, when you're testing a very smooth, very soft rubber go-kart tyre, it's very, very similar to what happens with motorbike tyres on a track. You get these little sort of threads of material coming off. There is an Italian term which I can never remember for them, but it's not. It's very, very descriptive, so it is. You can play around with all sorts of different rubbers then, because you can take a wee bit of rubber in the end of the pendulum, or you can take a strip of rubber and stick it onto a tyre. Okay, some of the experiments, we've got this pneumatic tyre. It could be a grip tester tyre, it could be a little go-kart tyre, or in this case, it's a rubber that we have selected to wear really quickly. Okay? Once you start to get a basic test going, you can start to go all sideways with it if you start to think outside the box. So, in the center is that high friction surface material, the highest ever high friction surface we have ever tested in the UK. That is the highest possible that you will ever get. And I say, because it's so good, I kept the samples. Okay? And that's what it does, that little strip of rubber, in 30 seconds. Because we're after the generation of microparticles here. We can't afford to wait 5 years for a road to cause wear on a tire and somehow collect these particles. If you can bring it back to the lab and do a really, really simple, really, really quick test, and play around with all the variables, then you can very, very quickly start to appreciate what's the key factors, what should we really be interested in. So, on the left is the same experiment, only on a smooth, I call it plastic. It's not plastic, it's some other type of poly something. But this sort of shows another phenomena. We've got heat build-up because you've got virtually no texture on that surface. It's perfectly smooth. But yet, look at all the rubber that's on the surface. Okay, so when we go down to really low-textured surfaces, is this what's happening? Okay, in dry conditions, we're getting really, really good skid resistance. But what's happening in terms of this wear or this interface between a tire and a textured surface? One extremely good and the other virtually no macro texture. So, yeah, little comparison of 3 of these little strips. Now, this is a 2-minute test. 2 minutes, that's all it takes. The bottom one there is on that smooth plastic type surface. The one in the middle would be a low rolling resistance type surface, asphalt surface. And the top one is a really good high friction surface. So how can you measure something there? Well, you can take some photographs, you can do all sorts of things. We've got our little Ames laser data. You can set it up to take different profiles. Once you have the profile then, you can bring it into some R software, and you can start determining all these sort of 2D parameters from the profiles. From the center of the little patch that's been scored to the edges, all sorts of things you can start and play around with very, very quickly and very, very simple and very, very easy. And you can pick some of those profiles and some of those parameters. And in this little example, we're just picking a couple of parameters. And at the bottom, we've got our smooth surface. At the top, we've got our high friction surface. And in between those two profiles is everything else in terms of how a tire is going to, how this strip of rubber is going to interact with all sorts of different types of road surface materials. And say this is sort of roughly where we're at the minute with this project. And just trying to think, we're almost finished. So that's in the lab, and then taking it into the field for verification. That's our little strip of rubber on a tire, little grip tester tire. And we ran this experiment on the road. We offset the tire to try and speed up things, and we basically got no tire wear. Nothing happened to the tire. It heated up a bit more. So whatever happens with real tires, remember they're designed to last. And if you're trying to get some idea right pretty quickly in a lab, you have to start playing with your variables. And say this is designed to fail. I would expect, we haven't run this yet, but I would expect we might get 200 or 300 meters out of this tire before it's totally gone. Okay, on my last slide. So in terms of some conclusions, there's a huge amount of interest in these microparticles, certainly back in my country, in the UK. Then everyone's just starting to wake up to it. If you talk to the tire companies, they have all the work done years and years ago. They know where they're at. For me to turn around and say to the asphalt industry in the UK, guys, to reduce tire particles, we're probably going to have to drop skid resistance. That will be accepted with silence. There's nobody interested in doing that. So, from what we've done so far in this, the aggregate, the type of asphalt, and remember I'm coming from the UK where we look at higher skid-resistant aggregates and mixes designed to have high skid resistance, I would predict we are in a bit of a dilemma about the future of tire particles. Or any country who's thinking of trying to increase safety. This is a really serious issue that is indicative of this triangle not being filled in. The road asphalt industry, the tire industry, and the car industry. The bottom two industries are hyper, they won't talk to you. It is really difficult to talk to them. And the road construction industry is, we don't know what's going on. Should we go for lower grip? I don't know. But when you look at what's happened to a car, in terms of braking, computers, intelligent vehicles, everything is saying we don't need grip. We don't need it. We need a little bit, but we don't need as much as what a lot of people have been talking about for years. We need to take these blinkers off and look at this in a totally different way. So, do we know what's actually happening? Absolutely not. And this is why research is still really, really interesting for me, who's coming towards the end of his career. But as I say, stepping back, I've worked with the industry for 40 years. And I have this, like a lot of the more senior people in this room, I have this big holistic appreciation of what the situation is and possibly how we maybe need to start directing ourselves. So, classic conclusion to any research project, more work is required. Thank you very much.
Thank you, David. So we come to the last presentation of this session. It's actually a presentation from Syed Reza Omranian. He is actually a postdoc at the University of Antwerp, but as he is not here, his presentation will be given by Cedric, and the title is the investigation on the influence of titanium dioxide on bitumen performance. So Cedric, you have again the floor.
Thank you. I thought if David can do a reappearance, I can also do it. So here I am again, long time no see. So yeah, it's actually a completely different topic. They put me in this session, but it's not related to road noise. So if you want to leave the room, feel free to do so. I won't take it personally. Titanium dioxide, who knows what it is? Show of hands. Limited. Okay, thank you. So there's a lot of people involved. So as Luc said, Reza is a postdoc. Ali Zain is recently started PhD student. So next time we report on progress, it will be him giving the presentation. And the other people are involved for their different expertise. So titanium dioxide is a nanoparticle that we are interested in because it has photocatalytic efficiency, or it can photodegrade pollutants. I will come back to that. And what I'm presenting today is actually work done by 2 master students in the last 2 years, and which will be then extended now by that PhD student. So nothing too fancy on the menu because, yeah, we're in Portugal with fine food, so let's keep the good menus for the restaurants. So a very simple introduction, what have we done, some results and some future research. So we all know what asphalt pavements are, and that's that there are a lot of them, and that there's a lot of pollution, air pollution. And one of the main contributing factors is road traffic. And of course, the pavements are close to the vehicles. So that's why there's an interest already for, maybe 15 to 20 years in looking for a possibility to photodegrade these pollutants, these gases, NOx, nitric oxides, and so forth, by, for example, titanium dioxide. Why titanium dioxide? It's cheap, it's non-toxic, etc. It's also used in paints, in sunscreen, and many applications. And it has different forms, and this form has shown the best photocatalytic efficiency. Sorry about that word, I will mispronounce it a number of times. What happens actually is the titanium dioxide is hit by UV light. UV light will give chemical energy to the titanium dioxide, and there's a switch of electrons and so forth. Long story short, some radicals, oxides, and so forth, hydroxyls are created, and they can then degrade and convert the pollutants, the exhaust gas, in something less dangerous or harmful for the environment. That's the basic principle. And it has been shown in literature that it works. I also have some doubts here and there, but let's keep that for another time. So there have been many tests around Europe and the world, not only applying it on pavements, but we are from a pavement research group, so we will focus on the pavement. Also in Belgium it has been tried on bricks in concrete. Very good lab results, on the road so-so. And yeah, worldwide, China, Italy, Japan, you see them mentioned here. So why did we start with this? Actually, because of Elisabete and Iran. Is Iran somewhere here? Yeah, over there. A visiting researcher who came to Antwerp a couple of years ago, and that's when we started looking at titanium dioxide. But as I said, we are asphalt and bitumen researchers, so we have been trying to get some good results regarding gas degradation, but we are seeing problems there. So we're going back. We're going to the fundamentals, and we're going to see what happens, what's the interaction on a chemical level, on a rheological level, when you start mixing or using titanium dioxide with bitumen. Sorry for people who are interested in road noise, it's different here. So we are using a standard bitumen, unmodified. For rheology, we use the DSR testing, and for the other analysis, microscopy, we use very thin film samples. The titanium dioxide is a commercial available type of Evonik. and it's nanomaterials, so it has a size around 25 nanometers. What are we going to focus on? Mixing process. If you mix the titanium dioxide with the bitumen, low shear, high shear, percentage, what happens? Yeah, we are mostly material engineers, researchers, so we focus on the rheology. Is there an effect? Is it a beneficial effect? Like, is it an effect on aging, for example? Or, as I said, it reacts with UV energy, so maybe that means that the possible harmful effects of UV will no longer affect your bitumen, but will play with your titanium dioxide instead of your bitumen. So let's see if it has an effect there. And also something we investigate quite recently is the microstructure, micrometer, nanometer scale of the binder. So the mixing process, we use a high shear mixture, but we can also do low shear, and we went from 0% to 4% of the binder weight in addition of titanium dioxide. Rheology is done by the dynamic shear rheometer, which is shown here. There we investigate a temperature range of 0 to 80 degrees in steps of 10 degrees. Aging is also investigated. You might know that, but aging on the road happens because of a number of instances: elevated temperature, of course, the loading of the vehicles, and a very important one is UV light. And we are focusing mostly on UV aging, but before that, we want to bring the asphalt and the binder into the preliminary state. And that's what you do with short-term aging. This simulates the installation process, and then it's on the road. That's the aging state we do first, and then we put it under UV light in a so-called weatherometer. That's extreme UV, 60 watt per square meter, so it's not what you have normal situation. And then we analyze what happens with the binder and the modified binder with chemical analysis, the Fourier transform infrared spectroscopy, and confocal laser scanning microscopy to see what happens on the surface of the binder. A lot of samples were tested. I'm not going to explain all this table, but you see the influence of the mixing process, low versus high shear, different percentages, short-term aging, and then we have a lot of subsamples that we then age further in steps of 8 hours of UV aging, and all of them were tested for some of them were tested for rheology, and all of them were tested with Fourier transform infrared and CLSM. A lot of results, I'm not going to show all of them, and we still need a lot of work to repeat and improve our work on this matters effect. So, main conclusions, let's say. When we look at rheology, that's of course one of the most important parameters to see if it has an effect on your mechanical performance of your asphalt. We want to avoid that, of course. And we see no effect when we mix the binder with titanium dioxide. Has no effect on the rheology. I'm not going to go into detail because I don't expect all of you interested. If you want to know more, we can discuss about it later. And also after partial UV aging. This has also been done at a lower setting of the UV aging. I expect if we would repeat this with the samples with the 60 watt per square meters, we would see a change in the behavior here as well, because the binder itself becomes very brittle, as you will see in the microscopy images. Some explanation about F-tier results. So that gives you an idea about the chemical composition, and you can use that, for example, to track the presence of your titanium dioxide. So you have your reference samples. We always did 4 replicates and a number of repeated measurements. That's 0% titanium dioxide, and this region will change when you start adding 2 or 4% titanium dioxide. The difference of the 2 lines is low shear or high shear mixing. And then when we start aging them, UV aging, or this is already short-term aged, we can start looking at specific bands in this spectrum. One of them is so-called the sulfoxide index. That's the reaction with between the oxides and sulfur. and with the carbonyl index. And those two are regularly used to track aging in binders. And so we want to see if there's a difference between an unmodified and a titanium dioxide modified binder. So these two is what I'm going to focus on right now. So when you go from the unaged state, the different colors are the reference, low shear, high shear, and with 0 to 4% of titanium dioxide. When you do short-term aging, almost nothing changes in this index. And when you start applying longer periods of UV aging, you clearly see an indication of aging shown by this increase in carbonyl index. Similar for sulfoxide, but less impact of UV aging. Of course, the standardized tests normally do PAV, pressure aging vessel, and they just eliminate, they don't focus on UV aging. And we believe that UV aging is also a very important one. But which is something that we really need to investigate further, is when you focus on this one here, you could say the blue and yellow one, those are the references, and you see that they clearly have a higher level than the ones with titanium dioxide. So this could mean that your titanium dioxide is somehow shielding your bitumen from UV aging as a sunscreen protector, but we need to confirm these results. Then some microscopy images, not going into too much detail there because it's very specific and I'm also not an expert on interpreting them. But what you see here is the verging binder, and then each time you add more aging. And as I said, the UV was extreme, the amount of UV, so you really see the appearance of large cracks and a very brittle surface. And so that's not what you normally hopefully will get on a real road surface. But it's accelerated and exaggerated aging. But you see clear structures appearing on the surface of your binder, and by counting them, you can also say something then about the aging state and compare it with the titanium modified samples. Mixing process, we could see that the titanium dioxide seems evenly distributed, which is already good. Maybe a little bit better with the high shear mixing than low shear, but we need to confirm again these results. Problem with microscopy is always that you're looking at really small scales. So this is 10 micrometer, but we should even go to nanometer scale. Okay, almost at the end. So what some of my colleagues really work on is so-called bees. He's not a beekeeper, but that's a phenomena that you see at microscopy images of some binders, that you have a pattern of white and black stripes, which looks a bit like the colors of a bee. And by tracking those bees, you can also relate them to the aging state. They will increase in size and decrease in number normally when they become older, when it's aged. And we see the same when we add the titanium dioxide. The size decreases and the number increases, so it means that it's less aged. So it kind of confirms what we see with the FT results, but we need to repeat again measurements. Why? Because it's all thin film, and if you reheat it, you're losing your information. It's really difficult to track this aging process in all the test results. But that's the work that my PhD student is doing at the moment. Most importantly for now is there's no impact on rheological behavior, otherwise that would have maybe already been a red flag. Might have a good effect on aging and act as a sunscreen, but we need to confirm that. And also the microscopy images confirm this hypothesis, but needs to be analyzed further. So we are repeating this aging study with better control of all the samples and an improved method to create those thin films, and especially to go from these thin films to the actual tests under a microscope, for example. And what we're also doing then, of course, is analyzing the gas degradation tests. And I just want to mention this is one graph that I'm showing here. And this might explain to me why it's not successful yet, or that there are still huge questions about the practical use of this on a real road surface. What you see is the gas degradation from nitric oxides, and they really show very nice results when you apply it on the aggregate or on a glass sample. Intermediate when it's on an asphalt mixture, but when it's on bitumen, it's really nothing. And we think it's related to procedures that you have to implement before the test, sinking of the titanium in the bitumen, or that it's reacting with VOCs, but that's for future talks. Okay, that's it for me. Thank you. These are the references, and these are our contact information if you would be interested in this topic. Thank you.
Thank you very much, Cedric. This concludes the presentation. So we are a little bit in delay, but we still have time for some questions. So is there anyone in the room who has a question to one of the speakers? No? Yes, Gaetano? Made the microphone.
Sì. Question is to Cedric, because we did some experiment, some work on mechanical impedance, and obviously we find similar results about the uncertainty related with the repetition, the repeatability. And we develop a system that permit to do automatically because that was one of the most important points. I don't know if you didn't present for reason of time this part, because theoretically it's not dependent, the force is force, but you change the position of the hammer respect to the, so this change the reaction. So I don't know if you want to comment this.
Thank you. No, I have read your paper. And I think that indeed it shows that some variability is removed by doing this procedure. But yeah, I must be honest, we have given up a little bit on mechanical impedance for the moment. So Belenia was working on it, and we got so disappointing results, and it was not really her main focus of her PhD. So what I presented to you is maybe 1 year old and predates the work that you and your group have been doing on the topic. So we haven't tried seeing if your setup would give an improvement for our results.
Other questions?
Yeah, my question is basically on the effects of titanium dioxide on, if you're breathing it, it's not good for your health. So is there any consideration taken into that?
I guess you mean because it's a nanoparticle. Yeah. No, we haven't looked at that, and yeah, we're for sure not the first one to investigate this. But yeah, it's always considered as a non-toxic component, which is used in the food industry as well. Recently there have been some minor upsets, so maybe it will no longer be available, but no, we have not checked if and how those nanoparticles would be emitted in the environment. And for the study that I just presented, when it's mixed in the binder, yeah, there's no risk. And of course, when we are mixing it, we are all using an FP2 mask like we all were accustomed to do for corona. Yeah. So it is a risk, of course, because it's a nanoparticle, but I cannot comment on how much is emitted to the environment when you would apply it. I cannot comment on that. But it's a concern, of course.
Thank you very much. Other questions? Yes.
Thank you. I have a question for Caetano. It's also related with photocatalysis. You mentioned that, if I understood well, that you have field experiment. Can you talk a little bit about that?
I cannot say more about the point. I know that the University of Cantabria did some tests for that. You know that I can come back about the TO2, or titanium oxide. There was a sentence of the European Court in December 2022, against the position of the European Commission that blocked the use of TO2. Because there was problems for the food. Now, this sentence put again the point on the table. So there is some for the TO2 application. What I read in the past was that there were 2 European projects about the use of photocatalytic in a real environment. The first one was a live project that produced good results, but after there was another that showed that you need a lot of surface to obtain some results. So this is the most important limitation for the use.
Other questions? I have actually a question myself for Gaetano about this VTEC, thin asphalt layer in Florence. So the initial noise reduction was quite spectacular, but you use a 4 millimeter aggregate. So are you not afraid that the noise reduction will soon disappear?
Yes, this is one of the points. We plan to repeat the measurements during the project, so after 1 year, and after there is the idea of the municipality of Florence to repeat in the time. Also, you have to consider that the traffic there is, as I said this during the presentation, is not so high. We are in urban area with reduced speed, so this could be helpful for that. But sure, the durability is a key.
There come lots of people to Florence. That's
moment we are doing other European projects in Florence. Particularly, we just finished the EVIA live project with the use of rubber asphalts, and now we are doing another live project with Filippo and SNEC live project and NIMO. So it's like a lab. In this period, we have the opportunity in Florence to do this kind of measurements, and also we did CPX measurements in all these surfaces. We will continue in the time. So this could be useful maybe also for the durability of the system.
Are there more questions? I think as we are a little bit delay, we should conclude here. Thank you once again to all the speakers, and thank you for your questions. And see you after the break for another very interesting session about rolling resistance.
So you were local, right?
Sorry?
You guys are local, right? Do you
I'm
know
not
the-
local, but
yeah, not local.
I work
Do you
here.
know that there's a website I can access to get to internet?
You should have.
Originally it
access.
cost Sibo or something, but I did not see that at all. So
Some people is
Yeah.
having trouble, but
Yeah.
it worked yesterday because we have the
Oh, I
meeting
see.
here and the password was the same.
For example, if you look at the
Yes, I'll show you.
sure.
It's this one.
Yeah. So but Wi-Fi Sibo is this available here or
Because you should come
see
to
that, right?
Eduroam. You go into Eduroam and then you
Oh,
put.
and type that one. Okay, got it.
Okay.
See.
Tem que remover esse daqui. Não tem espaço, né?
Não, isto é do apontador.
Daqui.
Se não puseres o apontador, não.
Vou conferir a minha se está tudo ok.
Copia logo na mão que gera a tua página.
Qual é a dela aqui?
Tem que abrir o pendrive dela.
Tá aqui já. PFDM. Deve ser esse daqui.
Aí
Amanda? Amanda?
Copia com o número 5, que eu acho que ela é a última.
Tem certeza se é esse aí, né?
Acho que é.
Essa daqui? Então, essa daí.
Já tem. Ah, que vai substituir, né?
This is the old time.
É isso, né?
No, that's not correct time.
Eu já tô pendrive só pra mim. Esqueci. É esse, não?
Okay, do that.
O mouse.
Do I
Esse
have
aqui é daqui.
some time so we can go through the inception, right?
Vamos olhar agora.
I do. I have it actually. So what you want me to do only for this session, right?
Yeah, yes. Because in this session there
Yes,
almost
yes.
all are young. So
For my session, yeah. So I will just give them a rating. I can do it later on tonight, if I take notes, or I have to do it right away.
if you do right away, it's done. So you can open the link. Just your name, so like the
For order 1, 2, 3, 4, 5, right? Everybody's here.
I just
Ela está no
mentioned
baú,
because it could have
que é para
some
apresentar.
changes, sometimes it happens. It's number
Oh, yeah.
1, number 2, number 3, number 4.
Okay.
Vê se... Ah, tranquilo? Obrigado. Não, sou bem o terceiro.
Já sabe, né?
Foi, né? Tá.
Okay, that's all. No, just to get down to that.
Yeah, yeah. He's such a good friend. Huh?
You can get a suntan with these lights here. You want to start? Good afternoon. My name is Camille Kalouche. I'm a professor at Arizona State University, and I'll be the moderator for this session on rolling resistance. Our first talk is our invited lecturer, Luc Gobert. Luc Gobert has a PhD in atomic and molecular science or physics from Ghent State University in Belgium, and he followed a postgraduate course in acoustics. In 2001, he became a research scientist at the Belgian Road Research Center, where he is in charge of the surface characteristics noise marking laboratory. He is an active member of the ISO and CEN work groups on noise and surface characteristics. He is conducting research into low noise road surfacing, the influence of texture on skid resistance, rolling resistance, and noise, as well as on measurement methods. In the last 10 years, he has been active as a participant or leader in 10 national and international research projects. Please welcome Luc to the podium.
Thank you very much for this kind introduction, and thank you very much for the invitation to give this keynote lecture. So I will speak about rolling resistance, so let me have this half hour to show you a little bit more about the wonderful world of measuring rolling resistance. Overview of my presentation. First of all, it has already been addressed. Maybe I can go quite quickly about that, but it's sometimes, I would rather say often, there is some confusion about what rolling resistance actually is, and sometimes it's confused with skid resistance. I will quickly go over that. And then I will speak about the trailer method. This will be the main part of my presentation. But there are also some other methods. It's also interesting to compare the trailer method with other methods. I will give you some practical examples because we also used these other methods. There are some interesting developments in Europe going on in the field of rolling resistance, and I will briefly address these as well, and I will finish with some outlook, what I see for the near future. First of all, rolling resistance, we can define it as a force which is needed to keep an object rolling. In this case, a wheel, a tire rolling over the surface. The essential difference with skid resistance is that skid resistance is about sliding of an object over a surface. So We want to have our rolling resistance as low as possible, as you will understand, and our skid resistance force as high as possible, or high enough. So that is an essential difference between the two. So the main origin of the rolling resistance force is actually the deformation of the tire, and there are some hysteresis losses in the rubber of the tire, which dissipates energy. Therefore, we need, we have this, we don't need it, but we have this rolling resistance force. And this force is influenced by the road surface and by the tire itself, of course. But as road people, we can only influence the properties of the road, of course. So why do we bother about it? Several reasons, but the most important one is this CO2 emission and this climate change, which is going on and more and more quickly. So we, as a road, as transportation, we are about responsible for 1/3 of the global of the CO2 emission, and the road surface takes about 1/5 of the total emission. So that's huge. And of course, there are some measures projected, and it is foreseen that this emission will go down. Everything goes quite slowly. And it's very welcome to have some extra measures, and the reducing of the rolling resistance of roads could be one of those extra measures to go and to make it, the curve dive a little bit further. I don't think that's a luxury to make it go down a bit earlier. So, a vehicle moving consumes energy, and there is a lot of losses, and the main three are the vehicle propulsion resistance, so losses in the engine. You have the aerodynamic losses. So for cars, this is not very high. For trucks, it's quite important. And you have also the vehicle rolling resistance, only one, which can be subdivided in other contributions, but we are only dealing with this tire rolling resistance, which is quite an important contribution. So actually, we are at BRRC have been pioneering on the study of rolling resistance, but the initial motivation was actually not the CO2 emission. It was actually the shortage of fuel. I'm old enough to vaguely remember that we had some car-free Sundays in 1973. So that was a problem with the oil-producing countries who were fed up of giving their oil for almost nothing. So they started to reduce the oil production, and then the Western economies, they reacted and were actually shocked. That was the first motivation. So, and due to this, my former colleague, Guy Descornet, he actually got a task from his superiors to say, well, have a look at this rolling resistance of this road surfaces which we have in Belgium. And he was a very bright and creative guy, and he developed this rolling resistance trailer to study the rolling resistance of road surfaces and to compare them with each other. So the design was actually the quarter of a car, that with a suspension and with a load which was representative for the cars of that time. I come back to that. Initially, a bit strange choice was that he equipped it with the PRC slick tire. He said, well, that was to eliminate the influence of the tire tread. Yeah, but that's true, but of course it's not very representative. So we came back to that later. So he actually developed a special design for this car, for this trailer. And actually what he did was he he pulled on the trailer on the end of a metal bar which was connected with the axle of the test wheel, and he put the charge load on this pulling bar. And then by the rolling resistance force R, you have an inclination of this bar. So this makes an inclination with the vertical force, and this we call theta. And this load, this makes that there is a vertical force, and the rolling resistance coefficient is actually the rolling resistance force divided by the load. And it's very easy to see that the tangents of theta is actually R divided by Fz, and if theta is expressed in radians, and as it is a very small angle, you can simply approximate tangents theta by theta. So he did some initial measurements in the beginning of the 1980s, and he measured on some common asphalt surfaces, on some common concrete surfaces, but he also measured on perfectly smooth surface and epoxy, and also on cobblestone, our famous Belgian cobblestones. On the extremes, he had actually 100% difference of rolling resistance coefficient, but of course between the normal pavement of that time, the difference was smaller. Come directly to the big problem with this kind of measurement. So the rolling resistance, typical rolling resistance coefficient for a typical road surface is around 1% to 0.01. This is a half a degree. So, and if you, of course, you want to compare different surfaces, you have to have a precision which is much better than that. Say maybe 1% of this magnitude, and so then you need a precision of about 0.0001 radians, and that's 20 arcus seconds. This is indicating that you need actually a high precision instrument. And the trouble is that you have a lot of influences that you don't want, but that you measure and that are added up with this theta. What you are measuring when you're driving around with this trailer, you have two important influences, and one is related to the attachment of the trailer to the trailing vehicle, and this is this alpha. This alpha is an important parameter, and it depends. It changes quickly. For instance, it makes a difference for your measurements when there is one person or two persons in the car, and even if you're driving sometime, the car consumes fuel, and the fuel level goes down, so the weight of the car changes, and then also alpha changes. So this is a parameter that has to be measured and has to be monitored very well. A second one is the slope of the road. If the slope of the road is also added to as an artificial rolling resistance, so that's also, you have to monitor and measure that and monitor that and also correct for the slope. There are some other disturbing influences. Very critical is as well the acceleration. So an inertial force, when you accelerate with the trailing vehicle, the towing vehicle, you have an artificial rolling resistance. Air temperature, if you don't master that very well, then you cannot make any reproducible results. The tire inflation pressure, of course, a tire which is a bit more or less pressure, it makes a difference. And also the air drag, which is especially annoying and ruining the measurements at higher speeds. At lower speeds, it's less important. At higher speeds, you see the influence of the air drag, which is not nice. There are some other parameters influencing, but which are much less critical. So the alignment of the wheel with this layout, with this design of the trailer, it's not very important. The tire load is not very critical either. So I come back to that. and the vehicle speed, so it doesn't matter if you are a few kilometers an hour faster or less than the target speed, so that is not very critical. So this is our trailer in 2023. It's still running, but there are some shortcomings. We can only, due to its huge age, it's 40 years old. So when Guy Desconnet designed it, the cars had narrower tires, and it's only possible to mount the reference tire H1, so the Avon tire on it, which is a bit narrower than the P1, the SRTT tire, which is just too wide to mount it in the design. So the wheel load is only 250 kilograms, which was okay for cars in the 1970s. The cars were much lighter at that time. Now the cars are typical, much heavier, 50% heavier. They were around 800 to 1,000 kilograms. Now they are easily 1,500 and up. So in the Rosanne draft specification, there was foreseen to have a load on the wheel of about 400 kilograms. The Polish colleagues of the Technical University of Gdansk, now it's called the Gdansk University of Technology, they have actually copied the idea of Guy, and they built their own trailers. They actually own 2 of them now, and they have, I must say, improved it. They have foreseen it with by the supporting wheels, and this is to eliminate this influence of alpha. So they are a bit more comfortable for measuring, so they don't have to bother too much about this alpha. They have actually done some nice innovations. They have some automatic compensation for the slope and acceleration, and this is by adding a counterweight, so that is automatically compensating. They have also, of course, made it possible in their trailer to mount the Avon and the P1 tire, and they have foreseen a 400 kilogram wheel load, which is more representative for modern cars. They have also sophisticated calibration procedures. So there are also other trailers which are based on another principle, namely simply you make a trailer and you add a dynamometer between at the towing bar, and then you just simply measure directly the towing force, so the rolling resistance force. And actually, in principle, it should work. It's even more sensitive to acceleration, but in principle, it should work. We have we still have it, a trailer which is based on this principle, but it was a student work. So it was a good job, but actually not very durable, not very strong, so we put it out of service. There was one with the German colleagues of BAST was based on this principle, and also some contractor, Colas, had a trailer based on that principle. There was a European project some time ago, Rosanne, and we held a round-robin test with the different trailers in Nantes, so in 2015, and it was a little bit a disaster, I must say. The comparability, reproducibility, especially when we look at the results for the SRTT tire, so the results are going always. That was not very comforting, actually, but as I said, we cannot, our trailer could not mount the Avon tire, so the SRTT tire, so we are not in this graph. But when we did the test with the Avon tire, then we saw that our angle-based trailer and the participating Polish trailer, we had very, very good agreement between our results, but the other ones were also a little bit, I can say it because the other trailers have been put out of service as far as I know. So we have tested repeatability and the intraday repeatability of the different participants. So from the BRC trailer and from the TUG trailer is around 2%, which is good and much better than the other ones. A problem was the day-to-day repeatability. So for the Polish guys, this was less than 4%, which is quite acceptable. For ours, it was 7%. So that was something, some scope for improvement. Actually, we have been enthusiastic about the subject, and we have been designing a new trailer, but because ours is, as I told you, 40 years old, so we have designed a new trailer foreseen from all the new stuff. And that was looking quite nice, but that then came COVID, and that was only, we have only the blueprints, and that costed already quite some money. And then for the realization of the thing is another 200,000 euros. So the Director General said, better to wait a little bit in these times of crisis. So we went for another option, that is for a refurbishment for the time being of our old trailer. So we had to remove the rust of it, and we renewed all the electronics and the sensors. And the thing is that we are actually doing now. So we tested it with the Avon tire, with this new sensor, which is giving satisfactory results. But what we are doing right now is actually adapt it, which is luckily possible, to mount this SRTT tire. A further step should be actually to allow a higher load, which is possible. But actually, it's not that critical, as I showed you. Maybe actually we could do reliable and good representative results also with a load of 250 kilograms. So we are also working on this indoor calibration procedures, a bit inspired by our Polish colleagues. An example of the use of our trailer is that we are studying a new kind of low noise concrete treatment surface, where we have the Flemish authorities, they made two test tracks. It's actually grinding and grooving with a certain pattern, in a longitudinal pattern in the old concrete, because this is old concrete, but by grinding and grooving it in a certain pattern, you can actually reduce enormously the noise, but that's actually for some other session. But we're also very curious what it would do, this grinding and grooving with the rolling resistance. So we went there and did some measurements, but still with the Avon tire. But anyway, we saw some interesting results. You see here the adjacent old concrete surface. Then we see the profile number 1, and you see a clear reduction. You see the bars are per 20 meters because it averages the rolling resistance coefficient per 20 meters. And you see, especially for profile 1, a neat reduction of the rolling resistance, which is nice. It combines the rolling resistance reduction with the noise reduction. And this is here, the profile 2 was less successful, and these are the other ones, the other adjacent concrete surface, which is much higher rolling resistance coefficient, and this is, as a reference, an SMA surface. So that's not a bad result. And actually, we see that at 50 kilometers an hour, we had a reduction for profile 1 of about 7% with respect to the concrete slabs which were adjacent, and also with respect to the SMA. You see that at 80 kilometers an hour, you have only 5.5%, and this is not that in reality, this rolling resistance coefficient would drop so much, but it's due to this air drag, which is very hard to avoid at higher speeds. So the most reliable result here is this minus 7%. But of course, it is measured with the Avon tire, which is less sensitive to texture. So we expect when we would measure with the SRTT tire that we would get a larger reduction. Some other methods, a coast-down method is possible. Fuel consumption measurement is in principle possible, and drum method, I can go a bit quicker because this drum method has been mentioned already today. So for an overview, I take some time to make some publicity for this. There is a chapter in this book, and we describe the all kinds of monitoring of measuring of road surfaces, but there is also some paragraph about the all these different rolling resistance measurements. We also have a publication from some colleagues of mine who compared in an objective way, of course, the different methods, and you see that actually the trailer methods has quite some advantages. With respect to the drum, I think a drum is also very interesting methods, because we also have used it, as I will show you, but there are some difficulties, and not in the least is the cost of the equipment of the drum is a huge investment. The trailer is not cheap either, as I told you, but the drum is a very high investment. So an example of a coast down experiment that we have done, sometimes you cannot do it elsewhere because that in the European projects we developed together with some major tire manufacturer new tires with the lower rolling resistance, and these were tires for trucks, and we don't have a trailer for trucks, so we had to make coast down measurements in this case. With we equipped two identical tractors of truck tractors with six tires with the reference and 6 tires with the experimental tires. Then we let them. We selected a road which was very straight and very homogeneous, and then we let the trucks accelerate to the starting line, and then at the starting line they pushed the clutch, the driver, and then they let them coast down until the next the line, which was 500 meters further, and they measured, they noted the speeds at the beginning and at the end, and from that we could measure the force which is actually was slowing them down. But of course the main force was the aerodynamic. So this is the results. We had to do it 60 times. We were a whole day busy with one experiment, and this is the force that slowed down the truck, and you see there is some difference. The difference was 63 Newton, and this was due to the difference of the tires. So this difference was significant, but very small to the other origins, the other sources. Drum measurements, we had also used this one. We had a project about this NGCS, and we had actually we don't have an own drum. This is another drum of the Technical University of Dansk. It's not the one that has been shown earlier, because this one is with a diameter of 2 meters. And we did an experiment with 6 tires and 3 speeds. And the idea was actually to optimize this NGCS. The NGCS that I told you had did very good results, very good noise results, but also very good rolling resistance results. The idea was we will try and find an NGCS pattern, grooves and grindings, which is giving either a lower noise and lower rolling resistance. So the idea, what we did, we took as a starting point the good profile number 1 that I showed you. We approximated that with 2 sinus functions, and then we started to play with these sinus functions, and we made 7 or 8 different variations of that, and then we tested them on the drum. And well, actually what we found out was not exactly what we liked to find, but the original one, the profile one, this is with the SRTT tire, this is with the Avon tire and so on. And these are the measurement with all the different surfaces. And what you see that for each tire, that you see that the profile one was actually the best. That was also the case for noise reduction, but also the case for rolling resistance. Of course, we would have liked to find a better variant, but that's how it is. So that was an interesting result that we obtained on this drum. Okay, that is how it works. So there are some interesting things going on outside, elsewhere in Europe. For instance, our Swedish colleagues, they have made an adaptation of an existing device. So everyone, not only we have to be creative to save money, but they have also been creative and adapted actually an existing device which is actually designed for measuring steering and brake forces. Braking forces on asphalt, dry and wet, and on icy roads. Is actually a device with a wheel that you can put under a certain angle, or you can put it aligned with a surface that you can pass here under the speed of 30 kilometers an hour. And you can measure the force on that wheel. So if you align this wheel with the motion direction of this underlying surface that you move, then you can actually measure the rolling resistance if you measure it precisely enough. And so that's what the Swedish colleagues did. I think it's a very interesting development, and this is the contact person if you want to know more about it. So in France, our colleagues of Université Gustave Eiffel, they're also working on that. They're working on the development of low resistance asphalt together with Danish colleagues of the Danish Road Directorate. They are also developing a model. And they have also a measuring system. This one is based on, actually integrated into a vehicle. For the time being, it's a vehicle with a classical internal combustion car, and this is still already working, but they are also working on integrating this measuring system in an electric vehicle. So it's also interesting. Veronique can tell you all about it. They have actually also working to see if they can have an idea about the rolling resistance with their Wiener-Schulz device, which is actually some, how would I say, special idea. So, but maybe if it's actually meant for polishing and for measuring the skid resistance. But if you measure the torque on this device with the three rubber cones, maybe you can have some idea about the rolling resistance. It's worthwhile to find out. And then you have in Austria also, they have also been creative there. They have a project to measure the rolling resistance of pavements on motorways. So they adapted actually a device which was devised also for skid resistance, the Roadstar, for the longitudinal friction coefficient. So they, instead of braking the wheel, they let it run freely and they measure the force on it, and according to them, they can measure the rolling resistance force with enough precision. That's, I think, the challenge. Anyway, I look forward to make a comparison of these alternative methods from the French and Austrian and other colleagues with our trailer and see how precise we can measure. I have maybe the relation rolling resistance coefficient actually doesn't interest us. What us interests us is the reduction of fuel consumption. And actually, when Guy Desconnet did some studies about it, and he found out that the difference of fuel consumption equals a difference of the rolling resistance coefficient divided by 5. But in more modern model, they say that the difference of fuel consumption is the difference of rolling resistance coefficients divided by 3, which might make sense because the cars have been much more fuel efficient since the time of Guy, and maybe it's quite right that now you have to divide by 3, but it's interesting. To finish the outlook, I think rolling resistance of pavements will be very important and relevant, and CO2 emission is very relevant, as I don't have to explain you anymore, and the energy will be expensive and scarce, so we will have to be quite energy saving. Even for electric car fleets, it's relevant. You can, by reducing the distance of your pavement, you can extend the range of electric cars, which is interesting. And also you have a higher saving potential because the well-to-wheel efficiency for internal combustion vehicles is about 30%, both for diesel and for petrol cars, but for electric vehicles, that's around 80 to 95%. So I think that we can, for instance, if you have some small changes in the rolling resistance coefficient, you can have a higher saving of energy, even if it's electric energy, but that's also relevant because we will also have to be careful with our electric energy. It has to come from somewhere. About the measuring, I see some renewed interest in the rolling resistance measurement in Europe. Measurements are very delicate, as I try to explain you, and the rolling resistance seems to correlate very well with texture, and some very important thing which has not been mentioned today is the tire enveloping, which makes it even better correlate. And I think that the actual future is not that we will go running around, driving around with these delicate measurement instruments over the networks in Europe, but that we actually, with these trailers and other methods, we will develop a reliable method, as already told earlier today, with machine learning and artificial intelligence. We can predict very well from a texture the rolling resistance, and then we can simply by measure on an easy and fast and cheap way the texture, and then we can predict very well the rolling resistance. Maybe to conclude, there is actually a Miriam platform which has been active already for years, and since it's actually a platform where people who are working on rolling resistance and interested in rolling resistance meet on basis. There is no funding, it's an own funded initiative. It has been led by the Danish colleagues, but I have handed over the lead to my colleague Anneleen Berhiers. There is a one time per year meeting online or in conjunction with the conference. There is a website that will be online soon, and if you wish to participate, you're always free to join and then send me or her a mail. I thank you for your attention.
Thank you, Luke, for a very interesting and informative presentation. I'm sure we're going to have a few questions toward the end of the session. We will have 5 more presentations, shorter presentation, 15 minutes each. We'll start with Manuela Genesel, and she will talk about the laboratory testing or new laboratory testing for assessing rolling resistance.
Good afternoon. I am Manuela Genesou, and I am pleased to have the opportunity to present our research work in collaboration with Fage company. The work revolves around the rolling resistance, a new laboratory test method for assessing rolling resistance to optimize pavement mixtures. In France, road infrastructure contributes to 54% of carbon emission, and we can reduce this emission through innovative road construction methods, and majority of infrastructure emission came from usage of the infrastructure. And roller resistance affects fuel consumption and greenhouse gas emission, account for 20 or 30% of vehicle resistance. By studying and addressing roller resistance, we can improve energy efficiency and make transportation infrastructure more sustainable. Rolling resistance originates from energy dissipation due to the deformation of the rubber of the tire in contact with the surface pavement. It is defined as the energy loss per distance traveled by the vehicle, and there are three physical phenomena that can impact the roller resistance. That can explain roller resistance. Deformation of the tire on the tire road contact area, aerodynamic drag on the rotated tire, and the slip between tire tread and the pavement surface. Roller resistance measurement can be realized with different methods. Cost down method, fuel consumption method, steady state wheel torque method. And here we have I present just two in situ and laboratory methods with trailers. And we have the advantage measurement directly on the network, study on the effect on road surface type, speed and tire, and you have also the drawbacks because the in situ trailer, it depends on the environment condition and the time consuming, and is very expensive also. The laboratory methods, we have advantage like a controlled environment, time efficient and cost effective in the long run. And drawbacks, lack of analysis on the impact of road pavement texture, because here we have the drum, and it not represents the surface of the pavement, so you can't measure the impact of the macro texture on the roller resistance. And also it's a limited range of the test condition. About the influence factors, energy dissipation occurs when tire dynamically deform on road surface. So asphalt concrete with different surface characteristics affect roller resistance by dissipating varying amount of energy upon contact with the tire. The roller resistance can be impacted by the rubber temperature, tire pressure, the load, the speed, and the torque, and this is the factor about the vehicle. And you have also a factor about the linkage with the pavement, the roughness, the texture, and the stiffness. And here we show the roller resistance measurement on the road section at a speed of 8 kilometer/hour. So these measurements were obtained using the trailer from Technical University of Gdansk. So a linear regression line can be used to approximate the relationship between roller resistance and mean profile depth. So the objective of this presentation is propose a laboratory method to measure roller resistance and its application to optimize pavement mix with a particular focus on assessing the effect of macro texture. The University Gustavo Eiffel and the Eiffage company have developed a new laboratory method utilizing the Wiener and Schultz device. So this one, and this machine is originally used to simulate in laboratory the polishing of the road, and also the skid resistance after polishing. So for the roller resistance test, the polish unit of this device, only the polish unit here, is used to calculate the roller resistance of the asphalt mixture. The polish part contains 3 rubber cones mounted on the rotatory head. This cone will rose on the sample that is located in the holder, and the holder is in the measurement base, and you can measure the torque meter during the test. And the cone's contact pressure are similar to the tire contact pressure. During the test, normally, in the polishing test, we use abrasive and the water to simulate the polishing, but in the roller resistance test with this machine, the test was made in dry condition. The rolling of the cone on the specimen surface generate a resistance torque, which is measured by the dynamometer. The torque resistance measurement allows characterizing the rolling resistance of different surfaces. The rubber cones rolls on the specimen surface, measuring the resistance torque to characterize the rolling resistance. The rotating head has fixed weight of 40 kilograms and adjustable speed. The contact pressure is around 0.0 megapascal, and the dry condition used without a water abrasive mix. The test duration is 600 rotation, and each sample is tested 3 times with a 5-minute cooling period. The resistance torque is measured at 1 measurement per second. They calculate the rolling resistance coefficient to use the torque, normal force, and the radius, average the values from the stabilized phase between 400 rotation and 600 rotation. This method focuses on the relationship between rolling resistance and the rolling surface microtrajectory. To validate this methodology, we compared the rolling resistance coefficient measured in the laboratory with those from the trailer method measured in the test track in Nantes in the University Gustavo Eiffel in Nantes. So we compare gaps between different surfaces measured by Werner-Schultz machine method, sample from the test track, and this was compared with trial in situ with the trailer, measured also in the test track in University Gustavo Eiffel. The objective is rank pavement surface based on roller resistance using the 2 methods, so Werner machine and the trailer in situ test. The sample, as I said, is 225 millimeters diameter disc, include different pavements and smooth tile. They were obtained from this test track notes that there are a lot of kinds of surface, 15 kinds of surface different. And this figure compares the normalized coefficient of roller resistance obtained from laboratory and the road test, showing the correlation between roller resistance and MPD, mean profile depth. The results showed the consistent linear dependence, and our procedure explored the effect of the speed, temperature, and surface texture on roller resistance. In this slide, we will discuss the optimization and description of the asphalt mixer tested in the iStrict project. So, 10 mixture was tested, and we considered different variables, such as aggregate from various carriers, or recycled dispersal. Different mix types include dense graded and open graded asphalt mixture. The particle size are ranged from 0.6 and 0.14. For our mixture, we use a Venner machine in the laboratory, and we tested all formula. And also we measured the MPG of each mixture. So here we have our results of MPG. And we used the LA texture machine to access the macro texture. The results showed macro texture values ranging from 0.07 to 1 millimeters and indicate a good surface quality. And the macro texture refers to surface irregularity with specific dimensions. In the optimization of the tested mixture, roller resistance was measured before and after polishing, and revealed no significant differences. So here we show only roller resistance before polishing test. Among 10 tested mixture, roller resistance value showed a potential 15 variation with the highest potential in F3 and F4 mixture. With a roller, the most relevant, most strong roller resistance values, and in the mixture F2 and F4 has the inferior value of roller resistance. Our focus was on tested conduct at 10 RPM, minimize temperature effect, and enable a relevant comparison between laboratory and road results. Each roller resistance test was repeated 3 times per specimen, ensuring repeatability. Average roller resistance values represented the surface resistance. The test asphalt mixture demonstrated varying roller resistance value despite similar macro texture. The chosen test speed and repeated measurement provide reliable and meaningful results. Here, we take the results, optimize polish and the roller resistance. So here we have the curve before, after the test of Venner Schultz machine. So we take the skid resistance value at 180,000 passes of the cone in the Venner Schultz, and we compared with the values of roller resistance. In the curves show initial increase followed by a decrease due to the bitumen removal, so we have a increase of the skid resistance, and after aggregate polishing, so we have a decrease of the skid resistance. Some mixes are ranked by highest friction values in F1 until F6. F6 mixture has lowest values due to grading curves and a lack of small aggregates. And the mixture F1, F4, Bs, and F7 contain many small aggregates, generate a lot of contact points, and this direct loss at the origin of the friction phenomenon. And here we have a cross-evaluation of skid resistance and the roller resistance. And we have the reference mixture F3 has the highest roller resistance value and the intermediate skid resistance, and the mixed F1 and F4Bs has the highest friction value and the intermediate value of roller resistance. To conclude, the new method for measuring roller resistance of pavement surface using a Venner Schultz machine, 15% of reduction in roller resistance of asphalt concrete achieved in a strict project. We have a reduction in roller resistance leads to a decrease in vehicle energy consumption and important environmental impact. And optimize roller resistance asphalt won 2022 roads Industry Innovation Committee, and IFAG University Gustavo Eiffel will carry test seats to evaluate our asphalt mixture under real condition and heavy traffic. And thank you for your attention.
Perfect time. Thank you, Manuela, for interesting contribution to this session. Our next presenter is Iran Segundo, and he will talk about the application of anti-icing solutions on asphalt pavements.
Good afternoon. My name is Iran Rocha Segundo. I am postdoc researcher here at the University of Minho, Portugal. And I'm going to present some results from a master thesis that I had the pleasure to be the co-supervisor. And the subject is the application of anti-ice solutions on asphalt pavements. So nowadays, we are developing two projects. The first one, headed by Professor Joaquim Carneiro from physics, has the main purpose to apply titanium dioxide over the asphalt mixtures to clean the air. And the second one is related to the application of phase change materials to asphalt mixtures to control the temperature and mitigate the urban heating island effect. Thus, our purpose here in the combination of the groups between physics and civil engineering is to functionalize civil engineering materials, providing new capabilities. So this presentation is divided in 4 topics: the introduction with the background, material methods used here in this research, the result and discussion, and the conclusions. A smart concrete is defined as a material that reacts upon a stimulus. This stimulus can be stress, temperature, and light. And this material, the concrete, can be made of cement, Portland, asphalt, and polymer. So just to exemplify, we have 2 of the capabilities in the right side. For example, the superhydrophobicity and the self-cleaning. And the superhydrophobic is related to the repelling of the water over the surface of the material, and the self-cleaning, the clean of the surface by the material by its own. So we know that one of the most dangerous situations for the road conditions is when we have water, ice, or snow over the surface of the pavement. So with this, the friction is highly reduced. And we have a lot of problems because of this situation. For example, we have increase in the road accidents. We have congestions, traffic jams, the increased consumption of fuels, and also the increased air pollution because of this traffic jams. And nowadays, we use techniques to remove the ice over the surface using salt materials, chemical materials, and these materials pollute the environment and also degrade, for example, structures. So we know that it is essential to drain or repel the surface water and ice and snow very quickly. And the main objective of this research is to develop and apply anti-ice solutions using nano microparticles on the asphalt mixtures. For this, we functionalized the asphalt mixture AC10 by spraying coating. The first layer of this coating was composed of a diluted resin, a resin epoxy, with different dilution rates. And the second one composed of the particle solutions. This second solution was composed of Teflon, polytetrafluoroethylene, in 2 scales, and with titanium dioxide nanoparticles. These particles were put in a medium, ethyl alcohol, with different concentrations. And regarding the first layer, we used different resin mass. So the asphalt mixture was evaluated under these three methods, the water contact angle. This one, we place a water drop over the surface and we see the wettability of the material by measuring the contact angle between the water drop and the surface. The second one, we observed the ice formation over the surface of the mixture in very low temperatures, even minus 15 degrees Celsius. And the other one, we used the pull-off test to see the adhesion between the asphalt mixture and the ice in low temperatures as well, minus 15 degrees Celsius. Regarding the results, considering the WCA, water contact angle, almost all the situations presented a higher contact angle than the reference mixture. We have here just two situations. These ones used higher amounts of the resin. This material decreases the water contact angle. Maybe the particles were sinking into this resin, and then we see that maybe it's better to use lower amounts of resin. And we tried to analyze as well different types of different concentration of the particles, and we improved the results more or less. And we see that the best proportion of the diluted resin is 1/3. So the best proportion of the resin, the solvent, and the diluted resin mass to develop the superhydrophobicity is 1/3 and 0.25 grams respectively. And here we see that analyzing the particles, the best situation was using Teflon with this size, the lowest size, with the titanium dioxide 2x2, and the Teflon, titanium dioxide and Teflon, but different size, 1/3x3. We see that in all the situations, the water contact angle was higher. And we achieved superhydrophobicity as well. In the cases that the water contact angle was higher than 150 degrees. So, regarding the freezing time, we see that in general, we delayed the freezing temperature and the freezing time. We see here by the red here increasing for all the situations, and, except for this one, and also the freezing temperature. So by this test, we confirmed that the superhydrophobic coatings delayed the freezing time. We see here that maybe this sample that used, we had a higher impact in the case that we used higher particles, higher sizes of the particles of the Teflon. So regarding the pull-off test, we decreased the strength of the ice over the surface, and the best samples were those 2x2 and 1/3x1 here. So we confirmed that we had a decrease in the strength of the connection between the ice and the pavement. So for the conclusions, the main objective of this work was to develop the anti-icing effects on asphalt mixtures, optimize the process, and we see that the best proportion of resin and solvent in the diluted resin mass to develop the superhydrophobicity is 1/3 and 0.25 grams respectively. The best coating was Teflon and titanium dioxide 2x2, in this case using the lowest size of the Teflon, and also 1 by 3 by 1 using the lowest size and the highest size here. So here we confirm that applying these superhydrophobic coatings, we can delay the freezing time and decrease the strength of the connection between the ice and the pavement. Thank you very much for your attention.
Excellent. Thank you very much. Very interesting work. Next presentation, Chris Tierney, measurements of tire test surface interface using thermal imagery.
Sorry, it's me again. Chris is in Canada and sends his apologies. Would really like to be here. Where are we? Okay. So what can you do with a thermal camera is basically the question. Chris was a part-time PhD student, and Chris moved to Canada with his family just before COVID. Didn't get his PhD finished, and was he had to go to Canada. So basically, we finished off his PhD during COVID via Teams. Chris sat in Canada in his bedroom, and I worked in the lab. And Chris told me what to do, and we basically shared our research together. So that's how we did this piece of work, and this is just part of Chris's PhD. So I'm just going to whiz through this. So Chris was part-time, and Chris he worked through a lot of stuff that we did in the lab over about a 10-year period, and then cherry-picked different ideas and pulled them together. And so the central theme of his PhD was tire surface interaction. How do you measure it? And in the lab, we have a small drum, tiny little drum, it's only about this size. That's our road test machine, which we talked about earlier on. We developed a method to take textured samples off road surfaces. We developed methods to basically take slabs, make slabs in the lab, and then cast circular test specimens. They put in the drum and then look at noise and roll down and all sorts of other things as well. We're doing a lot of contact interface measurements. Pressure pads. There's a slide earlier on where you use photographic film. If you've got a pressure pad, you can basically stand on it. I damaged my right ankle when I was about this height, and that's how I stand, and it sort of shows that I don't stand correctly. We developed methods, grip tester, how does a grip tester contact the surface? And so that's one of our rigid pressure pads. The top there is a more flexible one that you can drape over the surface and load it up under nice controlled conditions and see what happens. Top center is basically a slab of asphalt that we've pulled off our road test machine, which has had so much simulated traffic, and we'll look at how the contact patch changes X years, simulated years into the life of an asphalt. And then so down the bottom, we managed to get hold of scrum tires and so on, and we looked at sort of the different types of interface that the scrum measuring tires, the rolling resistance tires make on different types of surfaces. And I say this particular rig here, you can see the contact patch on the screen. And we also looked at the space between particles, which is something that a lot of people forget about, because we've got the points of contact associated with the texture, but we've also got the space. And somebody mentioned earlier on there about enveloping. And we've done a huge amount of work in enveloping, because that's how the tire goes into that space, or how the little bit of texture pushes up into the rubber. And I say these things, you have to think about it, and part of the work over quite a long period of time was, how do you measure these things? We also did a lot of 3D modeling, and then that worked into 3D printing. And I say we developed methods, take some photographs outside, send some photographs back to the lab, 3D printed, and then do all sorts of things. Or as the work got more and more advanced, we went more simple. And we realized that you have to understand the basics before you can try and understand the complex. And again, as the work developed, we went more and more and more towards simple surfaces, trying to understand those basic principles. And again, this is just sort of some contact patches that we got, looking at how a tire, in this case it's a friction measuring tire, a little grip tester tire, interacts these little ideal spaces. And the image on the left shows there's a very complex contact patch within one of these little simulated blocks of macro texture. And then as you have different orientations of little 3D prints, then that there has a big influence in the contact patch that you're measuring. This paper, as is presentation, is all about sort of what's happening from a thermal context. And again, sort of listen, go and visit in Delft and whatnot and see what they were doing, come back with all sorts of stupid ideas. And basically, our little drum, little grip tester tire, because that's what I've been measuring road surfaces with for over 20 years. I know a lot about road surfaces from the context of that tire, how that interfaces with the surface. But I really don't know a lot about the tire. And you set it up, thermal camera going, and it's really simple to do. But I say, unlike what Kumar was talking about this morning, we just looked on the outside. And I say, if Chris had stayed, we would have tried to go on inside the tire to see what was happening. But in one of our experiments, we just left the experiment going. And as the tire, as the drum, textured surface in the drum slowed down, we picked up this thermal image. And as opposed to looking at sort of, you could say, equilibrium, constant state conditions, this was at the very, very last moments. And this is how the tire was interacting with the textured surface in the drum and basically picking up the texture. So again, tying into what Professor Foy was talking about this morning, think sideways. We have to think about new ways of getting data. Data that comes from the vehicle, comes from the tire, comes from the car, whatever the car is measuring or it's doing. So we had all these different things going on. We had this data from the tire versus this is like an SMA type surface that's been through a couple of years simulated traffic, and it shows the distribution of pressure relating to how the macro texture is changing through the life of the SMA in the laboratory. And again, you could have picked that up out on the road, put the pad down and driven over it. So Chris, the way he was, he disappeared off and he says, okay, let's take this thermal image. What can we do with it? So Chris created a 3D model from it. If you think about it, it's really simple. X and Y, pixel size, you know the size of the image. And Z is your temperature, but Z is your height. So that's your X, your Y, and the Z. So you got a 3D model from a simple thermal image. Our little thermal camera, we could only pick this up at really slow speed. But if you had one of these really expensive, fancy thermal cameras, you could do this in real time at real speed. And again, in other forms of high-speed motoring activities, thermal characteristics of the tire is really, really important in terms of how those tires interact with surfaces and how those vehicles can get around and do the maneuvers that they do. So that was the whole point. So just by accident, we started, we've got 3D data here. And it ties in with a lot of our stuff that we're doing in 3D. And 2D profiles. And say, okay, there's a little blob of macro texture. And that's the profile across it. Okay, you're limited to the pixels and the pixel dimensions and so on, but there's measurements that you can take off that, very, very simple. And one of the things that's sort of talking to simulation people is that they've gone into the nth detail in all of these friction models and interaction models. And what they're doing, they're trying to step back now, and they're trying to figure out what are the key variables. What can we extract from all this data that's being measured that we can measure in real time that actually means something? Okay, and again, we're not saying this is an answer, but it's something that really simple to do. thermal imagery, because a tire sort of heats up depending on what it's driving over. If a tire interacts with a cold surface or a wet surface, bang, you lose the heat immediately. Again, if you ever watch the video when a car is going around a racetrack, you see the extreme changes and rapid changes in tire surface temperatures under those extreme conditions. But the same thing's happening out on the road from measurements that we've taken. So how can we sort of play around with that? Somebody mentioned a grooved and ground, is that correct? Concrete surface. Well, we did a bit of work on that a few years ago, and that's what it's looking like under a thermal camera. We were there trying to figure out these little grinds, do they wear away? And the answer is no, they don't. And that was the basis of our wear testing of that particular product or process. But say there's a little setup on the left, little thermal camera, little sample, and just stand with a hairdryer. And that's how the whole thing glows up. And from that glowing image, you can get a 3D model of the surface. Okay, that's fraught with all sorts of issues and problems and practicalities. So then, okay, let's work on something else. All we need is a very, very little difference between temperatures. That's all we need to pick up this 3D stuff. So we just chilled our samples. A little fridge, just brought them down a little bit colder than an ambient lab. And we set them underneath a little friction tire there. You can see a little sample sitting in the corner. We flicked the tire around, and we got these 3D images, these thermal images of our little ideal samples. Okay? So what? Well, it's what's happening in real life. This is what's happening as a tire goes over a road surface. It's just we can't measure it, or we don't know how to measure it yet. But I say, you have to understand the basics to work in the theories, and then go out and measure it using the way technology is advancing. So we had the temperature, 3D models. We have with all sorts of profile data and measurements of the profiles. Simple things like from this here, 9 little squares. You can work out the areas of them, very, very simple. You can bring together the hypothetical, the CAD type model data, the 3D printed model data, the thermal data. So what you've got, you've got different data sets that you're trying to bring together. And then sort of, again, Chris disappeared off and come back with this idea called co-localization, where you just superimpose one data set on top of the other. And from that then you're starting to look at this sort of hierarchy of different things going on and how they interact. Now, as far as Chris's PhD, that's as far as we got with that. So if somebody is interested in taking it on, please come and talk to me, because I would be really interested to take this piece of work on. So anyway, that's that presentation. So let's rattle through into the next one. I do apologize. I didn't appreciate I was going to do 4 presentations here. Right. So this sort of leads on a wee bit. And this one is a subject area that, if you go through the literature, there is very, very little written about grooved surfaces. Last presentation, really interesting that they were talking about it. But I say, in terms of grooved Marshall asphalt, certainly the airport that I took off in Dublin had grooved Marshall asphalt on the runway. And certainly as you travel a lot, whether you realize it or not, you're taking off and you're landing on grooved asphalt. Okay? So from a practical point of view, how do you measure those grooves? Okay, I'm thinking here the poor contractor. Heavy use on a runway, there's lots of rubber going down. When do you step in to take the rubber off? If you take the rubber off, what damage have you done to the grooves? It's that sort of scenario. And how do you measure things? So this is, again, this is work done by now a PhD student who's just finished, Jason Ferguson. And basically, grooves cut into Marshall asphalt. And we adopted two approaches. We cut different groove profiles into aluminium plates and did a lot of work on those. And then we got Marshall asphalt and cut different groove patterns into the samples. And this is the photograph on the right is the remains of the test samples after we'd simulated a lot of traffic. And the paint there is a very simple way of quantifying enveloping. We've done a lot of work on using paint removal, to look at how a tire interacts with the surface, or a test device, which gives you some idea of what you're measuring. Where are we at? So back to the road machine, and there's a subtle sample sitting on the machine. One of the things we heard a lot about through pendulum testing at the start, just using paint removal, different groove patterns, whether you have the grooves perpendicular or whether you're moving around at a different angle, how that little rubber pad interacts with the grooves, the different groove spacings, the different widths of grooves. Basically, simple paint gives a really good idea of what's being measured. So, practical. You're on a runway. You don't know whether to go in and take rubber off. You got a machine sitting there to take rubber off. How do you measure things? So you can turn up with sand, okay, the good old sand patch. Certainly in my country, in the UK, when something goes wrong in terms of texture, we fall back to the sand patch method as the definitive method. Lots and lots of other methods have been developed since, but basically it's good old sand when something goes wrong. We got a names device a few years ago, and we've been using it increasingly more and more. It's a nice, simple little device. It's a little laser device, gives you profiles, nice and accurate. You get a number that anybody can jot down, you get a GPS coordinate and all the rest of it, and it's fairly robust. I've dropped ours different times off the back of a van, and the thing keeps working. You can set it up to measure different profiles, and this is just, where are we? This is a grooved surface with 16 profiles. That's 16 measurements of a mean profile depth. And then the basic equipment will give you all sorts of other parameters. If I'm looking at a 3D surface and I'm doing a proper analysis, there's about nearly 90 different parameters that you can quote for a 3D surface. And these are just standard parameters, never mind others that you can make up. So if you go into the standard methods, the EN methods, the ISO standards, there's a lot of different ways of looking at those surfaces. It's trying to find the one that actually means something, which is the hard bit. So, in terms of sand patch versus Ames, that's what we got. Bingo. Couldn't have got it better. Little Ames device versus sand patch. For those test samples, almost perfect relationship. So, when I turn around and I've got somebody on a runway and they've got a bag of sand or an Ames device, doesn't really matter. The two results are going to give us pretty much the same result. They're not like for like. There is a bit of a difference between the two. So, what else can we do? Co-author, Phil Miller and myself, we've done a lot of work on photographs and what can you do with photographs. And we come up with a 3D method of take some photographs, make a 3D model. So I could photograph, I don't know, the bottle on that table, half a dozen photographs, make a 3D model. It's as simple as that. To go outside, 4 or 5 minutes, take some photographs, 3D model. As long as it's scaled, you can measure it. And again, this is a model here, one of the grooved surfaces, based on about a dozen photographs. And again, this is just, I don't have my phone, these are just phone photographs. There's nothing fancy now. And it just shows how the method is keeping up with modern technology. So everyone's phone, there's no need for a £10,000 camera and lens to do this sort of work. So 3D model, simple. What can you do with 3D model? Somebody talked about enveloping earlier on. There's a little green line there. The reason why it's all covered in paint, pink paint, is that we were looking at how the tire interacted into the spaces, into the cut grooves, and to try and get some idea of what's the depth in relation to the groove width or the spacing of the rib. Throw some paint on, roll it for a while, and the depth that the paint wears off, that's as deep as the rubber's going. It's not rocket science. And again, put this out onto a road. Now, you don't need good paint, children's paint, the sort of stuff that you can wash off the wall after they've gone mad. That's perfect. You want something that's going to last for literally 5 to 10 minutes. So, onto a road, into the wheel path, put some paint down, 10 minutes later, you know how deep tires are interacting with that surface. That's the contact depth. Space below it is just space. Important whenever it rains, because that's where your water goes. That 0.5 millimeter, or in this case, I don't know what it is, 0.6 of a millimeter is the depth that that tire was interacting with that particular groove. It is not massive depth. It's the tips of the aggregate particles. More tips, more contact points. That's how you're starting to mess around with the contact patch, generating the grip, the rolling resistance, the noise. So in terms of measuring all this stuff, there's not enough emphasis being done in that top, let's say, millimeter of these profiles, these 3D surfaces that we're all measuring now to great accuracy. And I think there needs to be a lot of work going into that tiny little bit of surface texture at the very, very top, because that's where the tire is interacting with the surface. And children's paint shows this. So where are we at? So, what we can do from a photograph, we can make a really good 3D model, but it has got limitations. All of these methods, we're trying to say what's good, what's bad. Sandpatch and Ames is good because the Ames is a laser, it goes straight down to the very bottom. If you're trying to get into the bottom of the grooves of the photograph, you can't do it. It's a thing called occlusion. So you end up with these V's. So if you're interested in lower down into, okay, what's the ability of a grooved runway to dissipate water under a tire of an aircraft, and you're basing your calculations on a 3D model taken with photographs, you're going to get a wrong result. But if you turn out with an Ames device, the laser is going to get to the bottom, and so on. So this is sort of where the different groove patterns come into it. Wider groove, you can get a better depth into it. Little tight grooves, all sorts of things going on there. So just little examples. You can do Abbott curves, you can look at volume parameters on the 3D surface of your groove patterns. Those are the two different groove patterns, just little Abbott curves showing the volumes at certain depths down into the surface. And again, these are samples that have had 75,000 wheel passes, so they're fairly knackered, and just showing how the surfaces, how the ribs and the grooves are wearing away. So each of the methods have got advantages. Sand patch, it's simple. If you want to fall back on sand, it ties in really well with Ames, with the laser measurement. And if you're interested in the top bit, the top few millimeters of your contact, in this case a grooved asphalt, then I would suggest the photographs, because you get a really good recovery of the 3D texture in those top 1 or 2 millimeters. So it's horses for courses, basically. The three methods each have got their advantages. They're all interrelated. All the parameters that you can get from your 3D surface, they're all interrelated. And it says just cherry picking the best parameter to go and quantify what it is that you're interested in. So Sandpatch, easiest to do. Ames is fast. Good correlation between the two methods. And then the 3D photographs is really good for that interface between the two, because it gives you so much more information than Sandpatch. Sandpatch gives you nothing basically about the interface. It's just a patch of sand, that's all it is. The Ames is better, but if you're interested in the 3D contact interface, the photograph method is by far the best. And in practice, I use all three. I use these methods, not say every day, but I'm going to resurface a racetrack next week, and I'll be using all three methods to keep the contractor on their toes. Thank you very much.
Excellent, catching up on time. Thank you, David. Please convey our appreciation to Chris and Jason for their contribution to the session. Our last speaker of the session is Amanda Alcantara. She here? Yep. And she will be talking about passive sampling calibration as an alternative tool for monitoring nitrogen dioxide in asphalt paving surfaces.
Good afternoon. My name is Amanda Alcantara, and I talk about passive sampling calibration as an alternative tool for monitoring nitrogen dioxide in asphalt paving surface. Sorry. I work in Federal University of Ceará, and my group research is trauma. The structure of these presentations is introduction, materials and methods, result discussions, and conclusions. Monitoring atmospheric pollutants by conventional methods is expensive, is dependent on electricity. Therefore, it is used in diagnose emissions in asphalt paving surface is unfeasible, especially in real contexts. As an alternative, the passive sampling method was proposed as a viable solution because it's consisting of low-cost device and that use the natural process of air diffusion to sample atmospheric pollutants. However, there is uncertainty in performance of these devices regarding sampling times and pollutant concentrations levels. Therefore, the objective of the study was to calibration a passive sampling method for quantifying nitrogen dioxide designed to monitor air quality and photocatalytic reduction of the pollutants in asphalt pavement in laboratory in real context. Device consists of Teflon cylinder with a filter impregnated with a selective absorber solutions for nitrogen dioxide. The prepared device were placed on acrylic supports and exposed to ambient air for different periods of the time and the different locations in the city to evaluate the system behavior. After complete the pollution collection periods, the filters were analyzed by UV spectrophotometry, and the pollutant concentration present in the air was determined by Fick's law. Fick's law considers the pollutant mass obtained in the chemical analysis, the gas properties, and device geometry to measure the air pollutants concentration during sample periods the time. The others, hours and days. The concentration obtained by the passive sample methods was compared with those obtained by the mobile air quality station from Fortaleza City. Its use on electrochemical analysis was a method sampling in quantification the pollutants. Such sampling campaigns were carried out. In campaigns 1 to 3, the samplers were located in the same environments where the mobile air quality station is located: the beachfront, arterial road, and bus station. The campaigns 4 to 6, the samplers were allocated in real contest the paving services. Therefore, sampling times were determined according to execution of each speed. Asphalt mix plant, 3 days. Transportation asphalt mix 30 minutes. And placement 1 hour. Result and discussions. The first campaign was carried out in coastal environments. The pollutants was detected only after 1 day of the sampling. The second campaigns occur in urban environments. The pollution detection time was reduced to 12 hours. The third campaigns were carried out in a bus station. The sampling time was reduced to 6 hours. The concentrations increase 2 to 3 times among campaigns. Meteorological conditions may have contributed to the difference in detection times. Since the presence, strong winds, and speed wind may have produced a wash effect and pollution dispersions. In terms of concentration, the data obtained by passive sampling are consistent with data obtained by air quality stations, which make it possible to access to correlation of these methods. The correlation graphics analysis evidences that the environment pollution concentrations seems to show the same behavior over the time. Above increase on the campaign 1, decrease on campaign 2, and stability in campaign 3. This suggests that the passive sampler is sensitive to environment regardless of its concentration levels. Correlation matrix data, it could be noted that passive sampling is strongly correlated with certified sampling, especially at higher ambient concentrations, bus station, for example. Besides that, the passive sampling showed a strong correlation with sampling time at lower concentrations, while at higher concentrations, the correlation with sampling times was not conclusive, ranging from negligible to moderate. The same behavior occurs in the air quality stations. The data from the paving service show that the proximity between a pollution source and pollution concentration level is also important parameter to be evaluations as it seems to favor the gas diffusion and pollute capture by the sampler. Ordering the concentration Other the concentration levels with their referred environment and sampling times, the environment pollutant concentration seems to be preponderant compared to be sampling time. The passive samples register conclusions, sorry. The passive samples registers The passive samples resist pollutants after 6 hours when exposed to low pollutants level environments, ambient air, and 30 minutes when exposed to high pollutant level environments, pavement services. It showed that the exposure timing and pollutant level concentrations influences the efficiency of the passive method. Also, the present study showed the potential of passive sampling as an sensitive and suitable method for diagnose emission in asphalt paving service. Upcoming work is, the present study suggests new gaps in the passive sampling methods and its use as an auxiliary method to studies of asphalt emissions. Therefore, it is intended to plot a calibration curve, concentrations versus time sampling on the controlled laboratory conditions to calculate the calibration factor methods. Furthermore, it is intended to test the passive sampling device as a method to evaluation the photocatalytic pavement efficiency in reducing nitrogen dioxide in laboratory in the real context. I would like to thank our research partners for their support in development of this work and everyone for their attention. I'm leaving my email for contact and thank you so much.
We have about 10-15 minutes for questions and answers from the floor, audience. I can see everybody. Very excited about going to the reception. I do have a question. Okay, Gerardo, go ahead.
Thank you. The question is a little bit generic, but maybe for Luke in particular. It's when we talk about rolling resistance, we typically talk about various components of that. We have one that is due to macrotexture, one that is due to the IRI, the roughness, and then the pavement deflection. Does the trailer capture all of that, or mostly the macrotexture one? That's my main question.
Actually, mainly the macrotexture one, which is actually the most important. So you have some contribution from the unevenness, but the contribution from the deflection of normal roads is second to third order effect. So it's you can calculate it when you have some deflection. Actually, you could imagine that you are trying to roll out of a valley that you create by deflecting the surface, but the effect is a bit small. It's maybe 1% of the contribution to the rolling resistance in the case of trucks. That's the worst, but the deflection is much smaller with small axle loads by car. So actually, you can forget about that. But the IRI is a bit more important, but we don't take it in our trailer.
Thank you, Luke. Okay.
Thank you so much for all your presentations, which were very interesting. Working from a perspective of a road agency or a private concessionaire, rolling resistance is actually an issue that we have to take into account very deeply. And I really enjoyed what Professor Goldberg said about rolling resistance and saying that we have to minimize it. But from your experience, and this question is for all the presenters that feel more comfortable in answering it, from your experience, what type of pavement surface layers would give better results for a low rolling resistance, and how can we maintain these surface layers with low values? Thank you so much.
Thanks, very interesting question. The texture is playing a major role, and how you achieve this texture, the material is not that important. So you can have low rolling resistance surface in concrete and in asphalt. Of course, skid resistance and rolling resistance are sometimes in conflict and sometimes not. At low speed roads, actually, you can combine both low rolling resistance and high skid resistance, because you don't need to maintain a high an MPD. At high speed roads, you need a minimum of MPD for road safety. To avoid aquaplaning. So for highways, you need to have some texture. And at least international research has shown that you need at least 0.5 as an MPD on highways. Actually, I would like that the road authorities in Europe would lower the MPD closer to this limit value to keep it safe, but what you have in excess of that is actually contributing to your rolling resistance. Actually is not good. So we should reduce our MPD values to 0.5, close to that, 0.5, 0.6 to be on the safe side. So how you exactly, which material you do it, that is less important. But of course, there is research on pavements with low rolling resistance. The thin asphalt layers have a low rolling resistance, so they can be interesting to be used to abate the CO2 emission. So that is but in concrete, so with this NGCS is also interesting. But then, of course, when you go to this, only look at this thin asphalt layers, you have, of course, other inconveniences, like the durability is less good. So when you reduce the size of your maximum aggregates, so then your durability, your noise goes down, that's good. Your rolling resistance goes down, is also good, but then your durability goes also down, and that's less good. So it's a compromise that you have to find.
Thank you, Luke.
First, thank you very much. I think there's a lot of exciting and interesting presentation. I would like to follow up that question that earlier mentioned about, I have that curiosity too. Kind of interesting in terms of rolling resistant, finding how can we utilize that in practical application. So based on that understanding, is there cases that when the pavement deteriorate, and the MPD maybe is changed. Is that, I'm just thinking about if I'm an agency, there's a high traffic volume, like in Atlanta, some of the roadway there, almost 250,000 vehicles per day. So if you drop down to a certain point, would that be reduced in terms of fuel consumption? Or, I mean, I'm just trying to see that in what way there, in different traffic volume roadway, if that MPD or whatever rolling resistance, that kind of information as a transportation agency, can they provide me to make some big judgment? Because if there's a huge amount of vehicle there, if some of those change there, if I take a certain action, do a resurfacing, multiply that huge number there, then maybe I gain a whole lot, maybe not a transportation agency, but the general public in terms of fuel consumption. So just try to get your input in terms of what do you suggest in terms of pavement deteriorated or low traffic road. I think you previously mentioned a little bit. So you maybe have some suggestion for transportation agency how they should do maybe in terms of making decision resurfacing a roadway. Yeah, thank you.
Professor Paulo, I need another drink today because I've been going back and forth, right? A lot of great questions.
And unfortunately, when pavements get older, the noise is generally going up, and also the rolling resistance is going up when you have wear that's maybe in the very, very beginning, when an asphalt is being laid, that you have some compaction that could, in the first 1-2 years, that you have a slight reduction of rolling resistance. But when you start to have some wear, then the MPD will go up and your rolling resistance will go up as well. It certainly is that in your pavement management system that in the future you could take rolling resistance as one of the parameters, and then maybe even if it is still in a reasonable state and it's still a reasonable skid resistance, but the rolling resistance has gone it's too high, it's a reason to replace it. Actually, a general rule is that from a rolling resistance, that the more often you replace the newer, you keep your surface layer, the better. But of course, this has also limits financially, and it's not the idea to replace your surface layer every year. But it certainly is something to take into account in future versions of pavement management systems.
I have a question for either David or Manuela. You know, one of those influencing factors we have seen in 2 or 3 presentations is the tire temperature. I don't do rolling resistance work. I was kind of surprised. I mean, do you really get that much temperature differentials in tires that will make a difference on the results? Anybody wants to answer? I come from a place, Phoenix, tire, the car, the pavement surface, the water, everything is the same temperature, very hot in the summertime. So I'm kind of surprised to see the images. And do you want to answer that?
In fact, in the laboratory test developed in the framework of this project, we measure the temperature and we make a correction of the rolling resistance coefficient based on the temperature of the rubber pad, because we have some variation when the cones are rolling on the pavement surface. Depending on the texture of the surface, you don't have the same excitation of so you have variation, and they are included. It was not presented here, but there is a temperature correction function, and this temperature correction function is on the same principle than the temperature correction function you can find on trailer or even on a real car. We have some dynamometric wheel on the experimental car, and we make the same kind of temperature correction. It's a linear, and we adapt the coefficient of correction to the rubber characteristics, in fact. So it is included.
Sorry. Add anything to it? Okay.
Yeah, so what we found sort of in our little drum, again, we ran all sorts of textured surfaces on the inside of the drum and did all those experiments and then brought a right back sample. And whenever we found out that tire companies use sandpaper when they're running tires. Okay, so we put sandpaper on the inside of our drum, fantastic surface, and you're playing around with microtexture, and it has a difference. Once you bring it up to speed, the temperature, how quickly you get up to speed depends on the surface that you're running on, depends on the load and all the factors that you can think of. Everything has an influence, and depending on what the combination of factors are, you end up with an equilibrium condition, an equilibrium temperature. And that's what you find in the laboratory when you do these sorts of experiments. And the same thing happens out in the road.
Any other? Yes. As I showed in my presentation, in fact, not only the temperature of the tread, the tire tread which is outside, but also the inside temperature affects the way the rolling resistance and probably noise or skid resistance behaves. So what we have seen is the difference of about, let's say, 20 to 25 degrees centigrade from outside to inside temperature, which is very significant. So I would say yes, it does.
Other questions? I had a question for Iran. So the size of the droplets when they freeze, do they make a difference? Because eventually they will all freeze, right? Do they make a difference in terms of the safety of the ice formation, all of that? Can you make a comment on this? Is the product that you apply, does it really limit the size or the diameter of those droplets?
Regarding the observation of the water drop, we place 5 microliters of the water drop over the asphalt sample for both situations, even for the water contact angle. And during the time, it spreads a little bit. We can see this. And if we have, for example, more hydrophobic samples, we will have a kind of a sphere. So the sphere is like spreading like this, you see? I don't know if I answered, yes?
Others? Well, we would like to thank all the speakers again for a great contribution to this session. Maybe a big round of applause for all of them. Probably a couple of announcements.
Thank you. So before leaving, please follow Professor Paulo Pereira. He'll take you in a walk to our reception that is near the castle, so our palace. And I'm sorry, but you will be walking again, so take a bottle of water. And the reception starts, well, in 20 minutes is the time to arrive there. I'm sorry. If you want to go to the hotel, no time to go to the hotel. And tomorrow, it's a very important announcement. Don't miss the start, because we start at 8:30, so earlier than today. And thank you very much for being so resilient, because our program is very demanding. And thank you again. I'll see you tomorrow.